Good morning. My name is Rod Alfernus, and I'm Dean of UC Santa Barbara's College of Engineering. It is an honor to welcome you to the second annual Center for Responsible Machine Learning Summit. Due to the ongoing COVID-19 pandemic, this is a fully virtual event. We are proud to welcome some of the top minds in the world to discuss artificial intelligence and machine learning related to COVID-19. My virtual backdrop is Henley Hall, which opened just last month. This 35,000 square foot facility is the new administrative home of our Institute of Energy Efficiency, It's also the home of Professor William Wang's Center for Responsible Machine Learning. This is a cross-discipline facility. We have learned that by diversity of background and interests, bringing faculty together in an environment to innovate and address major challenges for society, that cross-discipline collaborative environment is important. And we believe that Henley Hall will offer that opportunity here on campus. Hopefully in the near future, you will be able to visit our campus and see the state-of-the-art facility that was actually entirely donor funded. I'd like to thank our sponsors, Evidation Health, AppFolio, and Amazon Alexa AI for your generous support. We greatly appreciate it. I'd also like to welcome and thank our distinguished panel of speakers who are joining us from across the nation to discuss their innovative research to address this very challenging issue that COVID has put upon us. At UCSB, we recognize the importance, especially in today's world, of supporting AI research and development. We invested in the Center for Responsible Machine Learning last year, and through multiple initiatives and others on other campus efforts, especially those led by researchers like William, we are ensuring that UC Santa Barbara will be a leader in the ever-expanding field of AI. Nearly all of our classes this quarter, like they were in the spring and in the summer, are being held remotely to ensure the safety and well-being of students, faculty, staff, and community. Research, however, continues to ramp up in phases across campus in a responsible and methodical manner. In addition to helping solve the shortage in our community of PPE and testing kits, many of our UCSB researchers have shifted their focus to tackle COVID-19. The projects on campus range from UV lighting to destroy the virus, to a new material for vaccine syringes and vials, to a faster COVID testing based on CRISPR technology, and designing new algorithms to provide more accurate local COVID-19 forecasts, which you will actually hear today at the summit. These are just a handful of the UCSB researchers, like many of you, who are working tirelessly to make our lives safer and healthier and restore a sense of normalcy. They, like many of you, are prime examples of a culture of innovation and collaboration that drives new technology and discoveries that can make a difference in this world. And indeed, COVID-19 as a challenge is formidable, but together we can address this serious threat of COVID-19. So again, I'd like to welcome everyone to our summit. I wish you an enjoyable and a fruitful day, and we hope to see you on campus again. Until then, be well and enjoy today's summit. Thank you.
Welcome to the second annual meeting of the Responsible Machine Learning Summit. I'm your host, William Wang. I'm also the director of the Center for Responsible Machine Learning here at UC Santa Barbara. The CRML, short for Center for Responsible Machine Learning, was introduced in spring 2019 with a special focus on the study of bias, fairness, transparency, responsibility, accountability, in the context of a wide range of studies related to the ethical, policy, and legal implications of AI and machine learning. Right now, we are actively working with many initiatives on campus to strengthen our work along this line. So these sister and brother initiatives, including the Mellencamp Initiative on Mind and Machine Intelligence, the Data Science Initiative, the Institute for Energy Efficiency, Center for Information Technology and Society, and also Institute for Collaborative Biotechnology. At UCSB's CRML, we're actively engaging academia and campus in a wide range of programs. So right now we have 60 faculty members that are affiliated with this center. They're coming from more than 20 different departments and programs on campus. So in addition to this annual event, we also have distinguished lectures, and we're developing other academic programs as well. Now, I'm very proud to say that I think this is very important because we do also want to go beyond UCSB and trying to encourage the multi-institutional research efforts on responsible AI. And with our industry engagement, right now we are actively developing our corporate affiliate program, and I'll introduce our founding members of the corporate affiliate program towards the end. Now, a very important thing we care about is our students. So we just created the CRML PhD Fellowship, and this is really to award the best and brightest and to help them to support their study here at UCSB on the topics related to machine learning and AI. We're also actively working with many parties and shareholders and want to support the underrepresented minority students and help them pursue the study of AI and machine learning. So please let us know how you want to get engaged, and we're very happy to work with you. The CRML 2020 Summit is a very special event because this is a virtual event, and it is also a special focus on AI and COVID-19. So we have a list of wonderful speakers who are leaders in various international organizations who are at the forefront of using AI and machine learning fighting for COVID-19. So today we have 3 distinguished keynote speakers. Oren Ezioni will be our opening keynote following my opening speech. So Oren will talk about NLP and also how we can use Semantic Scholar to fight against COVID-19. And in the afternoon, Ryan Tibshani will talk about CMU's Delphi project, focusing on looking at COVID-cans and how we can use machine learning to predict and forecast the outbreak of the disease. And at the end of the day, Janae Wing will cover trustworthy AI, which is a very important angle that our center is focusing on. And we have a special panel this morning, and Lynn, Sarah, Oliver, Andrew, and Prem will discuss the impact of AI and machine learning and how we can use them to fight against COVID-19. And in the contact tracing session, we have 4 world-leading experts, Cynthia, Luca, Jeff, and Lisa. They will tell us issues relating to creating contact tracing apps and how do we model the human mobility and how we can responsibly trace the outbreak of the disease and also the contact. Well, in the health data processing and resources session, we'll hear from Luca, Florence, and John. They will cover many important issues relating to processing the health data. And following that session, we have an exciting forecasting session that will be led by Chen Chen and our own Xifeng Yan from UCSB. Before the closing keynote, we have very important vaccine design and also virus localization session that will be given by Liang and also James. So this is a very exciting day of program, but before we go to the actual program, let me tell you a little bit about logistics. So for each of the keynote talk, at the end of the talk, please remember there will be 1 live QA session, and also for each regular session, we also have a QA session that's going to be live, and there's going to be a group of speakers from that session. So please, if you have any questions at any point, feel free to type your question in the chat, and the session chair will be able to go to a question at the end of the session and will address your question. Now, finally, I want to acknowledge all these organizing committees for helping us, and I want to thank you for joining us today. Specifically, I want to thank the co-chair Yuxiang Wang, the organizing committee chair Laura Langen, Rob Dunton. I want to thank the session chairs RP, Misha, Ambuj, and Joe, and also our publicity DEFCON team. I have my special thanks to the campus leadership for sponsoring and supporting the Center for Responsible Machine Learning, and also our founding members of the CRML Corporate affiliate program, Evidation Health, AppFolio, and also Amazon Alexa. So thank you very much for joining us today, and I'm looking forward to a day of wonderful program. Thank you.
Good morning. My name is Oren Etzioni, and as you know, I'm the CEO of the Allen Institute for AI, or AI2, and also a professor emeritus at the University of Washington. It's my pleasure to talk to you today about Semantic Scholar, NLP, and the fight against COVID-19. I'll start with the very broad question, is AI good or evil? Which is surprisingly controversial, even in AI circles. I'll talk briefly about AI2, the Allen Institute for AI, and our mission, AI for the Common Good. And then I'll focus in on Semantic Scholar, our free academic search engine available at semanticscholar.org. And I'll explain how the capabilities we built in there allowed us to rather dramatically launch Cord19, an open resource for people wanting to track research on COVID-19. We launched that in March of this year. And I'll end with some thoughts about AI and science into the future. We need to start with the fact that for many people, AI evokes fear. And this isn't just folks who are ignorant. Folks like Nick Bostrom from Oxford, Max Tegmark from MIT, and Stuart Russell, who's an AI researcher at Berkeley, all talk about how AI could potentially spell out doom for the human race. Elon Musk, with his gift of gab, says, with AI, we're summoning the demon. In contrast, we have folks like famous roboticist Rod Brooks, who says if you're worried about the Terminator, just keep the door closed. And of course, through the wonderful abilities of reinforcement learning, this robot will eventually figure out how to open the door, only to find out that there's a staircase behind it, and it can't navigate the staircase. Eventually, it'll learn to do that, but there's another challenge and yet another one. So in short, we have a long way to go. The way Andrew Ng put it is that working to prevent AI from turning evil is a bit like disrupting the space program to prevent overpopulation on Mars. It ignores both the substantial technical difficulties, we haven't even gotten a single person on Mars, and of course the potential benefits. In fact, if AI is as dangerous as Stuart Russell says, we better get to Mars ASAP. So you have very smart people banding intuitions back and forth. In an article I wrote in MIT Technology Review earlier this year, I tried to put the conversation on a more empirical footing. Rather than arguing conceptually or philosophically, I tried to identify some tripwires, lines that if we cross, mean that superintelligence or human-level intelligence is approaching. I called these canaries in the coal mine. Canaries in the coal mines of AI are signs that we really are approaching human-level intelligence. Let's talk about one example. Let's talk about machine learning, which of course is the topic of our meeting today, the summit, as well as the tide that's lifting so many of these AI boats, both in research and in application. The thing to remember is that machine learning today is still 99% human work. If you think about the inputs to, say, a deep learning program, the target concepts, the labeled data, the algorithm, the design of the neural network, so many of these things, if not all of them, are determined manually. Of course, there's also deciding to invoke learning in the first place and assessing the output, whether it's satisfactory. And this is a frequent loop, again, all done by humans. The machine really only does the last mile of learning. Once all this has been set up, then it does the statistical computation to output a predictive model. So really, I think of machine learning as somewhat of a misnomer. It's kind of like saying that baby penguins fish. As you see in this video, what actually happens is the parent penguin decides it's time to get food, decides where to go, finds the fish, hunts them down, eats them, and then regurgitates pre-chewed morsels to the baby penguin. So machines don't learn any more than baby penguins fish. And this suggests a key AI canary. If we had programs that could automatically formulate machine learning problems, they would be working in their everyday context and realize, hey, I really need to sub-goal on learning something, maybe learning how to give a better talk in the time of COVID, whatever it is. That would be a major canary in the coal mine. But the successful machine learning systems we have to date don't do anything like that. In fact, it was a topic of research in the 80s and 90s with folks like Tom Mitchell and the late Alan Newell investigating that. But largely, this area of research has gone by the wayside in modern machine learning. So the bottom line is this: AI is a tool, not a being, and it's up to us, of course, to employ this tool or set of tools to benefit humanity. The Allen Institute for AI, founded by the late Paul Allen in 2014, is aimed at doing that. Our mission is AI for the common good. I've served as the CEO since the Institute's inception, and I'm pleased to report that we've done quite a bit of work in computer vision, natural language processing, and deep learning, producing over the last few years more than 300 papers in top-tier conferences and garnering something like 10 Best Paper Awards. We have more than 100 AI professionals. Our main location is in Seattle. We also have a smaller location near UC Irvine in Irvine, California, and another one in Tel Aviv, Israel. And most importantly, we're hiring. So hope you'll join us. I don't have time to get into the various projects at AI2. We have the Arista project, which looks at reasoning, the Mosaic project that figures out how to endow AI programs with common sense, the Allen NLP platform, which is an open source platform for cutting edge NLP research built on PyTorch. We have a thriving and dynamic computer vision project that both deals with vision problems as well as tying computer vision to robotics. And we even have an incubator, like many universities do. We also spin off various startups. So it's a very dynamic place, but my focus today in the short time that we have will be on the Semantic Scholar project. And the Semantic Scholar projects attempt to address academic information overload. We all suffer from too many tweets, Facebook posts, email messages, Slack messages, etc. But the academics, which I think is most, if not all of us here, also have to read technical papers. There are more than 8 million new papers published every year, and our studies show that scientists read on the order of 200 papers a year. So even if you're trying to focus on your narrow subdiscipline, it's extremely difficult to keep up. In response to that, starting in 2015, we developed an AI-based scientific literature search engine called Semantic Scholar, with the goal of cutting through the clutter and allowing you to find the key papers, the key citations and results that you need. And I'll talk about that now in quite a bit more detail. At this point, Semantic Scholar covers all academic disciplines. Its corpus consists of more than 190 million papers, and we have upwards of 8 million users per month. And as this graph shows, that figure is continuing to grow. What is Semantic Scholar in essence? The basics are a few. We map paper PDFs to a literature graph where the nodes are authors, papers, topics, etc. And they're connected by various relationships. Like in this little subgraph, you can see which authors influenced John Kleinberg and which authors did he most influence based on an analysis of the citation graph. And we have this kind of influence graph associated with each author homepage. We also have a search engine, which allows you to search, of course, on keywords, but also on various aspects of metadata. And then a key part of Semantic Scholar is we have kind of a Wikipedia entry for each paper. Think of it, we call these paper detail pages, and they contain not just the paper and the abstract, but also automatically extracted figures and tables, the references and the citations, links to software, if that's available, a GitHub repo associated with the paper, slides that may help you understand whether you want to delve into the paper or not, videos of talks about the paper, mentions of the paper in various blogs and news, really as much information as you can to help you decide whether you want to read the paper or not. In addition to that, we've also been quite innovative in defining new citation metrics. We have a much more semantic notion of citations that excludes self-citations. And by the way, we've found that men tend to cite themselves substantially more than women. So our citation metric is more gender neutral. We also exclude incidental citations, the kind you add in the paper perhaps at the last minute or as a de rigueur obligation. Yeah, I should mention so-and-so's work in some long list of citations. So we exclude those, and instead we include implicit citations. Sometimes you may mention a body of work or a particular system without having an explicit citation to that. So we include that. And then we also rank these citations by the degree of influence. So we look at two papers and ask, well, to what extent was this paper influenced by the famous paper on self-attention? Is it just a mention, or did it really build on that work? And we have a learned model that does this by analyzing the text of the paper and allows people to home in and focus on the most influential citations. And there's a little bit more about that in a paper, a short note I wrote in Nature back in 2017. In addition to this more semantic notion of citation, which, by the way, allows us to highlight far fewer citations for papers than you typically see. On average, it's about 10% of the citations, which, of course, allows you to focus in much more on the papers and citations that matter. In addition, we look at the number of citations per year for a given paper. We call that citation velocity, and we look at the derivative of that, the change in the number of citations per year, and that's citation acceleration. These two metrics are very helpful to focus in on the most hot happening papers right now if you're trying to keep up with the state of the art and with the most important recent results. So at this point, I would typically give a demo of Semantic Scholar. I really do hope each of you check it out on your laptops, but in the interest of time, I'm going to continue. I do want to give you a bit of a framework, because it'll be relevant later, to explain how all these different features in Semantic Scholar are organized. Basically, we think of engagement of scientists with scientific papers in 3 steps. The first one is you discover a paper through social means. You see a tweet about it, you get an email about it, through search, or maybe just browsing an online conference proceedings. The discovery process is supported in Semantic Scholar with the search capability, with the unique citation metrics that I mentioned, with various filters, and also with recommendations. The field has done so much work in recommendations of products or movies, and we've applied that to the problem of recommending related papers. We all have our Twitter feed or our Facebook feed, and we've developed a research feed. So if you wake up in the morning and you want to see, okay, what's been published recently that's relevant to my interest, you can go to our research feed. It'll give you suggested papers, and you can give feedback, more like this or less like this, and the feed will automatically adapt itself to focus more precisely on your tastes. The next step, once you've discovered a paper, is deciding, should I ignore it? Should I give it a quick skim? Or should I actually make it one of the relatively few papers I'm going to actually read in depth this year? And again, there's a lot of features in Semantic Scholar to support this reading decision. Of course, we have abstracts, but we also highlight the key sentences in the abstracts. We determine automatically which are the most informative sentences in the abstracts. As I mentioned earlier, we extract figures and tables automatically so that you can quickly peruse those and decide whether you want to read the paper, and that's particularly handy on a mobile device like this one. We filter, analyze, and sort the citations to give you access to the most important ones. And we also give you citation excerpts. I find one of the most helpful ways for me to understand a paper is I go and look and see what other people have said about it, particularly people who've looked at it in depth. And we make that easily accessible on the Semantic Scholar paper detail pages. And then the last thing, which was just launched, is what we call extreme summarization, or TLDRs. And this is a paper that was just accepted into EMNLP. What we do there is we look at the paper and the abstract, and we attempt to summarize it in a single sentence, a TLDR. So in this example, this rather long abstract, probably hard to read, is summarized by, we develop a new topological complexity measure for deep neural networks and demonstrate that it captures their salient properties. The TLDR is generated by a generative language model. Think of something like GPT-3, but tuned for scientific summarization. And we've launched this now for millions of papers on Semantic Scholar in an A/B test. So if you go to Semantic Scholar, you might see TLDRs, and if you do, we'd love to get your feedback, or you might not. In that case, it should be available for all computer science papers and all users quite soon. The last step in the engagement process is, okay, we've decided to read the paper, and of course now we want to understand it, retain the key information, and potentially even cite it in our subsequent work. And with there, we've started building, and this is joint work with Marty Hurst and Andrew Head at UC Berkeley. We've started to develop an interactive reading application that explains the paper's lexicon and the paper's mathematical concepts. Again, unfortunately, I don't have time to give you a demo of that, but if we have time, I'd be happy to do that afterwards. It's actually really, really cool. So I've done a whirlwind tour through the various features, but I want to also highlight that really what's happening here is a fundamental sea change in what we're doing in NLP. Traditional NLP, which dates back to the 50s and Harris's famous distributional hypothesis, you will know a word by the company it keeps, looks at local context. For example, the BERT program, which was developed based on our own Elmo embedding program, looks at something like 500 tokens, 512 tokens around a particular word. And a lot of NLP work is focused very much at the sentence level. We parse sentences, we translate them, we do information extraction from sentences. We found that to do the NLP we need for Semantic Scholar and for analyzing the scientific literature, we really need to think about document level NLP. How do we process a full document or even a collection of documents? So that means question answering is done not based on a sentence or maybe a paragraph, as in the famous SQUAD dataset, but over an entire paper or even multiple papers. We need to work on summarization. And particularly importantly, the context that we use in Semantic Scholar, based on a model called Longformer, is 60 times bigger, 60 times longer than previous context, which allows us to encode full papers in the context. And now, of course, we're thinking about hierarchy within papers. What are the most salient aspects of papers? All kinds of questions that come to the surface when your contexts are so long. This is a major technical achievement, required us to figure out how to do attention in linear time rather than quadratic time, and et cetera there. So with all this framework in place, it was surprising and yet not surprising that the White House, the Office of Science and Technology Policy, reached out to us through a colleague at Georgetown University on March 6th of this year and asked us to put together a machine-readable corpus of all the papers relevant to COVID-19, about coronaviruses and so on. And we asked them, okay, when do you want to have this done? And they said, yesterday. And I'm very proud of our team. Within 5 days, we were able to put together this unified corpus, and we launched it to the public within 10 days. So March 16th was this launch. We were able to form partnership with a wide variety of institutions, including the Chan Zuckerberg Initiative, preprint servers like bioRxiv and medRxiv, government agencies like NIH, and lots more. And so on March 16th, the White House announced this machine-readable COVID dataset called COVID-19 for COVID Open Research Dataset. And this got quite a bit of media attention. Fast forward to today, we now have more than 200,000 papers in the corpus. It's being updated daily as constantly there is new research on COVID-19 and new observations. The text is machine readable, but also the references and the tables, so that people can build AI tools, text mining and other kinds of tools to analyze the paper. And this was actually the basis of the most popular Kaggle competition ever. More than 2 million people viewed our data set, many of them driven by the Kaggle competition, which in turn generated a bunch of novel medical insights based on the academic literature. Wide variety of institutions got involved. I won't list all of them, but I do want to show you a few examples of the more than 50 tools that are publicly available today, building on the COVID-19 dataset. For example, AWS has a question answering system where you can ask questions like how infectious is COVID-19, what are prevalent antibodies in the saliva, and also more technical questions like are IL-6 inhibitors key to COVID-19? A question that frankly I don't know what that means. There's also a variety of systems. Here's one out of Korea University. We asked the question, what temperature kills COVID-19? And it provides the answer 56 degrees Celsius. And of course, the provenance, so you can dig into the paper and verify that, in fact, that's correct. And that's a good thing, because if you look at some of the other answers, they're not that good. So of course, this continues to be very much a work in progress. Excuse me. In addition, in joint work with UW, we've looked at scientific fact-checking. And so we can give this system claims and see to what extent the literature supports or refutes the claim. So for example, we gave it in a prototype demonstration the claim mass masking reduces COVID-19 transmission rate. And we see that in this subset of the corpus, we have one paper supporting that, and you can drill down again to the supporting text and the information. So again, very useful, and perhaps something that President Trump should have attended to more, but I digress. We also employ information visualization, and this is in the context of another system called SciSite, and this looks at the connections between proteins, genes, and cells as depicted in the corpus. It also is able to look at different topics in which scientific groups are delving into those and what the connections are between the different groups, either socially by co-authorship relationships or maybe topically. These are the purple links here. So again, I'm just going really quickly through these. The URL is here, and all these systems are accessible from the Allen AI website if you want to play with them further. The key point I'm trying to communicate is that we have done work that's really enabled the AI and medical communities to join together in this very important pursuit of both the vaccine and of clinical insights about COVID-19. Here's a wonderful quote from a colleague who's a clinical researcher at the Swedish Medical Center in Seattle. We've started to see medical articles utilizing COVID-19, either citing it explicitly or using it to find papers that provide key information and then citing those. There's a very quickly growing stream of these types of papers. And taking a step back, we really see a vision here that is for AI-based scientific discovery. So what if a cure for an intractable cancer is hidden amongst the thousands, if not tens of thousands, of reported clinical studies? We imagine that an AI-based discovery engine like Semantic Scholar could really help find a cure for a particular cancer, find a vaccine for COVID, find a better therapeutic drug, and really just help to answer some of science's thorniest problems. That's the vision we stated for Semantic Scholar back in 2015, and we're excited to continue to execute against it today. It's far from a solved problem. Now, going back to the beginning of my talk and these issues of is AI good or evil, I think it's clear to all of us thinking about responsible AI and responsible machine learning that AI raises a host of issues around privacy, around bias and fairness, around job displacement. But I want to come back to the question raised at the beginning of the talk with the remarks of Elon Musk and Stuart Russell and others. Is AI actually poised to destroy humanity? Is it an existential threat? And here I want to end with a quote from my colleague, Eric Horowitz, that really says it well. No, it's the other way around. It's the absence of AI technologies that is already killing people. If we had better AI, we could have better therapeutics for COVID-19 sooner. If we had self-driving cars, we could be saving lives on our highways every day. So AI is poised to benefit us and to save lives, not to destroy humanity. Thank you very much.
Thank you, Oren, for a wonderful talk. And now here we are going to the live QA session. We have many questions lined up for Oren. And let's start with the questions from the general attendees. So Ankita Prasad has a question for Oren. So how are the implicit and explicit citations for a particular paper detected?
I hope you can hear me okay, and thank you, William, for that nod. It is a very strange experience, I have to say, listening to the talk that I gave. Usually I give the talk, but I don't have to hear myself, so I'm a little bit shaky. It's kind of like looking in the mirror for an extended period of time. Anyway, to answer the question, let me describe the typical scenario. You know, we built back in the day a system called text runner, right? Text and runner. You know, they say that computer scientists are people who don't know how to use the space bar on their machine. So it can join one word. And what often happens in a paper is they'll cite text runner in the first mention, and then in subsequent mentions, they'll refer to, I don't know, Etzioni's system or the text runner without the citation. So because we analyze the text and we've built a model that sees the typical ways that the system is referred to, or different systems and papers are referred to even without the citation, we're able to detect that and construct a link between other mentions of text runner or that open information extraction system, what have you, and the original citation. So we don't lose those particular citations.
I see, thank you. Second question from participant Weizhe Zhang, and he's asking, we have timestamps for paper that is published, submitted, archived, and how would you be able to consider or use one timestamp as the published date? So how do you process the time in Semantic Scholar?
So The short answer is not very well. Let me answer a broader question. Basically, the timestamp, the different versions of the paper, slightly different titles for different versions, different ways to refer to the authors, sometimes with their initials, sometimes in different orders. All that creates a noisy paper space. And what we do is we try to map it to a semantic representation where a node in the graph has a single paper with a single title with the appropriate date, the appropriate venue, and the right authors. And this is something that we do. We're constantly monitoring and improving the accuracy of that, but it's highly imperfect. So you'll easily find examples in the 190 million papers that we have where the information is not 100% accurate. And if you think you can do better, what a great machine learning task. Please try it and share with us your approach.
Thank you, Oren. The third question from Hossein Mezadfar, and Hossein's question is, are we underestimating the danger of AI because of the current rapid leap in AI development?
I don't think that we are underestimating the danger of AI. I've talked to members of Congress, people in the popular press, and so on. People are very concerned about AI. And again, there are legitimate reasons to be concerned. We see there was just a recent announcement about how Google, even though it's very early days, has unveiled their riderless, I should say Waymo, right? Unveiled their riderless service in Phoenix. And of course, that's quite telling in the time of COVID-19. So millions of jobs or contract jobs for Uber and Lyft drivers are under siege. And I think that we really need to think about that. The good news is that people are. I feel like we are focused on making sure that AI responsibly serves the needs of society. That said, that doesn't mean that there aren't a lot of issues there, but we are as a community really genuinely thinking about that.
Great. The next question comes from Ivan Bekovich, and Ivan's question is very interesting. So he asks, can we use the techniques to summarize and explain papers be applied to writing better papers? And for example, how do we use the structural patterns that we learned to write better papers that could be easily understood by people and by machine?
So that's not something that that we've done, but I think that you're right. We have to raise, or that the questioner is right. We have to raise the level of discourse from just PDF files, right, where the metadata is often difficult to extract, and from just pure text because of the huge number of papers. So the same way that we have SQL, and that allows us to formulate queries over thousands or hundreds of thousands of records. We should be able to do that, asking questions like, okay, what is the state of the art on ImageNet 2? Or what are the most popular techniques used? And remarkably, it's actually quite hard today to do that because all the information is in text. I do think that it's within reach with modern NLP techniques to change that and to be able to map things to a more structured format. Now, the question was, how can we help? And of course, putting more metadata manually on papers helps. Correcting the metadata that's extracted by the machines. For example, Semantic Scholar would love to have a dialogue with authors that says, look, here's what we extracted. Any mistakes here, anything you'd correct. And of course, if you make a correction, this becomes labeled data for future instances of the machine learning process. It's a form of active learning. So I think that's a very rich and exciting area, but one that's just getting started.
I see. Thank you.
here's another very interesting question from Tefik Balton. So, there are this industry that basically takes money from authors and publish fake papers and having this fake journals that cite each other's articles. So is semantic scholar vulnerable to adversarial attacks that create fake papers that cite each other? So how do we prevent, the system being manipulated by adversarial attacks?
Well, if there's anything that we've learned, right, in recent years in machine learning, is that all our models and our systems are, whether they're in computer vision or elsewhere, are right, vulnerable to these adversarial attacks. Now, in this particular domain, we have a few things that help us. First one, as I mentioned, we avoid self-citations, right? People are already gaming citations with self-citations. We avoid that. Of course, as the question was mentioned, right, you can create a group of people citing each other and defeat it that way. I think that our best bet is the fact that it's a highly transparent system being viewed by millions of people. So to the extent that people generate these cliques that promote things, people can point it out to us and we can try to address that. I think that we do try to only use bona fide venues. So we actually recently delisted millions of papers that were effectively, kind of gray literature of the sort you're describing. So really the situation is that it's kind of an arms race, kind of like email spam or web spam that Google and others deal with. We find ways to identify and remove fake citations and fake papers or venues that aren't bona fide, and other people come up with ways to game the system that we haven't thought of. In particular, with generative models like GPT-3, right, there can be increasingly legitimate seeming papers that could fool our models, and that is one of our current concerns.
Thank you. Here's another interesting one. So I also from Ivan Bekovich. So he asks, how do we reduce the bias in paper citations by automatically suggesting citations that might be more appropriate than the choices that the authors made?
Right. So again, a great question, and this is actually one that we've worked on. So we built a system called AutoCite, where we said, hey, if you look at a paper and its citations and you view the citations as labels, this becomes a very nice self-labeling machine learning problem, right? We can build models based on literally millions of papers and their citations to try and predict what citation you auto-include, you should be including in future papers. And we've done that, and we found that unfortunately the precision of that, so we applied that to then papers where the citations were held out, the precision was quite low. So we can automatically suggest citations, but often they're not that relevant. So it's something that we need to improve, and the data sets are there. Now the question then goes beyond that and says, what if we don't want to just include citations, but we also want to reduce bias? And of course, we can change the loss function in the predictor to do that. We can take into account demographic factors like gender, or like how early is the person in their career, right? We tend to cite maybe more established authors, which has all kinds of negative things. We can introduce diversity into the loss function and say, okay, we're not just going to maximize the accuracy of the prediction, but we're also going to try to be more diverse in multiple senses of the word in that suggestion. So this is actually something that we've taken a first stab at, and the data sets are publicly available for people to continue to work on this problem. And I agree that it's an important problem. With all these online systems, we have what's called, the rich get richer phenomena, right? Where things that are popular or things that have a big name tend to attract more attention, and then that becomes a feedback cycle. But we can actually fix that.
Great, thank you, Oren. So we have another very interesting question from the participant, Carrie Oster asks, how do we engage high school students to participate this AI research?
Well, I think that we really need to start much earlier in teaching people what I would call digital literacy. Just the same way you need basic math skills, basic reading skills, you need basic computer and statistical skills to be a responsible citizen in our society. And of course, those are the foundations from which we can build AI participation. It's sad to me that even in some of the top schools in this country, where kids are in elementary school and they could already be engaged in this, there's relatively little of that. They all have, or I shouldn't say they all have, some of them have tech classes and digital literacy, but it's often learning to use features of PowerPoint. Maybe if it's really fancy, they'll learn to do Excel, as opposed to learning to program. Now, of course, organizations like code.org and others are working to change that, and it'll take time. So I think the first step is you build a foundation early, and elementary school is definitely not too early. Then when you get to high school, we do have a tremendous number of resources from Coursera, code.org, Khan Academy, and many others, where you can come up to speed. And a lot of the frameworks, let's say TensorFlow or PyTorch, and also frameworks like Allen NLP that we've shared, are all open source, and they have good tutorials and so on. One of the challenges, of course, is compute power. A lot of things don't run very well on a laptop. Take GPT-3. So I think that the next step is to pay more attention to what's sometimes called model distillation, but I just think of it as AI in a box. Okay, it should be the case that kids with a laptop can run AI software and be able to participate in tinkering and playing, and even in innovative research.
Great, thank you so much, Oren, again for the wonderful talk, and we really appreciate you for also this very insightful Q&A session. Now this concludes the first keynote talk, and we'll move on to the first session of the day, which is the contact tracing session. Thank you again, Oren.
Thank you, William. It's a real pleasure.
Hi, I'm Elisa Redmiles, and today I would like to speak to you about how to responsibly get Americans to adopt COVID-19 apps to improve public health. So computational problems of all varieties require constant decision-making. So in cases we're more familiar with, when we build machine learning classifiers, we're often having to make decisions about what features are fair to use when we're trying to predict different things, like, for example, someone's chance of committing a crime. In the case of coronavirus apps, we need to understand what data is appropriate to be used and which features we should prioritize when we're building these apps. And typically, as experts, we're the ones who set the best practices. We decide which features are fair to use or what data is appropriate for coronavirus apps. And as experts, when we make these decisions, we're trying to trade off costs and benefits. So in the case of coronavirus apps, we're trying to think about the benefit to public health versus the risk to individuals' privacy if we collect certain pieces of information. Similarly, in the case of machine learning classifiers, we might be trading off classifier accuracy against the unfairness of including particular features. And experts do not always agree on these best practices. So we've seen this in various cases in machine learning, as well as for coronavirus, both in terms of apps, as well as public health decisions about how to tackle the disease. And perhaps more importantly than experts disagreeing with each other is that experts and the users who have to use these systems may disagree. So experts' view on the trade-offs, the appropriate trade-offs between benefits, say, to public health and risk to privacy might not be the same as users' view or preference for how those things should be traded off in the applications that they're supposed to use. And this tension between experts' prescriptive best practices and non-experts' preferences or behavior, which they express by, say, choosing to download an app or not to download it, is a classic tension in moral philosophy, which frames this as a normative versus a descriptive approach. And we don't necessarily have to solely take one approach or the other. Usually we want to try to find a balance where we learn from non-expert behavior and express preference, and also apply some expert knowledge to protect people in cases where they may not be able to fully understand or express their preferences. And these descriptive ethics kind of approaches where we look at what the end users want and what they prefer in order to make computational decisions have been used in a number of different computational problems. For example, we can use them to identify ideal or acceptable functionality based on people's expressed preferences or natural norms. In the talk today, I'd like to speak about some work that I've been leading at Microsoft Research where we're using descriptive ethics as a way to understand how to create contact tracing applications and provide guidance for different organizations on what people's preferences would be around these applications. And why do we care about people adopting contact tracing apps? Well, for any public health app, adoption, of course, matters because we're going to improve public health, hopefully, by people using the app. But this is especially true for contact tracing, because with contact tracing, the benefit of the app scales quadratically with the number of users. So we need not only the infected person to have the app, but also the people who've been near that infected person to have the app. And so adoption is especially critical for contact tracing. When contact tracing apps first got brought up, much of the research community in computer science was very focused on privacy concerns, not just as a way to encourage adoption, but also as a guard as experts against making sure that appropriate data use was taken. And in this talk, I argue that appropriate or responsible data use involves not just privacy, but also respecting what users want in return for using these apps or using their data. And that goes beyond privacy to include benefits and their expectations for various other parts of the apps that we need to be aware of and respect when we're developing these in order to not just encourage adoption, but be responsible and respectful expert practitioners. So there are many possible inputs to someone's decision to install a COVID-19 app. So they might be interested in the benefits for themselves or for society from installing the app. They may make different trade-offs depending on who's providing the app. Is it coming from the CDC? Is it coming from their employer? Is it coming from a tech company? Of course, privacy and how much privacy risk will factor into their decision. How much mobile costs? Is this going to use my mobile data? Is it going to use my battery life? And while these are not necessarily always considerations that are in the forefront of our minds, particularly for users with different socioeconomic statuses or in different countries, different kinds of cell capacities and mobile data plans may make this quite critical. Users may care about accuracy. How well is this app going to work? How often is it going to be able to notify me of an exposure? And finally, related to privacy, things around data agency. Is the data that's being collected by the app stored on my phone? Is it stored in a central server? Do I have control over deleting it? And so forth. If you're interested in how these different user trade-offs align with different contact tracing and coronavirus app architectures, I've linked to a paper at the bottom of the slide that goes into more depth. In this talk, I'd like to address two research questions. The first is, which of the considerations I just discussed are important to future users of these coronavirus apps? What are their highest priorities, and how do we make sure that we respect those priorities? And the second research question is a case study showing that we can use descriptive approaches, so use people's opinions and our measurements of those opinions to predict their intent to adopt these apps. So we can actually understand what kind of benchmarks we might want to set for these applications to reach certain relative levels of adoption. So addressing the first research question, we conducted a series of conjoint analysis studies. And conjoint analyses are typically used in economics and marketing research in cases like these, where there are a number of different trade-offs that people can make. And it's not ethical or maybe possible to test them in real life. So I don't want to release a bunch of coronavirus apps that have privacy issues or accuracy issues just to see how people react to them. So I'm going to have them make hypothetical trade-offs as a way to approximate what they would do in real life. So in these conjoint analysis surveys, we provide people with carefully designed and tested scenarios, as well as some attention check questions to make sure that they understand those scenarios. And once they've gotten through the scenarios, they're asked to look at pairs of apps. And we provide information about the accuracy of the app, mobile data use, battery life use, information risks, privacy risks, benefits, etc. And people can pick between one of the pairs of apps or say that they wouldn't want any of those apps. And they make a number of these comparisons that allow us to infer how they're rating these different features. To provide a little bit of background, this study was conducted quite recently. We use a quota sample across the US to try to match the demographics of the census to make sure that the people that we're surveying are representative as much as possible of the United States. As I mentioned, people pass attention check questions, so we make sure they're paying attention and they understand the scenario. This was joint work with Dana Tjurman at the University of Michigan, and we're happy to provide more methodology details upon request. So what did we find out from running these surveys? Well, the research community was definitely right to go after our privacy and data use. That was the most important part of people's decision to install a particular coronavirus app. But people also care a lot about accuracy, how accurate these apps are, how well they're going to work. And that goes back to the point I made at the beginning of the talk, that responsible data use is not just about how we protect people's data, but also what benefit they get back from giving us that data in the first place. And accuracy is a big part of that. We see that people do care, although much less so, about the benefits of the app, mobile data use, and battery life. But something that it's important to discuss is that not everyone prioritizes these app attributes in the same way. So we actually, if we take a look at this chart, which shows the importance rating of the particular attribute, we see these density curves. And when we look over on the right-hand side, we see the correlation between someone's rating of importance for one attribute and another. And if we look here at accuracy, what we see is that there's a very strong negative correlation between the importance of privacy and the importance of accuracy. So we actually see that the people who highly value privacy are not the same people who highly value accuracy, and vice versa. We see a similar but much smaller correlation for benefits and privacy. So this is important to understand, that it's not that we can completely deprioritize certain benefits, but this analysis, A, lets us understand what are the most important ones in the overall population, and then B, that different people might be making different trade-offs, and that means we may need to market these apps to them differently, or even design different sets of apps that address different needs, but are interoperable so that they still help with public health. Okay, so moving on to our second research question. Privacy and data use and then accuracy were the most important considerations across the whole population. And so we wanted to understand, can we try to predict people's intent to install an app based on the level of privacy or accuracy that they're shown for this app? And the reason this is interesting is we always have a question with this kind of work, which is, are people just sort of expressing preferences, but they don't really explain much of their choice behavior? And so we want to see, how well can we predict based on these values? The second reason for doing this is that we want to talk about quantifying the amount of accuracy or privacy risk. So as an app developer, I have to make a call for when my app is ready to go out in the world, right? And I also have to make a call about how transparent to be about its level of accuracy or its level of risks. And so by understanding, how do people react to a 50% accuracy rate versus 90% accuracy rate, that can help us understand when we're ready to release apps and anticipate, what are the pitfalls we're going to run into? How well do we think these things might be adopted? Of course, this is just people's expressed intent to install because there weren't apps out that we could test with different accuracy levels, but research does show that the results of these studies do tend to correlate with real world behavior. Okay, so for this piece, we surveyed people on Amazon Mechanical Turk, and the reason that we didn't use a census representative panel was that we surveyed almost 4,000 people, so we needed a lot of respondents. We did check in a pilot study that mTurk was reasonable by comparing responses from a general population survey and from this mTurk survey, and found only one very small effect size difference. So we do find that Amazon Mechanical Turk workers are sufficiently representative, but please take the results with that in mind. Again, there were attention check questions, and we also did manual data cleaning because this was a quantitative related study, to make sure that people understood what we were asking and paid sufficient attention. And I've linked to the paper that provides more details about this study. Okay, so we wanted to model how likely people would be to install given some app with a particular sensitivity. And while I show in this chart percentage of COVID exposures detected, this is not how it was expressed to participants. So we actually gave people scenarios again. And then in the question, we told them that if they didn't use the app, 1 out of 100 times, public health workers would be able to detect and notify them that they were exposed. Whereas if they used the app, some true positive out of 100 times, the app would be able to detect and notify them that they were exposed. And every respondent saw only one value. And what we see is that as the true positive rate goes up, so as the app sensitivity goes up, people are more likely to install. And we can actually predict their likeliness of reporting that they would install based on both the true positive rate and their implicit perception of the privacy risk of the app, which I'll get back to in a bit. And we're able to predict this with 70% accuracy on a 20% test set. Which is, while it sounds low for computational things, actually quite high for human behavior. Typically, we'll see prediction rates even below 60% in good psychological models. So this actually means that people's intent to install is tracking pretty closely with their privacy perception and the level of accuracy of the app. And what we see actually is that there are particularly big jumps in the top and bottom 10% of improvements. Whereas, 50% versus 80% accuracy, we're not seeing huge differences. Okay, we can similarly take a look at false positive rates. So if someone's offered an app that will correctly notify them every time they're exposed, but it will also incorrectly notify them an additional certain false positive number of times, we asked whether they would install the app. And again, this was a separate group of people, so they hadn't seen any other question. And we see that their reported intent to install decreases when there's more than 10% false positives here. So they're pretty tolerant up to 10% if it's an app that has a perfect true positive rate. But intent to install goes down after that. And in other studies, we do see that people are more tolerant to false positives than they are to privacy risks or to false negatives. Here we have a prediction accuracy of 62.5%, so a bit lower, again using implicit privacy risk perception as well as the false positive rate to predict. So finally, getting to those privacy perceptions, we see that privacy expectations, including them in our models, improves our ability to predict. And they also independently influence people's intent to install. So we actually measured people's perception of the risk of privacy for these types of apps. And what we see is that on average, people expect that there's a 0.01 to 0.001% chance that information from a COVID app would be compromised. And this is about the chance of car theft, between car theft and petty theft in a given year. And people do have these expectations prior to us saying anything to them. And we wanted to test, how accurate our measurement was of these privacy expectations. And so we ran 2 different studies. One where we looked at intended adoption rate given some false negative rate or true positive rate. So the first thing I showed, so given some app sensitivity, how likely people were to install. And we find that the percent of people who are willing to install given some false negative rate and given some particular implicit privacy assumption is not statistically different from the intended installation rate if the privacy risk is made explicit upfront. So if we tell them that there's a 1 in 100 risk that the app will leak data, their response is the same as if they tell us they think there's a 1 in 100 risk that the app will leak data. So we do see that those implicit risks kind of line up with us telling them. And whether or not you tell them there's a privacy risk, people do have a priori assumptions. And those a priori assumptions do factor into their at least reported intent to install apps. So in summary, responsible data use is not just about privacy, although privacy is very important. It's also about providing technologies that respect user preferences, their preferences for privacy, their preferences for what kind of benefits or appropriate amount of cell use will be done when they install these apps. And so it's important when we think about these kind of applications, both now and in the future, to think about all the facets of being responsible with people's data and being responsible with their choice to install a particular application. If you're interested in additional descriptive work in this area, we have some work in Scientific American on which providers Americans are most willing to install apps from. We have more discussion of the importance of things other than privacy in an article in Wired. We have a couple of archive papers that I've linked to here. And I would like to acknowledge my wonderful collaborators both at Microsoft Research, Johns Hopkins, University of Zurich, and also the University of Michigan. Thank you.
Good morning. As a non-AI algorithm expert, but someone who uses big data for domain-specific questions, I'm very honored to speak at this Responsible AI and Machine Learning workshop with all of you really smart people here. I'm looking forward to sharing some of my thoughts on issues that I think are relevant to this very important topic. I also want to take this opportunity to learn from all of you. My topic today is machine learning in transportation, learning mobility patterns from big data. My talk today will be in 3 parts. First, I want to provide some motivation on why the study of understanding and modeling human mobilities is an important area. And I hope to inspire some of you who are hardcore machine learning experts to take on some of the unique challenges that we face in our field and form some collaborative relationships with many of my colleagues in the field. The core of my talk today is to focus on some of the data issues where I will talk about the old and the new ways of data generation process, on how that will result in various issues we experienced. I will also illustrate one example we experienced in COVID modeling, and which is a topic that William initially wanted me to speak upon, but I didn't really have much to talk about since the project has just started. So I shifted to this data-related topic on human mobilities, and I hope I do not disappoint all of you in the audience. In the last part, I want to share some of my thoughts relating to fairness in AI and machine learning, on which my only credential is really to serve as a committee member for a computer science PhD student whose dissertation topic is exactly this one. I do understand this is a very hot topic in your field. So what is human mobility pattern studies? It is essentially understanding and modeling an individual's activity and travel trajectory in time and space during a day, if we use a day as the time frame. It is illustrated here on the left side of the slide. And in this 3D space where time is a vertical axis and the other two dimensions represent the physical space, the ground truth human mobility trajectory is shown with solid black lines in this figure. We can see that from the figure, this person left home around 7 a.m., drove to a parking right lot, changed to bus, and arrived at work around 7:30. She then left work for lunch at 12 p.m. and back in office at 1:10. In the afternoon, she departed from work at 4:30 and went to a recreational place, perhaps a dinner place. From there, at 5:50, she went back to the parking lot where she parked her car and drove home. She arrived at home at 6:40. This slide of information tells us a number of three things. Actually, three things. One is her transportation choices. Second is the options that are available to her. And three are the costs. Here, I'm referring to generalized costs that include travel time, waiting time, dollar costs, and others to her. And understanding these three pieces of information for millions of people in a metropolitan region is the basis of many of our mega billion projects that determine the options that people have, as well as the cost they must bear in order to get to work, go to doctor's offices, or simply go to eat at a restaurant. I list a few mega billion projects on the right, including the most expensive nowadays, California's high-speed rail project, that is on the top right with a $77 billion price tag, New York City's Hudson Yard project with $20 billion, and my hometown, Seattle's light rail project at $55 billion. Of course, I also include something that is much smaller scale, but very useful for promoting everyone's health, and that is Seattle's Burguma Bike Trail. I'm trying to say is that if we're talking about education, healthcare are people's basic human rights, access to efficient, reliable, affordable transportation is also a basic human right. Here, affordable also includes time cost. In the past, many decades, information on how people conduct activities and travel in time and space have been collected by self-reported surveys, and most recently with GPS assists as a memory jogger. So yes, there are of course biases in self-reported surveys, but the important thing I want to note is that these are very carefully designed random probabilistic surveys with a defined target population. Today, it is an increasing trend that these surveys will be replaced by big data generated from mobile devices that you and I all have nowadays, from phone calls, mobile apps, or social media. So I illustrate first the old way and the new way of collecting such data. The differences is on the left-hand side is the old way, and the right-hand side is the new way. On the left-hand side, there is a defined target population from which one designs a probabilistic sampling process and a survey questionnaire, obtaining a set of questions whose answers are indeed for answering these specific questions. The actual survey data results from the sampling process and this survey administration process. Yes, it is a very laborious process that many of us actually naturally try to avoid, including me sometimes, but the resulting data set is often small compared to its counterpart, the big data, but the small data has very rich information that it carefully, if it is carefully designed and implemented, contains most of the information we need in answering some of the defined questions rigorously. The right-hand side is the passively solicited data generation process for virtually all big data nowadays. Of course, I here specifically refer to how the various location and the time relevant data are being generated. And it is this data that have been used for inferring human mobility patterns. First, it is some specific user groups subscribing to certain services, for example, a specific phone company or a social media service. And these services are often run by a single company. From these subscribed users, a data vendor running the services extracts data with their own unique technologies. And this results in big data. This is not a random probabilistic process. And in other words, users decide whether they are in the data set or not, nor do we know anything about who is in the target population, who are the users, and what processing techniques were used by the vendor to extract such data. So this process actually relate to result in several issues that I will talk about, illustrate with a bit more details. One is the representativeness. Second is a bias. And then there's also uncertainty. There are also time and space related issues in terms of the time lags of the data, as well as whether the data cover all geographical areas of interest. And we can also see that on my previous slide, where that I actually used GPS signals and mobile phone sightings to illustrate that where we might get, what information we might get from such data, big data. And here I show an example of users who use the service throughout the day. And you can imagine that the data resulted depends on who subscribes to what service and her usage patterns. If she only turns on the cell phone when she wants to call somebody and then turns off at other times, like my mother, she will leave very few traces. And if I infer her mobility pattern, I would have concluded that she stays at home all day long and days after another day. Well, in fact, my mother is quite active and goes out all the time. Let me illustrate some of the data issues we have observed in our own lab. And this is the air-based data for the Puget Sound metropolitan region, where we obtained data from 2018 to 2019 because we wanted to evaluate the impact of the demolition of a major highway segment in the area, followed by the construction of a new tunnel and then tolling. Here we simply calculated the number of observations per device per day in these three periods, and you can see that they are quite different from each other. From an average 85 in January 2018 to 53 in January 2019, and then 28 in November 2019. And we also observed that the majority of the users have fewer than 250 observations per day per person. Now you might wonder, why does that matter? It does matter, and this slide shows. And let's look at actually the right figure first. And you can see that the mean trip rate, which is the number of trips per person per day, steadily increases as the number of observations increases until when it reaches about 250. We know that from the previous figure that a tiny fraction of the users has about 250 observations per user. The left figure is a bit different, where the horizontal axis is a measure of how the daily observations are distributed over a day. And the maximum is 48, represent 48 half an hour segments per day. The larger the number is, the more uniformly distributed the observations are. This figure shows that there is a strong positive association between how uniformly the observations are distributed throughout a day and the number of days inferred. On this figure, again, I show that on the left, how neighborhood level attributes are associated with the fraction of the population in the neighborhood that is captured by this particular data set. On the right-hand side, I show how the neighborhood attributes are associated with the probability of trips in certain kinds of neighborhoods may be more or less captured in this particular data set. It is not difficult to imagine that if such data sets are directly used as a basis for making decisions on our mega billion transportation projects, that can be dire consequences that will take decades to correct if they are ever to be corrected. Now, I just want to show on this slide, I want to show very preliminary results. We identify with our COVID modeling, and this is very preliminary. And by the way, this slide goes to the credit of this slide goes to my collaborator, Dr. Vijay Gupta, and reinforcement learning expert at the University of Notre Dame, my own PhD student, Grace Jha, and Vijay's former student, Ben Bernhard, who is now a PhD student at Caltech. You can see that when there's no error in the case numbers, convergence is reached after about 15,000 training steps. And the number of the infected is below the hospital capacity, with errors that the number of the infected exceed the hospital capacity after 50,000 steps. And the amount of error we inserted in the case number is only about 5% of the true case data. So here, I want to summarize that in my own domain, which is using big data for inferring human mobility patterns, my understanding of various issues in the data, I feel that it's really imperative because there are high stakes. I summarize 5 kinds of issues, and they are representativeness, which refers to, does the data represent the population of interest? Bias, are there systematic factors that could cause the data to be overestimates or underestimates of the actual value? Uncertainty, time, and the space that I mentioned earlier. So I do believe that these 5 categories of issues are probably applicable to many other kinds of data that are beyond the human mobility domain. And within my own domain, that I have a question mark on the uncertainty. I have a check on the uncertainty, while I have question marks on all the other 4. And I feel that uncertainty is probably the least concerned issue in this case because of the large sample size. And I'm also trying to clarify that I'm not saying that these issues are equally important for all data sets or for all problems. In fact, it is important to recognize that for some problems, they are not important. So we should not get carried away. The point is really to recognize these issues when they are critical. So to close my talk in 2 slides, I just want to make some comment on fairness in machine learning. I realize this is actually very dangerous for me to do so in front of a group of hardcore machine learning experts. So please forgive me if my comments are misleading or represent my own misunderstanding. So my own understanding about the solutions to this issue in the field are primarily of 3 kinds: pre-processing, in-processing, and post-processing. I also posted a table of protected variables that I found many machine learning researchers use as a guide to making data or algorithms independent of these protected variables or removing their influences in the predictions. Now, based on this understanding, I'm now moving to my danger zone of offering some of my suggestions for the community. I want to offer 4 suggestions. First, data problems are, of course, very important, as identified in the AI machine learning community already, as well as in my own work with respect to human mobility patterns. But because of the diversity of the data sets that exist, we need multiple or many coordinated community efforts that are, each of them is domain or problem specific, but we must involve domain experts. Second, instead of trying to remove the so-called biases of those protected variables, why not study them? This is because many of them embody very rich social meanings. As an example, marital status indicates a very different life stage from singles, and thus have very different social and family responsibilities. The same applies to age and gender. These variables are routinely entered and studied in many fields, including my own field, transportation planning and engineering, because they enrich meanings, provide guidance for us on how to interpret the results and how to form transportation policies. And third, most, if not all of the work so far I have read in this field seems to focus on inequality or disparity. But I want to ask, is this what really matters in real life or even realistic? And perhaps it is time to reflect and ask these questions to ourselves. And last, while I understand fairness have precise and strict meanings, mathematical definitions in this field, I also tend to think that it probably varies quite a bit between different domains and problems. It is also probably not black and white, as crisp as a mathematical definition. Perhaps it is time to accept that, and let's work closely with domain experts in different domains and then try to synthesize to identify commonalities and differences. So this concludes my presentation, and thank you very much. I look forward to sharing.
Good morning. Here is Luca Ferretti from the University of Oxford. It is a pleasure to discuss with you some aspects related to a new technology that is app-based contact tracing, not so much in terms of the technology itself, but in terms of the reasons behind this technology from an epidemiological standpoint, and what are the current perspectives for this technology in this COVID pandemic. First, let me remind you why digital solutions are important. There are several traditional tools that epidemiology can use to stop COVID-19. One is, for example, physical distancing, masks, lockdown, and so on. These tools are either insufficient on their own, typically, or they have very high social and economical costs, as we know. The other one is mass testing and contact tracing. The combination of these two is always beneficial, but it has some issues with scaling up, both in terms of human resources and in terms of lab capacity and logistics. There is, of course, vaccination, but vaccination takes time. As we all know, vaccines have to be developed, have to go to a series of clinical trials, and then there needs to be some time to scale up production. So alternative digital technologies are needed for a fast, scalable response right now. One of the most clear cases where digital technologies can help is in contact tracing. Not only enhancing traditional contact tracing through more effective data management and data communication, but also directly by speeding up contact tracing. Why is this important? Well, the key reason is that half of the COVID-19 transmission occur before symptoms, and another fraction comes from individuals that are fully asymptomatic. So it's key to trace and quarantine their contacts, because by the time you stop the virus in symptomatic individuals, the virus has just gone forward to the next generation of transmissions. And there is a small time window to prevent the transmissions from contacts. The time window is broadly a few days. Typically, there should be not more than 2 days between when people get the symptoms and when you quarantine all their contacts. And of course, to be able to control the virus, there are some requirements in terms of efficiency. So most contacts should be traced and quarantined. So why is it so important that the speed of contact tracing? Well, imagine you have a symptomatic case. When you get the symptomatic case and you have tested him or her, you are already at the point where most of the transmissions have occurred. So you go and you trace the contacts. But if you spend some time finding and tracing the contacts will have already transmitted the virus forward. If you stop them almost immediately, they will have transmitted only to very few other individuals. And this is key to stop the virus. We proposed as a solution for this issue of speed and efficiency, digital contact tracing, where digital really means these two keywords. Now, it is key that these two keywords are realized, so the actual process should be rapid and should be efficient. And one practical way to think about this is to think about app-based contact tracing. App-based contact tracing is a very simple idea. Basically, you look at the contacts between individuals, where contact means spending some time at a short distance, 1-2 meters. You record these contacts via Bluetooth, low energy technologies, to the actual distance measurements and exchange of keys between the mobile phones of the two individuals. And this goes on as long as a single individual stays at home or goes to public transport, goes to work with some close co-workers, and then goes back home or with friends and so on. The day such an individual awakes with fever or other symptoms, he can simply report the symptoms and request a test, and if positive, instantaneously a signal can be sent to all his contacts, telling them to self-isolate for 14 days or to quarantine themselves, or eventually even giving advice on enhanced social distancing for possibly lower risk contacts. So this is a very simple idea that we have proposed back in March, and that has been picked up massively. There are some clear ethical issues behind this approach. It's quite clear that contact networks are very, very high sensitive piece of personal information. Maybe more than where we have been. So who we are in touch is perceived as a very personal information. And so this kind of technology needs to build trust and confidence at every stage so that people are confident that their data will be used only for this epidemic. It needs to have privacy and data users concerned, therefore, at the forefront. And the algorithm needs to be auditable and transparent in order to avoid any issue with public trust. And of course, a key is individual consent. While some countries have gone for mandatory apps, we believe that mandatory would probably be counterproductive, and approaches such as opt-out or purely voluntary adoption are the most efficient ones. There are also some epidemiological requirements for these apps to work. One is that they have to have a high user uptake and adherence to the notifications. Notification should be fast, because otherwise the whole process is useless. And notification should try to have a high sensitivity and specificity in terms of choosing which individuals to quarantine. There should be an integration with local health policies, because of course this is just a piece into the global integrated response to the virus. And most importantly, it should be possible to evaluate the effectiveness of these apps and possibly improve their effectiveness transparently and in real time. It should be emphasized that these apps are equivalent to public health interventions, and therefore their success is not measured in purely uptake or so on, but is measured in how effective they are in stopping the virus. There are three critical points. One is the high uptake. These apps require quite large uptake to work well. If one would have a massive uptake, so most individuals in a population would have it, say more than half of the individuals, one would reach a situation where you could have a real digital herd immunity, where essentially contact tracing by digital contact tracing would stop the virus. But as you can see, we are far from this threshold in most countries. You see Italy, for example, around 11%. England Airways, where I've always worked, is around 30%. And only a few countries have done better and still not at the levels required. So what you have is a scenario where only a few people in each community have the app. But what you can still have is a high local uptake where essentially app usage is clustered in some communities. This causes a very strong risk reduction in the community that is using the app. And as we have proposed, it's probably key for the adoption of these apps to involve local communities, to spread the apps in local communities, and where you get both the benefit, the immediate benefit, and the high uptake. And these apps can probably meet their value. And then scaling up these. This is a classical thing that has been done with many other technologies that are based on network effects. Another important technical issue is the fact that you should be able to test people very rapidly and efficiently, and of course have a rapid and effective case management at the time of passing the results of the tests and so on. This has been emphasized already by several people, most notoriously Bill Gates, who have stated that waiting for more than 2 days for a test result is insane, and he is right, because these are the times that we agree on. 2 days should be the time where all test results, or most of them, should get back, enable to do effective contact tracing. And then a very difficult point, but an important one, there should be some support from the government or the community for people who choose to do enhanced distancing or to quarantine or to self-isolate. Because without effective quarantine or self-isolation, it's not possible to stop the virus, because it is staying at home that stops the virus, not the fact of receiving the notification. It's also very important to evaluate these technologies. And one very, very interesting test is the one that has been done on the Isle of Wight in England. You see, the Isle of Wight is here south of the England coast. And it's a relatively small community, and it has been a key for the first pilot of traditional plus digital contact tracing, I think, in the world. And that pilot has had very positive results. Here you can see our statistical analysis. Here you see the famigerate R coefficient that says if the epidemic is under control or not. And the red line is the Isle of Wight, and this dashed line is a synthetic control produced from the rest of England. And you can see that they trace each other until the beginning of the test and trace program, and then there is a clear reduction thanks to the test and trace program. And this is the same, the relative reduction of the Isle of Wight. So we are talking about very effective interventions that can be combined with traditional contact tracing. And I think these interventions will have a promising future. We have now hundreds of millions of people who have downloaded these apps. And my feeling is that there is the potential for significant improvements in this direction. Thanks a lot, and I'm glad to take questions. Thanks.
Hi, everybody. My name is Jeffrey Kahn. As you can see here, I'm the director of the Johns Hopkins Berman Institute of Bioethics. My pleasure to be here with you today to talk about the ethics and governance issues related to digital contact tracing for pandemic response, COVID-19 in particular. So quickly, contact tracing involves a core tool of public health, which is used to identify individuals who are infected as a case. Then close contacts of that case are further identified and tracked down, gotten in touch with, and those people are asked to take protective measures as well as who they might have exposed, and those people then track down. So think of it as following up on a web of those exposed. It's very typical in public health efforts, in particular with sexually transmitted infections, sometimes foodborne outbreaks as well. It's a little challenging in the context of a respiratory infection like SARS-CoV-2, that is the virus that causes COVID-19, because it's a respiratory infection and people are spreading it before they know that they're sick. So using contact tracing is a helpful way to break the chain of transmission, manage epidemics at a low acceptable, manageable, not so much acceptable level, prevent surge of future cases, and hopefully in the process enable reopening of all the things that we've been, unable to reopen successfully so far. The challenge with the human approach, which is the one that's been around for a very long time, is that we currently don't have enough people to do it. The conservative estimate at this point is we need 300,000 people, literally a small army, costing many billions of dollars to do it. So just to put a point on this is not a very recent graphic, but you get the picture. The numbers of people needed, state by state. You can see that only one state on this map says that they currently had the needed number of contact tracers per 100,000 population to do that job. So a big problem. So one reaction to this problem was to say, well, let's think about technology. There are solutions that we might bring to bear across the world. And then once the countries of Europe and some of the Asian countries started to use technology, thinking about how this might work in the US, using technology, whether it be an app on a smartphone or just accessing people's location, using mobile phone tracking, where they may have used a credit card, where they may have accessed a national health system, for instance, just following people as a way of effectively doing contact tracing using digital technology. So maybe there's a way, right, to blunt the need for all these people and get us some of the same kinds of successful public health outcomes as human-powered contact tracing, or at least complement human-powered contact tracing. So how would it work here? Many of you, I'm sure, know that Apple and Google have announced a collaboration by which there is a shared approach to accessing the API. It would allow what is called exposure notification only. That is a very privacy-preserving approach by which Bluetooth on phones shake hands with other phones in proximity to it. And then when a positive COVID-19 test is reported, a ping is sent out to all the phones that have been within a specified proximity of a phone that was known to have be a person who was infected for a specific duration of time. So 6 feet, 15 minutes duration. All the other phones within a certain number of days of infectivity are pinged, and then those individuals whose phones were pinged would then have to follow up, go get a COVID test, or call your local public health department and they'll tell you how to go get a COVID test, and so on. The benefit of this approach is that there's no sharing of the information with public health authorities, so it's very privacy preserving. But the downside of that is it relies on individual action and follow-up for anything to happen. We don't get much public health follow-up unless the individual decides to do something if their phone is pinged. There are other ways, however, which would be using opt-in or opt-out models for sharing of data, such as whether individuals were exposed, and that could be reported directly to public health. Somewhat less privacy preserving would be the location of where people were exposed, and so then individuals could be more easily traced. The problem is that's not the approach that Apple Google has set up, and so we don't really know what individuals would accept, what populations would accept. So we don't know how broad or limited the sharing of data might be acceptable, sort of what data storage processes were acceptable, where that data should be stored, for how long, et cetera. So it's all been predetermined in some sense by the Apple-Google agreement. So the reaction to the introduction of technology for these purposes has had many reactions, most of which have focused on privacy. Like, how are we going to do this in a way that doesn't threaten individual privacy? Of course, this all seems to forget the fact that anytime you open up the map app on your Smartphone, you're being tracked. That information is being collected and stored, certainly not in a privacy-preserving way. So it's a little funny, I would say, unclear about why the dominant focus has been on privacy for this very compelling public health purpose when we don't seem to pay much attention to it for other seemingly less important purposes. But nonetheless, that's been the reaction and focus. So pretty clear that there's a lot of complicated stuff going on in the way this technology could be set up and the way it could be brought to bear in response to the public health crisis that we're all facing. And there has been no comprehensive guidance about how to think about the issues. So this graphic is meant to represent, in a very crude way, the interplay between all of the things that are going on and others too, but the sort of main things that are going on. So, there's technological capabilities which interact with how well the technology might perform, which are affected by the public adoption and acceptance and therefore use of the technology. So how widespread the use is within a population, what the law has to say about particular use and by whom. The public health needs, of course, should be overarching and most important. And of course, we want to all get back to a healthy, functioning society, which is why that gear in the center is the largest. So given that there was this gap in lack of guidance, I led a large project here at Johns Hopkins to try to first analyze and assess the ethics and governance issues and then make some recommendations about how we might go forward in effective, informed, and responsible ways for the US in particular. Here's the project timeline. For those of you in academia, you'll be kind of both, I think, impressed and maybe aghast at how fast we did this. Testament to what we were facing, as a country and a society, and the ability that we have to bring to bear many smart people, many talented people, working very hard over a very short period of time to try to provide some thought leadership around this issue. So I took a call from our university president, Ron Daniels, on the 18th of April, very late that evening. He called me and said, I think there's an opportunity here and a need for the kind of work that you all do at the Berman Institute to lead a national, if not international, project to try to provide some direction and thought leadership around the ethics and governance issues of this thing being termed digital contact tracing technology. So I said, that's great. I think you're right. I got together a group very rapidly the next day. And as you see here, we wended our way, though it was more like a kind of linear sprint than it was this kind of twists and turns of steps. But we consulted with experts first within our university, and then with a lot of contributors from across the US and across the globe. We drafted a report very quickly. As you can see, with a running start on April the 19th, we had our first draft on May the 5th. We shared that. The consensus group that was formed, as it says there, the 26th of August, helped to craft that first draft and then gave us feedback on a second draft. Anyway, long story short, we got to a finalized product report and its recommendations on the 19th of May, literally 1 month after we started. The Google Doc version of that document was handed over to colleagues at the Johns Hopkins University Press, who turned it into a physical book literally within 1 week. So we went from the idea on April the 18th to a physical book available for purchase in a hard copy form or free to download on the 26th of May. Unprecedented in the speed in which we did this, with a lot of really good content as a result. So here's the piece that we focused on. As you see here in the animation, we focus on the ethical values and principles as our focus for this work. And let me tell you the sort of high level takeaways, and then I'll show you where you can get more information about this report and its content. So a few high level takeaway principles. First, transparency and public engagement are essential to anything like an inclusive digital public health response. So be really clear about what you're doing, why you're doing it, engage the public in what is acceptable. This is just good public health policy from an ethics perspective anyway, brought forward into this domain. Second, the approach the technology takes and uses must represent the least infringing in terms of civil liberties necessary to accomplish the public health goal. So don't infringe privacy more than you have to achieve the public health goal. I would say the Apple-Google approach doesn't go far enough, frankly. It's too respectful of civil liberty and doesn't accomplish the public health goal, but that's a sort of different, that's a more in the weeds kind of argument, but clearly it's relevant to the way we think about what technology is used and how. Third, the use of the technology must be guided by best available evidence. So here we're in a situation where we don't know what will work best. How will performance be affected, by levels of adoption, which in turn, is partly affected by how high the positivity rates are in a community. Will more or less privacy affect the willingness of people to use these apps? And that, of course, will affect performance. So we need to learn as we go. And this isn't even beta testing. This is, whatever, presumably that's called alpha testing, when you're introducing something very, very early on. But we're doing that in kind of real time during a pandemic. So we got to learn as we go. Responsible use of these technologies for public health require meaningful governance and accountability. So how to do this, what are the rules of the road, and who is accountable for making sure that happens? That brings in governments and policymakers, quite obviously. And then lastly, any deployment of these technologies must be rooted in a commitment to equity. Some communities have greater and lesser access to smartphone technology. And so if a community doesn't have a lot of penetration of smartphones, then they should get more human-powered contact tracing. Of course, all of this in the context of a highly mistrustful populace at the moment. And so there may be a lot of concern about how these technologies are being used and an unwillingness to accept them, rather than a suggestion that equity is about denial of equitable access to benefits. It may be the other way around. People don't want these technologies being used in their communities. So that's a big part of what's going on at the moment. All right, so we worked hard to write this report, which identified public health needs and technological capabilities. This is just a table of contents pulled out so you can see the various chapters and the contents of those chapters. And you see all the way through from public health, how does it work? What is digital contact tracing and the technologies brought to bear? What are the ethics of designing and using these technologies? And what are the legal considerations? We actually had a lot of pro bono help from Arnold & Porter, a law firm in Washington, D.C., help us with this, along with some legal experts who were part of both the Berman Institute community and colleagues from across law schools in the U.S. and internationally. So we had a lot of legal expertise on this. Recommendations in this report were focused in these three big areas: public health, ethics, and legislation. That's policy law. The recommendations are captured here. I'll be really quick because I'm running out of time. We think it's wrong for technology companies to control or set these terms by themselves. That should not be the way this world is set up. They shouldn't presume to know what's acceptable to the public, and we certainly need input of public health as well as the public to figure out what the right way to set these are. So I think we've already sort of got off on the wrong foot with Apple and Google telling us the way this will happen. No one size fits all. We think that different communities will answer this question in different ways. Start with a middle ground approach and then modify based on performance, adoption, and local needs. Governments shouldn't mandate this, but they should be voluntary. Certainly in this environment, that seems the most sensible way to start. And Congress needs to enact legislation so that we don't have a crazy patchwork. But we know what the rules are that aren't relevant, or relative to state borders, but rather are national. All right, here's the team. Not important, except that's me in the middle, and really amazing, hardworking colleagues of mine who put in incredible hours over a very short period of time. We had people from across the tech sector, my colleagues in academia, as well as international folks from US, Switzerland, Israel, and law, public health, ethics, policy. That's where you can get the book. It's free online at that link, Project Muse. It's also free, available as a Kindle download or wherever you get your e-books. Thank you. And with that, I'll stop and look forward to the Q&A discussion.
All right. Thank you, Jeff. And thank you all for participating in this session. I'm the session chair, and I'll be coordinating the question answer session. So, so first set of questions, I think like Alyssa already answered some of the questions. Maybe I can ask some questions in addition to the ones that we already have. But Alyssa, if you want to take a few minutes and maybe like summarize the answers that you gave for the questions that were already there.
Yep, absolutely. So folks had asked a couple of questions about sort of what drives different people's prioritization of some of these attributes, like let's say accuracy versus privacy. We discussed this a little bit in the paper that's on arXiv, and we have some other results that aren't up there. But one of the things that we see is some correlation both with political leaning and with people's sort of COVID experiences. So we do observe that in the US, Republicans tend to prioritize privacy of these apps more, while Democrats prioritize accuracy. And that relates to kind of some existing known findings around sort of political leaning and privacy preferences. And then we also see that people who are essential workers or who know someone who died because of COVID tend to put less priority on accuracy. And finally, those who have better knowledge about COVID, so they better understand how infection spreads or et cetera, people who have better knowledge about COVID prioritize accuracy, whereas those who have less knowledge about COVID tend to prioritize benefits, where benefits are like, oh, the app will tell me that I've been exposed or it helps me join the fight, versus kind of those true positive, false positive things we spoke about. That's, I think, kind of a good summary of what we were discussing in the chat.
Cool, thank you. I have a couple of more questions for you. I think one thing that was not clear to me was about how are we quantifying privacy in this survey, right? Because privacy can mean a lot of things. Is it about the data that is going to get collected, or is it like also have some transparency about how the data is going to get used? Because a lot of people I know, including myself, using these apps, my concern will be about who's going to use this data. Is it going to be sold in through third-party services, or like will be used by other government agencies, which I don't want access to my data? So were these part of the surveys, and any thoughts on that?
Yeah, absolutely. It's a great question. So in the kind of quantitative survey that I talked about at the end, we were specifically talking about privacy in the sense of my data will be used for purposes that are not contact tracing, and sort of how likely people thought that was to happen. And you make sort of a great point, which is, people are often like, well, how do we know that people's perceptions of the likelihood of that happening are accurate? And of course we don't, but we also don't really have any measurement yet of how likely that is to happen either. So that's kind of why we went with that. In terms of your broader question, in the conjoint analyses, we actually explored showing people different privacy risks, where some of it was about, data retention versus an attacker getting a hold of it versus different entities that they might care about getting access to their data. And we see that one of the big concerns that comes up is exactly kind of what you describe, which is sort of authoritarianism. Is this going to start an era of government surveillance? And that's a little bit different than people's concerns in maybe other apps, where it's more about the tech company or sort of people making money off of data or et cetera. We see a lot more of that surveillance kind of capitalism concern coming out here. And so I think for app providers, that's something to think about when you're marketing your apps. Is sort of one thing that we're testing now in field studies is, should they even mention what data is collected or how they're protecting people, or is it better not to say anything at all? And sort of, is it ethical not to put that in an ad? So those are all kind of great questions we're still working on.
One more question before I move to the other speaker is about, so Luca made this point about the speed of contact tracing. So in terms of benefits in the survey, were you covering that point as well?
Yeah, so that's a good question. In the surveys that I presented, we were not talking about speed. We were more talking about coverage. That's something we've been thinking about exploring in some new surveys, because that does seem to be like a strong driver we see in a lot of our work, is people really want information more so than anything else. So actually, even more so than contact tracing apps, they would love apps that give them sort of personalized updates about the state of COVID where they are. And so I think that's actually a really great point, that speed might be an incentive that we hadn't considered in June when we were running these studies.
All right, thank you. So let me move to the next speaker, Cynthia. Thanks for the great talk. And I have a couple of questions for you. This is very basic, but we talked about the mobility modeling. And there has been a lot of work in the mobility modeling in general, and we have understanding of those mobility patterns at coarse level, fine grained level. But is this something that can be combined with the existing digital contact tracing techniques to improve the accuracy of the results, or reduce the false positives that we have in the digital contact tracing? Do you think that is something which is a viable combination? If not, then what are the challenges?
Thank you. That's a very good question. I haven't given too much thought about that. And so, but yes, I do think that is where the direction should be going. But not only that, part of the work that we have also been doing is to provide personalized recommendations. And so, not only to do the contact tracing for COVID-19 pandemic, but also there are also opportunities to do more personalized and tailored recommendations that is depending on time, what people do at the location for preventive health as well.
I see. So I think in general, we've been talking about app-based digital contact tracing, but there are so many other sources of data, as we can say, for example, cellular data, which is relatively coarse grained, not as fine grained. Has this data been used in some type of policy making, if not contact tracing, but policy decision making about which type of counties should be open, which type of counties should probably remain closed? Any insight on how this type of relatively coarse grained data can be used to drive the policy decisions?
So yes, I feel there are a lot of potential on that line, and we are working toward that. I see two ways, and one is that in almost all the the spread of disease modeling, traffic is an important factor, right? And so that's one. And the other thing, I think there's a lot of gap in the current area, is that we actually don't understand very well about the various kinds of contact patterns that people have, depending on the kind of land use and the kind of activity patterns. And so this is also, I think there's a lot of need for that area. And I also think that it's a contact pattern that ultimately, fundamentally underlines the spread of the disease at a location as well as between locations.
I see. Cool. All right. Thank you. Let me move to the next speaker, Jeff. So I have one very high-level question for you, which is that what type of we talked about the regulatory oversights. So what type of regulatory oversights exist right now in terms of data usage? Especially, I'm asking from the Google and Google and Apple perspective, that they were collecting data at scale, but are there any clear regulatory oversights of how that data should be used and not used?
Thanks for the question. I think it's really important, and unfortunately, the short answer is no. But it's no because, as I'm sure many of you who are watching already know, this is a somewhat unique application, right? So it's technology being brought in from our smartphones into public health use. So that's novel in some sense. And so, it invokes everything from HIPAA to public health emergency powers. The other thing to say is it depends on who's the user, right? Who's using the data. And governments, which is where our focus has been, there'll be a different answer about what they can do or not versus employers, say, or institutions like universities where I work, all of whom will have different rules apply, different laws apply. And so it's a really confusing environment, I think, is the short answer to the question. One I was pretty critical, as I listened to myself talk, pretty critical of the Apple-Google approach. In some sense, not their fault. There's been a vacuum at the top, and the approach that they have taken is so privacy preserving that it doesn't run afoul really of any of the kinds of concerns that I've only really briefly laid out. The book, and I, for those of you who are asking, I posted a link to the website where you can get it in the chat, so have a look there. But we actually did a fair amount of evaluating the various law, policy, rules that exist in the various categories. So it's quite a lot of detail. What should happen, one last thing I'll say, is there should be congressional action that will clarify the answer to the question, because nature abhors a vacuum or whatever. Uncertainty is terrible, and that's what we're facing. So just add it to the list of things where there isn't clarity in the context of how to behave during the pandemic and our response to it. So I think a lot of really important work to be done. And frankly, we've been, I don't know, screaming is quite right, talking to as many people as will listen to us about the need to get some things done. But, like a lot of other areas, there just has been very little action and traction.
Okay, cool, thank you. So I have one related question, something that you mentioned about this process, that when we started, we had little knowledge about how things are going to pan out. There were so many moving parts and variables. But given that all the knowledge that we have right now, do you think that we have, a good sense of if there is a next pandemic or something of the same scale? Are we prepared? Are all the different gears that we have, all the balls on the bearing right now, or we still at the same stage as we were in March or February earlier this year?
I think we're much better than we were back in March. And there was a lot of activity in the chat when Alyssa was speaking, and I ended up texting her privately because a lot of her work is really interesting to the work that we're doing. So great, thank you for inviting us. There's a lot of opportunity here for collaboration and to put us in a better position next time. We haven't talked much, and I don't know whether you want to, about what's happening at the state level. So there's now, something like 26 of the states in the US have either implemented or announced that they will be implementing the Apple-Google exposure notification platform. And so, there is still time, and unfortunately there is still a pandemic. So we'll actually learn more, I think, in the coming months that may help us with this pandemic, and certainly will put us in a better position for the next one.
Okay. And I think something that we briefly covered was about the audit and the algorithmic transparency for usage of data. So some there has been in the academia, there has been some work about how we can enable privacy preserving analytics at scale, privacy preserving machine learning. But have those ideas been applied in practice right now, or we are far from applying those works, and there is still a lot more work to be done to make all those theoretical works a bit more practical in this setting?
Yeah, I think the latter. Although I would maybe ask you, frankly, and your colleagues, is less the world that I know. I did, in your question in the chat, I was thinking about how to answer. And one thing I would ask to Alyssa, maybe we'll have a conversation among the panelists, is people have been very focused on privacy and the use of their data in this context. But goodness, every time you open your phone and use Google Maps or Apple Maps, or depending on the app you use, your geolocation is being collected, and that data is being stored. And unless you go through the 8 steps it takes to erase that, it's in the cloud for a really long time. And the next time you show up in Baltimore, it will tell you that restaurant you ate in 3 years ago is across the street, right? So it's a little baffling to me that in the context of a public health pandemic and a real emergency, and our wishing we could leave our homes, that we're overly concerned about sharing data in this context, but we're not in all these other contexts when we use our phones for much less important things, I would say. So there's, I think, a really interesting question about transparency in this context and not in others. I don't get it, but I'm not on the, I'm not an app developer, I'm not on the tech side. So maybe that you're going to tell me, it's our world, and that's the way it is. But I think that hasn't been super well communicated to the public, I think, is part of it. And, last thing I'll say is, if you've been watching the presidential debates, I'm making a political comment here, but a lot of the argument has been about transparency or lack thereof, right? So it has to be, all this conversation has to be situated into the larger political context in which we're living. So anyway, maybe I'll stop there.
Fair enough. I think before Alyssa, you answer, I would add a bit more pieces here. That the study that you did had clear takeaways for app developers who were developing apps for contact tracing or COVID-related apps, right? But are there any takeaways for the general app development, right? About sensitivity to privacy and benefits that they're getting from the app, and is this something that can drive future app development in general, or they are very different lessons given the gravity of the situation we are in? Those takeaways are very different from the normal apps that we use.
Yeah, so I think this is a great point, right? Which is we are seeing more transparency in some ways than we usually do. And I think I come from a more traditional security and privacy background. I saw sort of a surprising amount of engagement, right, from my colleagues in this conversation. And I think this was sort of one of the few cases where we talked about privacy and security at the beginning of app development, right? Usually technology companies kind of make whatever, and it has some clear benefit, and then people go and adopt it, and then later people get fussed about privacy. And this was sort of an unusual case where it got proposed ahead of time, and so people sort of got to fuss in advance. And in some ways that's a good thing, but in some ways it has also led to a lot of sort of noise in the press and et cetera for users that may have created sort of the impression that there's, maybe more concerns here than there are otherwise. And obviously we do have sort of health information, although a lot of the conversation has been about location information and so forth, which obviously is in a lot of apps. And so I think you kind of do raise an interesting point now of, what do we need to actually achieve public health goals, which sometimes the restrictions like not collecting as much data as public health agencies would like through like the GAN framework can be problematic, as well as sort of what's the cost benefit analysis, right, for users. And I think that's where, hopefully as we move forward, we will have more measurement on the sensitivity of these apps, how effective they are in, starting to reduce death rates, et cetera, so that people can make those trade-offs. And I think that's something we struggle with kind of generally in the privacy and security space, right, is that we kind of raise a lot of concerns, but we can't always say, here's how big that concern is versus the benefit you get from, say, using this product or et cetera. So I think it's a hard place to achieve a balance. Yeah.
Fair enough. I think I have a comment here from Zara, and she says that the medical information is very different from what you ate in restaurant, and that's why people are really concerned and sensitive about the privacy. But I think maybe it's this pandemic and the need to have sharing of this medical information or location information, which is kind of starting this debate about privacy, because by design, most of these applications are transparent, and the privacy issues are under the hood for most of the time. But because now this is something in the public discourse, so maybe there are lessons for us to maybe both the from regulatory perspective and from research perspective, we get more teeth in terms of figuring out what should be the question that we should be asking for any type of app, and what type of privacy questions we should be discussing, and what type of discourse we should be having on privacy here. Because if we are sensitive about privacy for the contact tracing apps, we should also be sensitive about the apps which are tracking our locations and making recommendations about these restaurants. Should they be judged differently? Or if not, if we come up with some mechanisms of how we can enable more transparency for the algorithms that are in use by these applications, I think they can be broadly applied to applications that are not necessarily related to COVID.
Maybe I'll start, and Alyssa can join if she wants. The truth is, if infectious diseases are reportable to public health, full stop. It doesn't matter whether that information is gleaned from an app on your phone or the fact that you went and got a COVID test. So when that happens and it's positive, it is reported. And that's by law, and that's longstanding public health. It's a good thing, right? When there's, infectious disease in a community, we have all sorts of tools to address that. And so I guess one thing I would say to push back a little bit, yeah, of course, medical information about people is different, but we're talking about very specific kind of medical information. And unless you want to kind of reopen the argument about whether infectious disease information should be reported to public health, to me, this is just about how technology can be used to do the thing we've already been doing. And that's why, I mean, again, it's proving the point, I think. Somehow this has gotten people's attention. I love Alyssa's point about privacy was at the front end of the discussion here, rather than this app has some benefit and you want access to it. And in order to get that benefit, you have to give up some of your privacy or have your data be collected and used by somebody. Here we're saying, we need your private information in order to help all of us. Now that's what's interesting too. It's not about whether I get some benefit from an app on my phone. It's to serve the public health good, which is a collective benefit. And we have a much harder time getting our heads around, the value of that. So anyway, I'm lecturing about public health and ethics here, which is what I do for a living. So I apologize, but I think that's a really interesting point, and we haven't somehow communicated that. And again, it's not Apple and Google's job to communicate that, but that's sort of how it all unfolded, a little bit backward.
All right, so I guess we're towards the end of this session. Any closing thoughts before we move to the next panel?
Can I maybe add one comment, just follow up on that?
Sure.
So Jeff, I completely agree with you. I also just want to mention that one line of work in my lab actually looking at how people share different kinds of information and different kinds of resources with different kinds of people in response to a mega earthquake that is imminent for the Pacific Northwest region. And so this might be something that all the technologists might find useful, is that what we find is that people's level of willingness to share varies when you're talking about what kind of information or resources to share. And it also varies with different kinds of social ties, whether they are relatives, neighbors, friends or the acquaintances or people living, and there's also a place attachment too. And also, it also varies under different kinds of situation. And so people will be willing to share their medical information, for example, in an earthquake context. And I would think a similar context would be COVID-19, right? And so I definitely see one of my collaborators is a blockchain expert. And so we definitely see many opportunities for technologists to move in to address these kind of issues, but we need to kind of design the technologies by being aware of these different social contexts that people are in.
All right, thank you, Cynthia. Thank you all the speakers for your time and sharing all these insights with us. We'll move to the next panel. I'll pass the baton to Joe, and he'll lead the panel. Thank you.
Thank you very much. It's been a really fascinating symposium so far this morning, and it's my privilege to host the next section. I'm Joe Walther. I work at UCSB as the director of the Center for Information Technology and Society, a vastly multidisciplinary center of which William Wang and many others who have joined us today are affiliated members. But I'd like to introduce the panelists for this particular session and get underway with them. And this will also be kind of a check-in to make sure everybody is with us today. We have joining us today Lynn Fitzgibbons, who is the chair of the Division of Infectious Disease at Cottage Health here in Santa Barbara. And I see Lynn is there. Good to see you, Lynn. Also joining us today, Oliver Morgan, Director of Health Emergency Information and Risk Assessment at the World Health Organization. Oliver, are you here? Fantastic, great to see you, and I'm glad you're here. Andrew Mutz is with us today, or should be with us. Andrew is the Chief Technology Officer of Property Management at Appfolio. Appfolio is a software company create systems for landlord and property management companies who will have a different perspective on things. Thanks for joining us today, Andrew. It's great to see you. Sarah Hooker, I see, is lit up and looks to be to my left. Thanks for joining us, Sarah. Sarah is a research scholar at Google Brain Artificial Intelligence, where she has done studies on interpretability in deep learning and trustworthy AI, and we're looking forward to your observations today as well. And finally, the last member of our panel is Heng Ji, who I see lit up and smiling with us. Thank you for joining us. Heng Ji is an Amazon scholar and professor in computer science at University of Illinois, Urbana-Champaign, who focuses on natural language processing and its connections with data mining, social science, and vision. Well, I've had an opportunity to mention each of your titles and affiliations, but we've kind of prepared the panelists today with a number of questions. I'd like to do these questions in a round robin sort of fashion. And the first question asked, titles aside, could each of you tell us briefly, what do you do? And how does your work involve data and the potential application, if possible, of AI and machine learning? And let's just keep going in order and start again by asking Lynn, could you introduce yourself aside from title? What do you do?
Thanks, Joe. Pleasure to be here. So my name is Lynn Fitzgibbons. I'm an infectious disease doctor. I spend most of my professional days actually working with residents and medical students. I have a couple of faculty affiliations, and so I do a lot of clinical teaching. But after the last couple of hours, I actually realized that my introduction should have been, I am, compared to the rest of you, a visitor from another time, because I am probably one of the only clinicians on this panel or on this entire symposium. And so much of the conversation thus far has really, I think, exemplified just how archaic some of our clinical and public health methods thus far have been. And so I do a lot of clinical infectious diseases, a lot of academic infectious diseases, and work closely with public health department here in Santa Barbara, California. I'm also, I think, really, really pleased to say that I collaborate with a few of our sponsors and our leaders for this symposium, very peripherally related to some clinical suggestions in the realm of COVID-19. So that's, I think, what I do, a visitor from another time.
That's great. Thank you, Lynn. So your data comes from articles, streams of analyses, as well as watching patients. That's an amazing perspective, and we're glad you're with us today.
Thanks.
Oliver, what do you do?
Great. Well, it's great to be with you all today. So I'm based in Geneva at the headquarters of the World Health Organization, and I run a department that actually is located not just in Geneva, but in 6 other locations around the world. And we run a 24/7 operation that does a number of different functions on behalf of WHO. Primarily, we're in the business of detecting new public health events around the world. Predominantly infectious diseases, but they could be chemical exposures, radiological exposures, or any other type of health threat. And then once identified potential health threats, we also conduct risk assessments on those threats and then make recommendations accordingly for response or whatever we think is appropriate at the time. And then we additionally conduct investigations, field investigations to investigate outbreaks, epidemiologic type investigations. And we also set up surveillance systems and contact tracing operations in many different parts of the world, depending on what the needs are. So we have a broad epidemiologic focus, but we're quite data heavy, and we develop a number of tools that we use in-house to do this work, but we also work with many partners in many countries in sharing tools that we collaboratively develop. Thank you very much.
That's an amazing scope of responsibilities and accomplishments. Out of all those things, Oliver, can I ask, is there one of those aspects with which you are most personally involved that occupies most of your time on a day-to-day basis?
Well, I mean, we manage a large number of events all of the time. We have at any one time about 160 different events that we're responding to around the world. And each day some events get closed out and new events come on. So it's a balancing act between identifying what's going on and keeping track of it. And one of the big challenges that we have is actually managing such large amounts of information. Each event that we manage creates a huge amount of information, and digesting and sharing that is a real challenge to us. So my particular role is to, I'm at the interface between the technical team who's doing the work and then, the response team that's responding, as well as interacting with different countries.
Very good. Thank you for those insights. Andrew, how would you describe what you do on a typical day?
Yeah, so in my work, I am primarily focused on the intersection of business software, real estate business software, and artificial intelligence and machine learning. So we're not as much doing the cutting edge machine learning research that perhaps members of the audience are doing, but instead what we're doing is we're paying very close attention to all of the breakthroughs that happen in the academic world, and then figuring out how to take these pieces and build them together as part of broader products that actually fit into people's daily lives, fit into their working environments, and actually sort of solving that last mile problem of getting these amazing breakthroughs in machine learning into people's hands and actually, doing work for them. And to do that, a lot of our work with ML focuses around the workflows that happen in these businesses, automating these workflows, optimizing these workflows. A lot of it involves computer vision, conversational AI. And so, as I sit on this panel today, my work doesn't directly connect to public health or to COVID, but COVID, of course, affects all of us. And so COVID has affected us and our products and our work.
Very good. We'll have an opportunity to hear more about how it has affected your work as we circle back. I appreciate it. And Sarah, what can you tell us about what you really do?
Hi, Joseph. Lovely to be here. It's already exciting to see the spectrum of experiences that other panelists bring. What I do is a lot of my research is focused on how do we create interpretability tools, particularly for machine learning models that are considered black box. And a lot of what motivates my work is end domains like healthcare. It was really interesting hearing Lynn talk about her experience because, in fact, 90% of predictions in healthcare are still based on heuristics, which are developed by domain experts as well as rule-based. So a lot of what motivates my work is how do we equip domain experts like Lynn with interpretability tools to leverage machine learning models in a way which is responsible and still gives us understanding of model behavior.
Very good. Good. Looking forward to hearing more about that. And Heng-Ji, what do you do in your day?
Hi, everyone. So I'm a professor. Normally what I do at this time is to teach my class. I was recruited at really last minute yesterday or the day before yesterday, I don't remember, by my boss at Amazon because I joined Amazon Scholar a few months ago. So normally I will say no in my academic world, but in industry, I just cannot say no. I'm replacing him. But more seriously, I would like to talk about my research on COVID-19 literature mining. So I have been working on finding knowledge, construct knowledge network, knowledge graph from scientific papers, and try to build a bridge between scientists and doctors. So I'd like to share some results with all of you. I went to UCSB in February. So that was for another workshop William organized. That was actually my final trip before pandemic lockdown. So it's very memorable for me. Very happy to see all of you.
Good, good. Thank you all for those clarifications and introductions. Some of you deal with machine learning and AI more, some of you deal with it less, but all of you deal with different kinds of data. I wonder if you could tell us what kind of, what are the data that are most useful that you use to draw insights and make decisions about COVID-19 related problems in your particular professional role? And if you could tell us, are these data related to understanding the effects of the disease and what kind of effects? For instance, some will be on business processes, others will be on individuals' health. or are these data about transmission or possibly interventions? What data are most useful to you, and what make it useful? What are the nuances that make it particularly useful and interesting? And let's keep going around. Lynn, if you wouldn't mind addressing that first.
Sure, thanks, Joe. So really, as a clinician and as an educator, I have spent every day on a variety of dashboards. And I am looking at real-time data from, of course, our local community, our state's community, our neighboring counties, our national data, and spend a lot of my day, again, real-time, staying up to date on that data. And I think to Sarah's point, really trying to take on the task of interpreting it for whether it's our hospital administration and leaders, our county health leaders, academics with whom I collaborate at UCSB, or the community at large. But I would say on a very kind of in the trenches, on the ground way, I am taking data that is real time, that is available to me from now, of course, a tremendous number of sources, and trying to make it digestible to the receivers, to the people who really need to understand. With that, of course, I do spend a lot of time also, I think, from more of a consumer user perspective, looking at and using forecasting tools, very much again on the consumer end of it than compared to the rest of you. And I think what I would point out is, of course, what everyone on this call knows well, which is as we move from what's happening today to what's happening tomorrow, the public and the leaders making decisions for the public are obviously faced with a tremendous challenge in how that data is being presented to them, who is interpreting it for them, and again, all the nuances that come with that. So I think that's in a nutshell how I am using data right now.
Very good. Lynn, just to follow up, when you say you're using dashboards, I assume the dashboards are presenting incidence data, how many people are infected, how many people are hospitalized, how many people are sick, and you're using that for different regions and different aggregations. Would that be correct?
That's right. And I think, again, everyone on this call or on this symposium is well aware, but remember, even just that data has tremendous heterogeneity. As our denominator with regards to test positivity has fluctuated across the time course of the pandemic and geographically around the world and around our nation, just interpreting something as simple as test positivity has been a challenge. Trying to get the media and community leaders to understand that the hospitalization metric may be the most accurate, but of course is delayed by 1 to 3 weeks with regards to a primary transmission event, it is again another set of challenges. So that, you're exactly right. It's really based on incident, case rates, test positivity, and I think all of the really public-facing dashboards that I'm working.
That's a central paradox that you reminded us of. Even real-time data are by definition historical data when it comes to hospitalizations and infection. That's fascinating. Oliver, you're dealing with lots of different problems in lots of different locations. What are the data sources that are most helpful to you? What are they about, and what do you do with them?
Well, actually, what Lynn said resonates a lot with me, and around trying to interpret information and data, and the more you have, the greater the challenge of interpretation becomes. At the simplest level, we receive information around cases and deaths. I mean, as the let's say the essential variables that we're receiving information from every single country in the world every single day. And many different contexts, and to have information that is comparable or even interpretable across many different countries, not even talking about within countries, but across countries, is a really major challenge. I think the broad category of information that actually, in my experience with COVID-19, but also with all other infectious diseases, that really is the most useful is the contextual information. And that is a loose collection of different types of information that can come from any kind of source that you can imagine. And what we really use at the moment is expert knowledge in individuals who often know the parts of the world that we're talking about and have an idea about the cultural aspects, the social aspects, climate, the types of animals and agriculture in those places, and so on and so forth. And so we have a kind of a human synthetic approach where we have people who understand the particular places and understand those contexts, and then feed that in and matches that with the kind of raw numbers that we get. We're working hard to try and include more and more let's say, automated approaches to trying to understand context, digesting a lot of different information types, using natural language processing tools to try and extract information from different sources and digest that. But I would say, broadly speaking, contextual information is what really makes the data useful.
Very good, thank you. Andrew, you deal with data and problems of a different kind. You mentioned earlier that part of your mission is to develop software to help people with data. What are the data that you find most useful that help you design the systems that you're involved with?
Yeah, absolutely. The connection between COVID and ML systems that I think is most interesting in the context of our work that I'd really love to highlight it's not exactly how data and ML systems can help in the fight against COVID, because obviously we're not a health organization and that's not our area, but it's actually the other way around. And it's the effect that COVID and specifically the lockdown is having on the world and on potential applications for machine learning systems. So for us, we work every day to do this, to actually get this machine learning technology to fit into people's lives and to automate processes, optimize processes, these sort of things. And the observation that I'm going to share with you here is very obvious in retrospect, but it took me a while to come to this observation, which is that when you're actually trying to fit this technology into people's lives, a machine learning system can only really be effective if people are willing to digitize the things that they are doing, if they're willing to work, if the information that's flowing around is already digital. Many business contexts are not entirely digital. Many business contexts, you'll have a real world office, you'll have people interacting face to face, and then after the fact, you go through all of this work to try and get the important information into information systems, into systems of record, to keep track of what's happened, to keep track of what was agreed to. The lockdown and COVID has fundamentally changed that. And today we cannot easily interact with each other in any sort of physical environment. And now as a result, everything is being pushed into digital media, just as this interaction right here, as I'm talking to you today. And that really changes the game for us as we are building technology systems and as we are trying to take the amazing innovations that come out of ML breakthroughs and apply them to people's lives, because we no longer have to work hard to get people to digitize what they're doing or digitize their business. They must digitize. We speak in shorthand that say that COVID has sort of advanced. It's been like a 5 to 10 year leap into the future and the trends that we're already moving forward in terms of digitizing things. So this means that now there's a ton of data that we can derive insights from. And that's actually where the ML fits in, which is, let's say you've got a conversation like this over audio and video. If you and I were agreeing to some important business arrangement, or there were details of this conversation that were critical to record in a system of record, it is only ML technology that can take this unstructured conversation and from that distill down to actual facts that need to get recorded. And so I think that the cultural changes that we're seeing as a result of the lockdown are going to mean that there's going to be far more ways to apply ML over the next 10 years as a result, because everything is now digital and we have far more information to work with.
Fascinating, thank you. Just to clarify, I don't think we mentioned that part of the mission of Andrew's company is, at least initially, it's property management software. And so the pandemic has affected people's mobility and the rental business and so forth.
Yeah.
So I think this is their core focus, but as we're hearing, it becomes much broader into a variety of businesses. That's fascinating that life has become digital as a result of the pandemic. Fascinating. Good. Sarah, what are your favorite data? What are the data that you find most useful in relation to COVID-19, and what do you do with it, and what interests you about it?
So my vantage point is a little bit different because in some ways as a researcher, my role is to not be too data set specific. And in fact, is to develop techniques that are not tied to a single data set, but allow interpretability across many. So perhaps I'll zoom out and perhaps I'll talk about what aspects of data specific to COVID has made interpretability so complex and so difficult, which is that the data which has emerged is not in the static form that is very typical of lovely research data sets. It's in fact evolving over time. So Oliver and Lynn both mentioned this, but it's also the selection bias of what data is reported. So particularly with forecasting problems, which we've seen a lot of in this pandemic, mainly because of the need to have some estimates about progress, it's very complicated with parametric models to have a data set which is missing certain slices. And that being said, is that a parametric model basically reflects the data that's trained on. So we have both missing slices in terms of we've over-indexed on the most critical cases, but also we have a variety of sources. So we have non-uniform inputs. This is what Oliver was really talking about in terms of the chaos of multiple different nations or even hospitals who are reporting things in different ways. But finally, we also have certain biases in terms of the representation of certain racial groups or different age groups. And how do we essentially ensure that the way that we're interpreting reflects what we know is missing, but also doesn't amplify questions of fairness? And so these all pose particular challenges. It's very interesting. The last thing I'll say here is that Oliver mentioned this defaulting to contextual information. So this is very common when, in fact, you don't have high certainty in your data. You default to qualitative support to allow you to weigh things better. It is not great from an interpretability perspective, from a machine learning model, because the tricky part is when you're relying on contextual information, there's an asymmetry of who has access to that information. So it's made interpreting these particular forecast models particularly tricky if we think about it in terms of how to place certainty on estimates.
Fascinating. Heng, same question for you, please. What are your favorite data? Why are they interesting? What do you use in relation to COVID-19?
I would not call it the favorite. I think my feeling is always very mixed feeling about this data. So the data I'm processing is scientific papers. The motivation is really like there are just too many papers published about COVID-19. I think everyone says, every crisis is the opportunity, but there were just too many papers. On average, there are about 650 papers published every day about coronavirus. So it's just becoming impossible for scientists to read and do the knowledge discovery. So my goal is to be able to convert this data to semantic information and then from information to knowledge, to be able to speed up the knowledge discovery, scientific discovery. So one scenario that I have been working on with doctors and biologists is this drug repurposing. So for clinical trials, you may have a long list of candidates, and these candidates change over time every week. It's very expensive to do any kind of clinical trials to rank the candidates. Also, it's very difficult for them to decide the threshold, like what we mean by success, right? Maybe 60% people, 70% people, they got their symptoms reduced. Is that a measure of success? So what they really want to know is what kind of chemicals and genes related to coronavirus and that are connected with these candidate drugs. So what we do is we go ahead to extract all kinds of information, entities, relations, and events involving these entities from massive amount of scientific papers, construct a knowledge graph, and then we provide a search engine, question answering engine for these users, so they can answer questions, so they can get to see the evidence from knowledge graph. And we also work on drug repurposing report generation. So we get a fixed list of questions from doctors and scientists, and then we are able to provide answers to generate report automatically for them. So far it has been quite a learning experience, I would say, because I learned to kind of narrow down the research scope to a very specific problem. And I also learned how important it is for us to work closely with the domain experts and get feedback from them constantly and to improve our technology. Yeah.
Fascinating. Well, I think you raised an issue that kind of leads us into the next question. In your efforts to try to synthesize the knowledge that's showing up in this vast amount of publications, you are most assuredly trying to make some application of AI or machine learning, and that really is the next question for all of you. And Andrew hinted at this already, but perhaps each of you can tell us a bit more. To the extent that you are applying artificial intelligence or machine learning processes, what, in very simple terms, for those of us who are not expert in that area, what can you tell us that machine learning is doing or AI is doing that helps the process become more informative, that leads to different kind of insights than before you were able to manage without the application of AI and ML? And if you're not using those particular applications, perhaps you can tell us what kind of contravention or new invention in the data that you are using has made it more insightful for you to be able to interpret. And if we can focus on AI and ML if you're using it, and again in simple terms, I would love to hear about that. Let's go around again, and that means we'll go back to you first then.
Sure, and maybe for this one, it is actually good for me to go first, because I wanted to just take just even a few seconds to give context to my opening comment with regards to just really what is happening on the ground in the world of public health and clinical infectious diseases.
Good.
We literally still have public health nurses with clipboards going out and saying to a person with an infectious disease, "You have an infectious disease. Where were you? Who were you around? And do you know their phone numbers?" Just for context. And I'm not saying that it's this archaic throughout the world, throughout my community, throughout the country, but I just point out, I think for context, I think our opening really excellent keynote speaker, had the wonderful quote that it's the absence of AI technologies that's already killing people. And I would just emphasize that I think without getting into any of the controversies regarding AI and whether we're going to overpopulate Mars and with what speed we're going to do that, just more frankly on the ground, if I, as a clinician, as someone who is passionate about community health and public health in my own community, in my own state, and around the world, if I had the ability to, again, more ubiquitously roll out the Apple Google app or other versions of the different, I think, AI and ML founded technologies that we've spent the morning talking about, I can unequivocally tell you we would be saving lives. And so I think it's a long-winded way of saying I, in my day-to-day, yearn for using more AI and ML, but I really fundamentally would argue that we are not yet.
Fascinating. You also bring up a paradox that I think Andrew's earlier comments made clear. They're clear to me as well in terms of now because of the pandemic, everything has gone online. My own research as a social scientist, I study human relations and how people communicate through technology. When I started studying this, your email was a slice of your life. Your use of Facebook was a small slice of your life. But of course, since the pandemic, all our relationships have become entirely online. Although you have reminded me, the only parts of our relationships that are not online are the ones we are capable of transmitting a virus to one another. That is happening face to face. We have data about everything else else except potentially the most vital part. So I understand what you're saying, Lynn, about we need more data, we need more application. I understand what you're saying, Andrew, that everything is online except one thing. But perhaps we'll learn more about those things. But let's continue around and perhaps back to you, Oliver. Tell us how ML and AI are changing things. What we're learning that we have not been learning without them.
Yeah, I think it's certainly assisting us in doing our work, and that's probably the best framing of it. I think we have a machine, a data machine called epidemic intelligence from open sources that digests information that's digitized, and we get different types of information. For example, some information coming from ministries of health. We get information coming through maybe listservs from academic or professional groups. We get information from media sources, all sorts of different sources. And we have to work our way through it and pick out the relevant pieces of information. And we're currently processing about 500,000 kind of different pieces of information each day. This is around the world, and they're in different languages and all sorts of different features of those data. And we use natural language processing to help kind of work with those data and try and extract the information that we're looking for. But we still end up having to, which I alluded to, really there's quite a lot of human touch to really understand. The natural language processing can help us work with those data and get through that in a day's business cycle. But really to properly understand it is really taking humans, trained individuals, to look at it and understand what these data are telling us. And I think that's, as we go along, it's getting better and better and helping us further and further. But we've still got a long way to go to really make sense of all of this different information. And it has to happen in real time. We have to do it in every 24-hour cycle. So the more we have that can improve the work, and also working across multiple different teams in multiple geographic locations. And what Andrew said, I thought was fascinating about, how digitizing information and about how we work with it amongst each other is also changing.
It sounds as though you share a concern that Lynn expressed to us. You're getting data in machine readable form, and you're getting the information coming from people taking notes on clipboards as well. And it sounds like your challenge is to find a way to aggregate and synthesize these things.
Well, yeah. I mean, I would just echo what Lynn said. I mean, in public health, particularly, digitization of information is still a challenge that hasn't been overcome, largely speaking. It's similar to the clinical interaction when you go to see your doctor, and they in some practices they are entering information during your consult, but I mean in many other parts of the world, it's still happening on paper. And having digitizing information in public health, really, there's a lot of work to be done there.
Very good. Andrew, you were the first to mention AI and machine learning applications when we were going around and talking about what we do. Can you give us an example, illuminating example of applications that have changed the way you're able to understand things, or your clients are able to understand things because of AI and ML applications? Thank you.
Yeah, absolutely. I'll give you a very concrete example. So in many businesses, probably most businesses today, most businesses still get a ton of physical mail, right? And this physical mail still has a lot of very important information. Sometimes the most important pieces of information still arrive in the mail. And for years, we've wanted the people who use our business software to digitize all this physical mail. We'd love them to go to the scanner, scan it in so we have an image that we can work with. And then once we have an image, then machine learning computer vision algorithms can do so much work for them. And when we can't get them to scan it themselves, we also offer mail scanning services, right? You know, for a price, we'll scan your mail for you, redirect it to a facility, we'll scan it all. You don't even have to touch it. Now, prior to COVID, this was a much harder sell. Prior to COVID, people were like, well, I'm already getting the mail, I'll open it up. You know, I don't really want to deal with scanning it. The conversation totally changes once COVID happens, because at that point, no one wants to go into the office. No one wants to have to interact with colleagues while opening mail, these sort of things. And the idea of, you know, paying some reasonable fee to use a mail scanning facility all of a sudden is extremely exciting, because they're now working from home, right? How are they going to get at their mail? And what they would love is get all that physical mail digitized. And then once it's digitized, they can see it through the computer. And so that's just one of many examples how COVID has pushed everything to a digital format. And now once it's in a digital format, these amazing ML technologies that have been built over the last 10 years can take hold. And a lot of the things that they were doing in the first place when they sat there looking at this piece of paper, now an algorithm can do, you know, data entry tasks, these sort of things. And so mail scanning is the example of today that we have deployed applications that people are using today. In longer term, I think that it is more the video feed, the audio feed, you know, that less structured data that's harder to deal with, but ML technology will let us sort of do the same basic thing, but on that less structured data.
Well, let's say I'm a small business owner or a business owner of any kind. I understand the advantage of having all my mail scanned and digitized. That means I can read it from home. But you're saying that there's another form of value to add to that, is that we can apply machine learning algorithms and do different kind of analyses once things have been digitized. So on top of my being able to read it from home, what does the world have to offer me through the application of machine learning once I scan my mail?
Yeah, absolutely. So I'll give you an example. Many businesses have an entire department dedicated to accounts payable. They get thousands of bills a month in the mail. They got to figure out, should I pay this? Is this a legitimate business expense? Have they overcharged me? Did they actually do the work? There's all these questions that they have to ask, right? Now, computer technology, even traditional software, can answer many of those questions, right? We've got access to the financial accounting system. We know the budget. You know, there's all these routine questions that we can ask. But when the format of the information is in a physical context, you can't just automate it all away, because a machine still doesn't know how much money was this invoice even asked for. There's a piece of paper in the real world that they can't even see. And so there was a data entry task that was particularly onerous before. Now that the physical things are digitized, we can deploy algorithms to do the data entry, and then we can apply algorithms. We can just do traditional software to do the math, right? You know, is this within budget? Did you expect to spend it? Is there a purchase order for this? Okay, well then we'll just write the check. Those things are easy. We expect technology to do that, but it's that sort of last mile of the digitization that we didn't quite have until now.
Fascinating. So now it's not just a matter of ubiquity, it's a matter of analyses that would take people to do, and not necessarily as consistently or carefully. Fascinating. Thanks for the illustration. Good. Sarah, where do you see ML and AI applications changing things in a way that's improved your ability to provide insights or decisions?
Yeah, it's actually a really interesting question, because it could be defined as broadly or as narrowly as you want, and which makes it a fun one. So I work primarily with very complex models. Like, a lot of my work is with deep neural networks, which are considered black box. And a lot of it's how do we leverage those models to provide highly reliable and explainable insights. In many ways, your question is, how has that changed this task, this period of time under the pandemic? And I would say in a few ways. Like Andrew mentioned, this growth of multimodal data. So multimodal data is where you have language data and video data and audio data. And in many ways, the challenge is both a modeling challenge as well as an explainability challenge. So how do you incorporate data which is formatted in very different ways and which may be extracted using different models And how do you weigh those jointly to arrive at a decision? But secondly, it's an open challenge how to interpret multimodal data sets, primarily because we typically have multiple models involved. So then how do you explain the final decision as a weighting of the former? Another thread that I wanted to talk about from an interpretability lens is something which has come up in the discussion, is that the challenge on the ground is not deep neural networks. In many ways, it's interpretability for the data distribution itself. And those tools tend to go back to very basic statistics. So often, simpler is better. How do we understand anomalies? And how do we do anomaly detection within data input distribution? So this is a topic I've done quite a bit of research on, and it's how do we have automatic tools to surface to domain experts what is uncertain within the distribution. So surface examples that are more challenging for a model to learn, or even basic rule-based. This is not formatted in the same way. Surface, is this record recorded the right way? And I think it's a good reminder because this was mentioned at some point already, but the truth is, when we talk about AI, the temptation is to jump to deep neural networks. But in fact, for many use cases, we want simple interpretability tools that the domain expert feels confident using that can help surface issues with data. Because in this scenario, one of the key traits is a lot of data at once, but of unpredictable consistency. And really the challenge becomes highlighting that in a way that doesn't require a lot of human hours. So Oliver talked about not having that many hours in the day. It's how do we create interpretability tools and outlier detection methods, which my research has focused a lot on, that can surface to his team what he needs to spend time looking at as problems.
Fascinating. Good. Well, Heng, you kind of started us down this trail when you described that you work on systems to take all these articles that come out and synthesize something meaningful about it. I wonder if you could tell us more about that. What does AI or machine learning do to help you accomplish that? Or in other ways, how does it help make your decisions and your output more fruitful in relation to COVID-19 issues?
Sure. So I have to clarify, this is really not a new application. Because of COVID-19, we have a small community called BioNLP, which has been there for more than 15 years. And people have been doing this, from biomedical literature, chat culture knowledge graph. So in the past, we just enjoy, having any successful methods from news domain, and then we just consider paper as a language, just apply anything we already put more effective in news to literature, and we publish papers. So that was my initial thought at the beginning. So in the middle of March, I thought, okay, since I have this machine learning model, I already know it will work for news articles. Let me just train it for a new domain, new ontology using new training data. That's it. And I put up the knowledge graph up to my website. And then we got 600 downloads. I don't know who are using them, but it's kind of amazing. And then we got a lot of contact from many medical school students, 60 medical school students. They volunteered to help us annotate data, look into results. So then I feel a lot of responsibility. And we're not just talking about getting F score 80% and publish a paper, where this is about life test decisions, right? So then we start to look into the results, and then I realized it's not a good culture really wait for everything that is like successful in our general news domain and apply to literature. There are many really interesting and unique challenges about papers. So for example, the sentences in papers are very complex, right? Because they are written for domain experts. And the authors, they won't bother to explain those abbreviations, particular concepts, because they assume you already know that as part of your background knowledge, but the machine does not know that. So it's very different from news. When we talk about some new entities in news, we try to explain the title of this person or explain what this company is about. But in articles, that kind of methods, the dominant deep neural network methods using semantic embedding representation will completely fail in this kind of genre. And we also need to, for example, look at multimedia information, because a lot of the side effect results, how the clinical trials results are all reported in figures and images and tables. They are not written in natural language text. So that's why we start from scratch, basically. We start to build a new ontology, new benchmark, and look into new way to encode semantic representation, change the neural architecture, and then collaborate with computer vision experts. So I think these are the good lessons I learned. Basically, if the application is really, really important, we need to seriously look into what they want and look into the challenges about the particular data set. Yeah.
Very good. Interesting. So a lot of different perspectives, a lot of different approaches, and ML badly needed, doing much different things. My next question is, if we could give you as big a research grant as you needed, or if William Wang gave you his credit card and said, go out and get whatever machine learning or AI application you need, what would it do? In other words, what new development in AI or machine learning do you wish you had that would help you process information or make the kind of decisions that you need to do in each of your lines of work? What's the next step? But not in terms of algorithms, but what would it help you accomplish with information that would make it more useful in terms of the goals that you have? And Lynn, you said you would welcome just about anything. What would be your first pick?
You're muted.
Thank you. So I think the last couple of hours have given me I think an increased optimism that I don't need that credit card. I think that the direction that things have moved this year have been incredibly positive. And there are two specific but very different topics that impact me, my students, my residents, and all of our patients very directly. I think the first is, of course, the contact tracing piece. And I think that anything that we could do to accelerate this buy-in by the public, the privacy hurdles and some of the really excellent bioethical discussions earlier today. I also wear the hat of IRB chair for our institution. And I think anything to get us on solid footing, again, with regards to contact tracing going forward, is going to have a real, tangible, quick impact. I think the second, just to Heng's point, this is an unprecedented year for so many reasons, but top of my list really is the burden of responsibility we've put on our clinicians around the world in keeping up with the science and making sure that literally today, I am aware, as I am faced with a patient with severe COVID-19, I'm aware of where the data stands right now so that I can do the best by the patient in front of me. And to some degree, as much as I like to think I've kept up day to day, really since January, I know that what I was doing in May is different than what I did in July and different from what I'm doing right now. So I just, I think, again, optimism that what I've heard today with regards to the huge benefits that we are getting from ML and AI in giving the clinicians around the world the tools that they need in their tool belt to be able to, in an efficient way, get those answers in a way that, again, they can help the patient in front of them. That's, I think, the two clear applications for me.
Very good. Oliver, what's on your wish list?
You know, one of the things that we we're kind of looking at for, you know, next year maybe, which is on our wish list, is really how can we pull in all the different pieces of information around a single event and create a narrative around, or a kind of synthesis of all of that information, and do that automatically. So, for example, any outbreak or any kind of outbreak around the world, you know, you might have information about obviously the cases, but also, you know, some laboratory information. You might get different types of information from different sources. There may be, you know, agricultural or animal information involved, and at the moment, you know, we have to pull all of that together manually. We also have, a lot of problem with, multiple different sources reporting slightly different things, kind of to Lynn's point, with a fast moving event, staying on top of what's happening is particularly challenging, and different reports, have different, they're not always up to date, or you don't have the most current information. So I think, one of the things that we'd really like is to be able to pull in all of the different strands of information around a single event and help synthesize that in a way that really, maximizes the amount of time that we spend on the kind of the human touch of the data.
Very good. Thank you. Andrew, how about you? What's on your shopping list for the next big development that'll help you analyze data even more beneficially?
Yeah. So the challenge that we run into, that I know there's been some academic work in this area, but I'd love to see improved tooling and more accessibility, is that when we're working to try and bring machine learning developments into real business contexts, it's really, really common that the most interesting data sets have a ton of private data commingled with a bunch of other data. And this can be a challenge because we have access to really large, rich data sets, and we can't share those with outside people. But usually the people who have the best ideas about how to solve these problems are people outside the organization. And so from a collaboration, from an open source perspective, we'd be really excited about being able to more freely, work on algorithms to interpret, documents or these sort of things, because that's something that, we just want to have the best tools. We don't need to keep it private necessarily. But a challenge that we always run into is that, to use the accounts payable example that I used in the past, when we go out and look at what other researchers have out there that they've maybe shared, usually they can't share their best data sets. And so as a result, you end up with, it seems like a lot of the really vibrant progress in the industry happens surrounding large open data sets. If everyone's using Reddit or other, open sources of information, and when your data is inherently private, there's a lot of challenges there. And I know there's been some academic work done in this area, but it hasn't really translated into tools that people are actively using. So I would love to be able to somehow bring in external innovation without violating any of the necessary privacy guarantees surrounding our data.
So when you talk about private data, you're talking about data sets that contain personally identifying and sensitive information about individuals. You're not so much talking about data sets that are proprietary and owned privately by a corporation, although there could be some overlap. Is that correct?
That's right, like incidental PII. So if you have a document, there's no trade secrets in that document. There's nothing terrible in there, but there's people's names, phone numbers, addresses, and so for privacy reasons, we can't distribute that or share that with people, of course. But it would be great to somehow enable innovation to interpret these data sets without getting tripped up on violating anyone's privacy.
Very good. Sarah, you deal with much different kinds of problems. What's on your wish list for the next development that would help you find more insight in the data that you deal with?
Well, it's interesting. I was going to talk about an extreme of what Andrew is describing, because it's a very interesting relationship when we want to train models beyond just test set accuracy, when we want our models to not only be high performance, but fair, interpretable, robust, privacy, which Andrew mentioned. When we weight one of those properties, we tend to compromise on another. It's the no free lunch. And at an extreme of what Andrew is describing, we have algorithm models for things like contract tracing, which have to be privacy preserving. In fact, they guarantee privacy preserving. And what's interesting is that by definition precludes a lot of types of interpretability that we normally think of within our interpretability toolkit. And so it becomes harder to audit the model, but I also see it as a huge opportunity because in many ways it forces interesting new ways for us to validate that the behavior of these algorithms are the way that we expect. For example, thinking about complementing algorithmic tracing with just more human capital invested in tracing to see if the behavior can be audited using humans doing the same thing, but it goes beyond that. It's even how we think about new ways to still gain intuition into the decision boundary while preserving privacy. And it's often under the most severe constraints that researchers do the best. So in some ways, it's an exciting new chapter because we're facing this heterogeneous landscape of multimodal data, enormous volumes of it, but also needing to guarantee that other properties are not compromised in the process of gaining intuition.
Very good, good. And then back to you, Heng. What's on the horizon is the best new development you could hope for in AI and ML to help you do the synthesis work that you're doing?
So I guess I don't need more money. I don't need a Williams credit card. I need more time. I mean, I need more time from both the domain experts and also myself. So for example, for the new ontology construction, we do need to find more fine-grained knowledge elements, right? Because in the past, in the community, people only look for chemicals and genes, but now we are looking at 140 types of entities, how they interact with each other, how they affect the disease, and what is their connection with the different types of drugs. So this will need a lot of time from the domain experts to help us define the ontology, annotate some benchmark so that we can do our hill climbing of our algorithms. And I only have their time during their evenings and weekend because they need to do something more important in hospitals. I don't blame them, of course. And our biologists, they are also very busy at something more important. For example, designing their drug testing device and those kind of methods. It's much more important than helping us. And for me, I need more time because I'm now in the middle of my DARPA evaluation. We are looking at drone bombing and Ukraine-Russia conflict. It's just, I know I wish I could spend a lot more time on helping scientists rather than looking at why Russia and Ukraine are conflicting. So I don't know how to solve the problem. I guess we will have to prioritize our own research time and maybe make the annotation more scalable, I guess. Maybe. So I'm now actually building a platform. I already have a platform that can collect papers from 3 APIs on a daily basis, and we're updating knowledge graph. And I hope to get more domain experts to help us in a much larger scale in crowdsourcing way. Yeah, I think that's
so the improvements that you see that you, with enough time, you'll be able to produce them yourself. And that may be true for many of us, but it's fascinating that these things are within your grasp, but we're just a little bit beyond them. The next question on my list resonates just a little bit with a question that one of our attendees raised. Now that question came up for Oliver Morgan in particular, and our attendee asked something about contextual data in terms of how will that help in terms of different cultural and social aspects that are currently challenging your work. How might more contextual data help you figure things out better with response to the cultural and social aspects? But I think all of us deal with cultural and social aspects of the data. Clearly, data come in different forms, and a lot of work is going on to try to make it interoperable and machine readable. And Oliver talked about natural language processes before, trying to help contribute to that. But I wonder what other cultural factors. The World Health Organization deals with different availability of data, different cultural nuances of data, and different data that are particular to different regions or countries. Lynn has mentioned this also, is that, all these different data sources that she might want to take advantage of, they don't all say the same thing that she's trying to find out at the same time. All of you will face challenges in trying to get data, aside from Andrew's challenge of trying to get a more comprehensive data set. What are the barriers? Are they cultural? Are they legal? What are the issues that help prevent you from becoming more comprehensive in the analyses that you would like to be able to perform? And we'll go back, sorry to keep doing this, but this round robin seems to work okay. In fact, it's been very stimulating. Lynn, can you start us? What are the cultural, legal, or developmental barriers that would help to remove for your work?
Well, as I've done a couple of times so far, perhaps what I'll do is actually expand on the question by giving really some real life examples. Let's think about the clinician's approach to a patient 50 years ago, without data sets, but with perhaps clinical training, experience. The clinician approaches a patient and absolutely assesses the patient with an exam, but also whether deliberately, subconsciously, or perhaps deliberately excludes some, we can use the word bias, we can use the word categorization, we can use the word contextual, but brings with them some stamp with regards to perhaps that patient's socioeconomic status, that patient's perhaps race and ethnicity, less so to do with perhaps race and ethnicity, but perhaps truly to do with the fact that some race and ethnic groups have different genetic predispositions to certain diseases, including in the world of infectious diseases, tendency towards metabolic syndrome, tendency towards diabetes, and the list goes on and on and on. We had a fantastic grand rounds at Cottage a couple of weeks ago, given by one of our senior residents, that addressed really the challenge of when is that contextual framework that a clinician applies to a case crossing the line between being beneficial and being detrimental. And so I think, again, I would just point out, again, to expand perhaps on your question, I'm dying to hear the rest of the panel's answers, but I think that the challenge is this has been part and parcel of clinical medicine and public health approach, and a necessary piece, a critically necessary piece since the dawn of these professions. How can we make sure, if we're now introducing big data, ML, AI, into these fields, how can we make sure that we're using this for good and not evil? And so I'll pause there. And that's I think, I don't know the answer, but that's my version of the question.
That's a humongous question, Lynn, and thank you for leaving that with us. Let's continue.
Here you go.
No, it's the question of our generation. How do we facilitate equity without crossing a line? What do we need to know in order to do it, and what are our guidelines? It's a question that I think troubles all of us in a number of our practices, but clearly because of metabolic issues, it troubles your profession especially hard.
And I'll just perhaps to phrase it, again, for just one last tiny anecdote. On a daily basis, if I am approaching a patient who may or may not have COVID-19 in our community, and we have a community that's about 50% Caucasian Hispanic, and 50% primarily Caucasian non-Hispanic, and I know that our Hispanic patients have been very, very disproportionately affected by this disease, and may, again, statistically have a slight increased risk of diabetes, metabolic problems. Ought I, as a clinician, consider that patient's ethnicity as I approach that case, both with regards to the likelihood of that person having COVID, but also with regards to how I treat that person? So that's the anecdote.
And the more information, the better, or the more information, the more of a paradox.
Right.
Fascinating, and thank you. So let's go on, Oliver. What are the barriers? And I'm sure there are many, given the global nature of your organization. What are the barriers that you find that make it difficult to synthesize data or perform analyses with AI and ML?
Yeah, I think it's really finding the the key elements that matter in terms of trying to interpret the data is probably the biggest challenge for us. I think when you're talking about people's health and you're talking about the transmission of infectious diseases during outbreaks, people's behavior is inherent in that, in the spread of diseases, and understanding how people behave is critically important to understand how diseases spread and how interventions can be most effective. And so that component is often very difficult to manage quantitatively, largely because the type of information, I mean, Joe, you mentioned that you've been looking at these issues for a while. I mean, the type of information about how people interact with each other and, is very difficult to have in a digital format. Just to give an example of how difficult it can be. I mean, I'm thinking, just to use a different example from COVID. I think in 2016 we were working on an outbreak of a disease called Rift Valley fever. It's a viral disease that the virus is transmitted from animals to humans, and these are often livestock animals. And in Niger, they have a large nomadic population that drives their cattle for many hundreds of miles across the country, and in fact, across the border into the neighboring country as the rainy season changes. And so all of these cultural factors and location environmental factors really feed into how to assess the risk of a few cases. Does that represent a risk of a large outbreak or does it not? But you have to take into account, the environmental factors, the animal factors, the human behavior factors, all at the same time. That's really, I think, the most challenging aspect of interpreting any data that we have about people's health.
Very good. Same question to Andrew now. You mentioned a very interesting way, the privacy restrictions that prevent you from getting data that you could otherwise use usefully. What are the other barriers? Any cultural, legal, or other barriers that stand between point A and point B for you?
So in terms of greatest barriers, there's sort of two questions that have been discussed. One is the greatest barriers, and another one that was mentioned earlier by Lynn was like, how do we use AI and data to do good in the world and not do evil? I would say that there are certain things, in my role, we're taking the results that researchers create and figuring out how to apply them to the real world. And when you do that, when you're not working in a abstract academic context, but instead in a very concrete context, certain things get a lot harder and certain things get a lot easier. The things that get harder are things like, okay, you can recognize something in a computer vision context in the abstract, but how do you actually make it useful to this person in their workflow? Those things are harder, but things that are easier are actually things of, not of ethics and not doing harm, because you're very close to the problem and you know what's going on. You don't have to think like, well, what are all the possible different ways this could be used? Because you actually are so close to it, you know exactly how it will be used. And I'll give you a very concrete example that has happened at our company. If you think about potentially problematic ML models, one of our products allows landlords or property managers to make decisions about who should be able to live. You have many people applying to live in an apartment, and it's going to make decisions about who is the most likely to actually pay their rent versus not pay their rent. Now, you could get yourself into a very problematic situation if you built a deep neural network that had access to a ton of data and it was a black box model that you couldn't explain, right? And if I understand correctly, a lot of Sarah's research is, how do you take a complex model like that and sort of understand what's going on in order to make progress on that, right? But what's great about being so close to the context is that you can just ask yourself, well, what would really be the benefits of a deep neural network in this context? It would be what? An additional 2% improvement in rent repayment rates, or it's some small amount of improvement over a traditional ML model that's easy to explain, which is itself only a small improvement over heuristics, traditional software heuristics that it can be very easily implemented in a way that's not going to do any harm. And so for us, it's actually much easier to do this because we can just choose the right tool for the job. And this is a perfect example where we just don't use deep neural networks for things that would be a problem like that, because we're so close to the context that we can just say, hey, for this application, an inexplainable deep neural network is fine, and for this application, it's not. And we can weigh the cost and benefits because we're so close to it. So I would say that that's one area that we have an easier time with, being so close to our problems.
Very good, thank you. Sarah, you try to make complex problems much more simple to deal with. What are the barriers that you are dealing with that are standing in the way of making things more effective and simple still?
Yeah, it's interesting. So I am guilty of being that abstract academic that Andrew is talking about. No, not at all. I think, in fact, it's a good forcing function, because the goal of my role is to provide interpretability methods which transfer over time and over domain. So it's actually the most challenging extreme. We heard earlier about this different medical problems. So now we're in COVID, but the next pandemic might involve a very different transmission rate. And so a lot of the interpretability methods I work on are how do we equip the domain expert to leverage information as a way that's actionable to their downstream task. A good interpretability tool allows the domain expert to be the final arbiter. In fact, I would talk about two different types, which are very, very different because they're very based on different end use cases. So we have single explanation methods, which are essentially trying to predict what is important for this particular prediction. And that's always going to be needed for end consumer use cases or end patient use cases, where a patient wants to know, why did an algorithm make this decision for me? But you also have the use case of, for example, Oliver is looking at this variety of different input distribution. And for a decision maker like that, it's much more important to know relatively, how does this relate relative to what the rest of the distribution is? And how do we surface outliers? And then the domain expert, frankly, for interpretability research has to be central, because the truth is that the composition of data for different problems is going to change. It's very interesting, this idea of how does this relate to other questions of fairness. So interpretability is really a tool to audit fairness. So the whole motivation of interpretability is to provide effective auditing tools to surface some of these problems which Lynn and Andrew have noticed anecdotally about their domains. And in many ways, the challenge of my research is that a lot of fairness to date and fairness research to date has relied on the presence of labels. But this is not a very realistic real-world assumption. We don't, particularly for fast-moving data sets, we don't have codified what are sensitive groups. And in fact, the goal of a lot of the outlier methods that I work on is how do we automatically surface these underrepresented attributes that the model is having trouble learning, because then that positions that, given a human domain expert's time is limited, extremely, as we've heard about these evenings and weekends when doctors are available to actually give input, how do we surface the most likely problematic data for them to look at? And that's what I see as very interesting, because the goal is to provide generalizable tools that put the domain expert at the center and that they have trust in, because it still allows them to navigate the data distribution in a way that they know best.
Very good. And I'm sorry to do this, but Hank, I must ask you to be brief because I've allowed us to get over time. I apologize, but can you give us in less than a minute, what do you think are the barriers that are preventing you from going forward, unless it's just time to do the work that you need to do?
I hope scientists can make their data more transparent. So for example, we cannot deal with the figures because we need to do OCR, we need to read the PDF. So if they could share their original source data, that would be extremely helpful. So, making it more transparent. The other thing is I kind of plead to bad scientists, please stop publishing too many bad papers, because we are looking at all kinds of conflicting hypotheses from knowledge graphs. So So if they, put anything bad data in their paper, our knowledge graph will be producing all kinds of noisy results. That's it.
Very good. Thank you. Well, thank you all for joining us. Thank you for watching. If you were one of the attendees, I apologize. I wasn't able to get to some of the really good questions that you asked, but I feel badly about that. But I want to thank all the participants for their generosity, not only of their time, but for their dedication, to Sarah for trying to make things simple, to Heng for trying to synthesize knowledge, to Andrew for trying to make things work, and to Oliver and to Lynn for keeping us alive and healthy as well as they can. Thanks for your participation. Thanks for all your good work. It's been my pleasure to be with you today. And now I turn it back over to the organizers to get on to the next segment. Thanks so much.
Thank you.
Hello, everyone. My name is Florence Hudson. I'm Executive Director for the Northeast Big Data Innovation Hub at Columbia University, and I want to thank you for having me present at the UC Santa Barbara Center for Responsible Machine Learning Summit on AI and COVID-19. I'm going to be talking today about the COVID Information Commons. The COVID Information Commons serves as an open resource to explore NSF-funded research addressing the COVID-19 pandemic. The COVID Information Commons is funded by the U.S. National Science Foundation Convergence Accelerator Program under Award 202-8999. The COVID Information Commons increases accessibility of information regarding NSF COVID Rapid Research Awards. It facilitates knowledge sharing and collaboration across COVID research efforts and serves as a resource for researchers, students, and decision makers from academia, government, not-for-profit, and industry sectors to leverage research efforts and findings and accelerate research to mitigate the societal impact of the COVID-19 pandemic. It organizes relevant information in multiple ways, for example, by research topic, institution, and geography, which I'll show you, and it will provide links to PI and research team data and present project information in ways relevant and user-friendly for users in academia, industry, government, and nonprofit sectors. It will also incorporate a coronavirus-related information from other NSF research projects, which it already does to some extent, which I'll show you, and more over time. If you would like to provide any feedback on what we do, please feel free to go to the website at covidinfocommons.net. We've been deploying the COVID Information Commons in a phased approach. We received the award in May of 2020, and we launched the Minimal Viable Product, or MVP, in July of 2020 in our Phase 1. Phase 1 has provided a web portal to search for US NSF COVID Rapid Awards, which are Rapid Response Program Awards. It includes two search mechanisms and tools. One is the customized NSF simple search for COVID Rapid Awards by NSF Directorate. All 8 NSF directorates represented, and I'll show you that. It also provides an advanced COVID Research Explorer with machine learning generated maps, which is very cool, and provides different facets of search into the award database. It provides powerful querying and visualization. You can search keywords, topic, award type, institution, all sorts of parameters, and drill down by award to get all the information you need. In Phase 2, which we're deploying now in steps, we are linking to demo videos, researcher videos, research funding opportunities, global data sets, groups and guides, and events. We're also providing additional collaboration capabilities through monthly PI Lightning Talk webinars and a Slack channel. You can see all of those things I've already discussed have been checked off. They're done. In October 2020, as we complete Phase 2, we're adding PI-provided links to NSF COVID Rapid Award-related information and collaboration opportunities. Phase 3, which will be post-award, which is TBD, how we're going to do it, when we're going to do it, and what it's going to be. But some of our thoughts are to search for other pertinent award information, enhance researcher collaboration, and other ideas that you may bring forward as potential users. The COVID Information Commons, which we call the KIC, is brought to you by the Big Data Innovation Hubs. There are 4 NSF-funded Big Data Innovation Hubs around the country. I lead the Northeast Hub in the Northeast, centered at Columbia University, but supporting those 9 states in the Northeast, as you can see. The South Big Data Hub Executive Director is Renata Rawlings-Goss. The West Big Data Hub Executive Director is Meredith Lee. And the Midwest Big Data Hub Executive Director is John McMullen. And we all work as a team on delivering the COVID Information Commons and supporting our researchers. So when you go to the website, you'll see beyond the links that we're going to show you on how to search the award database that we've provided a number of webinar videos to really humanize the site. We have a user tutorial that teaches you step-by-step how to use the tools. There's a launch and demo video, which had our first 2 PI Lightning talks. And then we're having ongoing monthly COVID InfoCommons community webinars with PI Lightning talks. We had one in September with 8 PIs, you can see here with some of their team. And we were delighted toward the end of the webinar, one of the researchers who presented, one of the PIs, Nora Garza at Laredo College in Texas, said, "Your site and the ability to come together is marvelous. I thank you especially for thinking about this and bringing us together. People will be able to use your site as a proper, safe, true information source." We were delighted to hear that because that's exactly our goal. So please use it. We also have on the website a Meet the Researchers tab. And there you can see their research lightning talks. We've actually broken them out so you can see them by PI, by researcher, so you can learn more about their specific research and collaborate with them. We also have information that we've received from a number of the researchers in the Northeast. We've been doing interviews, 5 questions with COVID researchers. We asked them to tell us what's their research about, why did they choose this research, what are their goals with it, what might the solution provide, are there collaboration opportunities, multidisciplinary, multi-sector. So there are other opportunities like this that you can use to learn more about the research and the researchers and begin collaboration. Also on the website, we provide global resources that a lot of people have been sending us because we have this website. We have global research funding opportunities, US and international, global data sets from 6 of the 7 continents, North America, South America, Europe, Asia, Australasia, and Africa. And there are links to all of these open data sets. And then groups, guides, and references, organizations, and networks. We also have an events tab, so you can see our next event will be the October 16th Research Lightning Round webinar. So please join us. You can register, add it to your calendar, and you can also see past events and review those. And you can also join the Slack channel. Our September webinar, as you can see, had 8 different researchers from doing 8 different pieces of research funded as eagers and rapids. So there are some other beside rapid awards in the database. And you can see they're from different states: University of Texas at Arlington, Princeton University in New Jersey, University of California, Embry-Riddle in Florida, University of Chicago, Laredo in Texas, and they're from various NSF directorates and divisions. So we can see NSF engineering is represented, both civil, mechanical, and manufacturing innovation, as well as chemical, biological, environmental, and transport systems. SISE, or Computer Information Science Engineering, is represented in a number of ways. Education, human resources as well, and there are other directorates and divisions as well. In October, we're going to have 8 more PIs presenting, and you can see they're funded by also the Social, Behavioral, and Economic Sciences Directorate, the Biological Sciences Directorate, as well as Engineering and SISE, and some of the others, and Office of the Director, and from various states and institutions. So this is a really wonderful collaboration opportunity. You can learn a lot about the research. The COVID Information Commons project team consists of our PI, Jeanette Wing, who you will hear from later today at the UCSB event. She'll be presenting on Trustworthy AI. Jeanette is our principal investigator for the COVID InfoCommons, as well as the director for the Data Science Institute at Columbia University. You can see here the 4 Big Data Innovation Hub executive directors. On Florence, I lead the Northeast Hub, Meredith Lee leads the West Hub, John McMillan leads the Midwest Hub, and Renata Rawlings-Goss leads the South Hub. Katie Nam is our operations manager in the Northeast Hub. Helen is our junior at Columbia University, who's done a wonderful job helping us with the website. And then we have CUIT, Columbia University IT, and Columbia University Libraries helping us to create, support, and host the website. So let's look at some of the opportunities you have to leverage these different tools to get into the award database. So first we have these icons to find NSF COVID Rapid Grants by Directorate: Biological, Engineering, Behavioral and Economic Sciences, Social, Behavioral and Economic Sciences, all these different directorates. So you can click on any of these and see the NSF COVID Rapid Awards that have been funded by that directorate. Let's look at Office of the Director. This one is handy because I know ours is in there. So here you would get to this page, and if you clicked on Office of the Director, and these are all the awards, NSF COVID Rapids, that have been funded through that directorate. You can click on the COVID InfoCommons to learn more. And you would get the abstract, all the information about the PI, the program officer, the email for the PI, the university or institution, and a lot of information, all the publicly available information regarding the award. The other tool we have on the website is the COVID Research Explorer ML Maps, or machine learning supported maps. If you click on that, you get this really cool interface into the award database. You can see there are 723 NSF COVID Rapid Awards at this time in the database, and they give you this topographical map. You can see what some of the patterns are across the focus areas for these awards. Social distancing, not surprising, pathogens, cases, patterns, knowledge, academic and learning, devices, detection, particles, protein, very interesting. So this gives you a view of what are the focus areas of what's going on, what's missing, and you can scroll in and you can dig in and see a little bit more. Very interesting view. Then this is my favorite view, but I'm a finite element modeler by training, an aerospace engineer. So this is a tree map, and it clusters these awards in different categories. Here you can see the 723 awards, clustered in a number of ways. And on any of these, you can click on the award and find out whose award is it, what's the title, what's the award number, the institution, how much money they received, the PI, and the PI email address. All customizable through the field section. So let's say you're looking at this and you say, well, I really want to look by state and I really want to see the institution names. So you go in and you can use your settings and change it around. And then you say, well, which ones are in California? So you click on one of the California institutions that received an award, and then all of the California awards light up. Very interesting. Here I clicked on one. You can see it's a rapid at the Sonoma State University, their award number, the amount of money, the PI, and then here we have the program officer name too. Very interesting. Let's say I really just want to look at the California awards. So then you can go into the query and you can change it. And you can say, and state, California. And these are all the awards, 77, a little more than 10%. 77 of the awards have been awarded to California institutions. Here's one, the Scripps Research Institute. Then let's say you're looking at this by institution and you say, but I want to see who the PIs are. Maybe I know some of these people. So then you go into the settings and you change it and you say, label these by PI. So then when you toggle, you can see here we had USC. Oh, Dominique Duncan is one of the awardees. Where else is USC? Oh, look at that, Daniel Bennett. Very interesting. And you can do this and find the PIs as well as the institutions. Then let's say that you want to say, well, I really want to look at a specific topical area, machine learning, the topic of our meeting today. So then you can go into the query and say, and machine and learning, and then see there are 73 of these awards, these 723, that actually talk about machine learning. Monitoring aspects, social distancing, science, very interesting. So some of the domains that they're using machine learning for in the COVID research. Then let's say that you want to look at the tree map. Here we have the topographical map. Now I want to look at the detailed level again. Let me look at the universities, the institutions. Once again, let me dive a little deeper and look in California. That's where we are today. So we say end state California and machine and learning. And there are 13 awards related to machine learning of the NSF COVID Rapids in the state of California. So here I'm looking by institution and I click, oh, UCSB, what a coincidence. And then I can change it to PI again. Oh, here are all the PIs, very interesting. And you can customize all these views with this fields button. You decide if you want to see the division and directorate, show it or not from NSF. Do you want to see the abstract? How much of it do you want to see? You want to see the PI name or not, their email address, and you can customize all this, which is really, really handy. So that's a quick overview of what we provide in the COVID Info Commons. We really hope you can take advantage of it. And part of what's important to us in the big data world and for the COVID Info Commons is making sure we're abiding by FAIR principles, that data is findable, accessible, interoperable, and reusable. So we abide by these. You can find all NSF Rapid Awards related to COVID easily in context with the COVID Info Commons, very accessible, public award information, all these facets of it. It's interoperable in that researchers can collaborate. You can download the data and use it elsewhere, and maybe we can do something more about that in the future. And it's reusable. You can extract it, share topical maps, awards, spreadsheets, all of that. And there's more we can do. We'll continue to try. So for our next steps, I would say use the COVID Info Commons. Join the Slack channel, register for the webinars. Next one's October 16th with 8 more PI Lightning Talks. Sign up for the KIC community to get invited to these events, and then collaborate with the researchers. Our next presentation on the COVID Info Commons is at the Academic Data Science Alliance Leadership Summit, October 13th. and email us any input or questions at info@covidinfocommons.net. It's been a real pleasure. I wish we were in person, but we're not, but at least we could still share information. Everyone be safe and well, and thank you for having me.
Hi, everyone. I'm Luca Foschini, co-founder and chief data scientist of Evidation Health. Evidation is a company that runs studies, research studies, large, decentralized, that have a digital component and go across therapeutic areas. Here you can see COVID, cognitive impairment, cancer, atrial fibrillation. You can look up more at evidation.com/research. But the common denominator of all these studies is really that they contain, they collect PGHD, person-generated health data, which in the pictorial representation you see here on the left is all data generated by smartwatches and smartphone and other wearable devices, commercial wearable devices even, that can tell us something about cognition in this particular case on the left-hand side. And on the right-hand side, you have other, even more futuristic example of how biometric data might be collected by smart clothing and smart homes and all sorts of smart devices that we'll have around us. But we should not forget that PGHD, person-generated health data, is not just biometrics. It's actually any piece of data that is generated or mediated by an individual and measures something about their health. So that also includes patient-reported outcomes, symptoms, and also really the more traditional medical data, such as electronic health records and insurance claims that nowadays you can have on your phone, and as an individual, you can even authorize out to your physician or a principal investigator of a study, like you would do with your Fitbit data. So it becomes almost natural to ask ourselves, can PGHD, person-generated health data, tell us anything about COVID that we don't know already, thanks to other data? And on mainstream news, I'm sure you've seen some of those articles that ask the question, can your blank wearable device tell us something about COVID? This article specifically covers a story of myself that in early March, I felt like I had a little bit of cough and something that felt like flu. And then I saw that my Apple Watch was reporting a huge spike in resting heart rate, more than 10 beats per minute from 50 baseline that I have to more than 61. So given the fact we know that resting heart rate changes in resting heart rate are a reflection of autonomic response that could be happening for many reasons, but one of those is infections, for your body fighting an infection. We have seen already, this is on the left-hand side research from us for a couple of years ago, that resting heart rate collected from Fitbit devices specifically jumps around days of influenza symptoms onset. And on the right-hand side, you see a more recent work that takes those jumps in resting heart rate, those anomalies, aggregates that at state level and shows that the fraction of anomalous resting heart rate, people with resting heart rate, really closely matches the ILI, influenza-like illness reported cases by CDC in that region. So you would expect the wearables can tell us something about infectious disease and COVID specifically. So we tried to test this hypothesis. We ran a study. This is the meta-archive preprint, and we're now going through peer review. And we wanted to really understand whether wearable devices can tell us something about physiological changes that might be associated with COVID. And also we wanted to characterize COVID in real life settings before you go to the hospital. So we took a participatory flu surveillance study that we run on a platform called Achievement. It's a consumer-facing app with 4 million users in the US. It looks like this. Anyone can download it. You can connect your Fitbit and other wearable devices to it, and you also get the opportunity to join research studies. One of these studies is, again, it used to be a participatory flu surveillance study that every week will ask you about flu symptoms. But as soon as the pandemic hit, we expanded it to also include COVID-related symptoms. So every week I will ask you whether you have symptoms, and if you say yes, then you're brought up to a follow-up questionnaire that asks more information about the severity, the duration, and the care-seeking behavior. So for the purpose of this presentation, I'm going to focus on 3 cohorts, cohorts of 230 actually COVID-19 cases that reported being tested positive for COVID. We're going to compare symptoms and wearable device signals with 2, let's say, control cohorts of flu patients. 426 flu patients at the same time of COVID, called non-COVID flu, and 6,200 flu patients pre-COVID, before the pandemic. We're using 2 different control groups to try to rule out temporal effect, to try to actually take into account temporal effect coming from lockdown measures. So from a symptom reporting perspective, we see that COVID, which is reported in teal, tend to persist longer than flu in a variety of symptoms. Specifically here, fatigue is highlighted. This was data that was first looked at in May when long haulers, long COVID, now you see every day on the news, wasn't really well understood as a phenomenon. But you do see that if you, in this particular case, we're plotting the percentage of a cohort. Again, teal is COVID and dark blue is flu. Over time, where 0 is the day of symptom onset, you can see that fatigue has a more prolonged footprint, and so I have other symptoms. Switching gears and going to wearable device data, if you aggregate steps and you somehow compute an estimate of what the person would have walked had they not been ill, then the change with respect to that estimate, change with respect to the baseline you expect, is somehow a measure of the burden of the illness and mobility, a measure of lost step. And so we see that for flu, that the burden goes quickly to 0 as the infection resolved. But for COVID, even if the data sample is small here, it doesn't. And again, we didn't know about long COVID back then, but now that could be actually one of the possible explanations, people that are experiencing symptoms for weeks and months after the illness starts. So finally, to get to the resting heart rate, we started talking about at the beginning here, we're reporting the percentage of cohorts of each of the 3 cohorts that are reporting anomalous resting heart rate, where anomaly is defined as more than 1 standard deviation away from the individual baseline that is being computed over 28 days before a specific day. You can see here that we're computing anomaly at different thresholds, not only 1 standard deviation, but also 0.5 in more shaded color. But if you look at the solid dark red, you see jumps in percentage of the cohort that reporting anomalous results right around symptom onset for COVID. But you see so also for flu, not so much the flu contemporaneous to COVID, but the flu before COVID also does exhibit some of that behavior. So resting heart rate seems to be has some sensitivity, but definitely doesn't seem to be a specific signal only to COVID. So what are the applications? What can we use this data for is the obvious question. It doesn't seem to have a diagnostic level sensitivity or specificity. So can we still do something with it? And the hypothesis that yes, there are 2 applications come to mind. The first one is the one pictorially represented here on the left-hand side, an early warning system that can trigger early isolation of individuals when there is a suspect of an infection going on. We know that the infectivity is the highest at the beginning of the symptoms, actually 1 day before, if you have symptoms, because a lot of people don't. But let's assume we focus on the one that do. If you're able to tell someone to self-isolate while they wait for a confirmatory test, which these days can be sent at home in less than 24 hours, and you get results almost right away, then the person can stay, the confirmatory test turns out to be negative, they can go back to their life. But if they're positive, they have actually saved themselves from spreading the disease to other at the time of the highest effectiveness. So on the right-hand side, there are different scenarios that shows that with high frequency, even if low sensitivity tests, you can still significantly flatten the curves under some assumptions. And what the sensitivity and specificity are for different devices in different settings are being now surfaced and published by different groups. And you can check out results from Whoop and Fitbit and others at the bottom of the slides. Another obvious application comes from aggregating the data over a geographic area. So on the left-hand side, you see a screenshot from the Delphi blog. Ryan has talked earlier about that. Aggregating self-reported symptoms at a county level matches very well the case count for COVID for different counties. We at Evidation see the same things when we aggregate at the state level. We don't have so much data in self-report specifically, but definitely self-reports does match case count at state level. It becomes the same idea becomes even more interesting if you could overlay wearable device anomaly on top of self-reports. So the right-hand side plot here comes from a paper that utilizes very many different streams of data, including smart thermometers, for example, to get better estimates of hotspots. And they could include squarely data coming from wearable as well. So to conclude where we started, the resting heart rate jump that I saw, and I thought it was COVID, I couldn't get tested at the time. There wasn't testing available in Santa Barbara, but I get tested later for serological testing. It turns out it was not COVID. So resting heart rate definitely it might be sensitive, but it's definitely non-specific. So what do we need to learn? What do we need to understand to turn these insights into evidence and eventually even into applications? I bucket the next steps or the problems that needs to be resolved into three buckets. The first one is about validity. We need to better understand specificity of these systems, not only against healthy control, but also against other infectious disease that are not as problematic, like flu. We need to really understand sensitivity in terms also on asymptomatics and pre-symptomatics patients. And this can only be done if you have labels in your study that come from viral load tests. And we're running this kind of study right now, sponsored by BARDA. And finally, you need to understand performance in these models really in true perspective settings. And we have a methodological paper coming out soon that shows that true perspective testing done right might actually show lower performance, significantly lower performance than retrospective IID testing. Second, we need to realize that this data comes from populations that are not representative most of the time because they're biased towards digital access. In case of wearable, even more so, they are biased towards owning a wearable. So any model built in that needs to be understood in limitation and potentially reweighted if we want to use it for a larger use case. For those that are doing supervised training, the labels that they collect in the ground truth on the testing is also extremely biased because test results might not be understood by a participant what kind of test they got, and also tests are not administered at random. Actually, the way they are administered varies with time and different policies in different states. Finally, and most importantly, if we ever get to a deployed application, specifically individual early warning system case, we need to keep top of mind justice, which is who can benefit from this. We know that the data doesn't come from everyone, but even more so, we don't want to keep anyone from a possible intervention that can benefit their health. We need to understand privacy implication, true or perceived. What data do we need to give up, or do we feel we're giving up to enable this application? And finally, most importantly, it's really much more than the math and the sensitivity and specificity of the model itself. Much more important than that for adoption and use and successful effectiveness in real-world setting is the human factor. How is the information displayed to the user? how fast is the confirmatory test coming, what is the logistic involved, and how is the communication end-to-end understood, and how can the application finally be effectively trusted. That is really the key for adoption and making a meaningful impact. Thank you.
Hi, everyone. My name is John O'Donovan. I'm really happy to be here. Just want to say thanks to William Wang for the invite. Really appreciate it. Today, I'm going to talk about AI and telehealth and the research and innovation work that we're doing at Teladoc Health. So before I start my talk, I just want to kind of show you where I am. I'm here at our Goleta campus in the Innovation Center. And this is a demo center where demo center formerly InTouch Health, which shows examples of all of our medical devices that are used to allow remote physicians beam in to clinical situations where their expertise is needed, but they can't physically be present. And we have a software called Provider Access Software, which allows the providers to use cell phones or laptops to access these devices all over the world. So we work in neonatology. We work a lot in stroke and behavioral health and several other areas as well. So I got about 15 minutes, so I'm going to get moving with this talk. So I'm going to just give a quick overview of the research and work that we're doing in AI here at Teladoc. First, a little background about the company. So many of you might be familiar with InTouch Health. InTouch and UCSB have strong connections. The founder of InTouch Health, Yulin Wang, graduated from UCSB, degree in engineering. And there's many connections, other people, former UCSB people that are here, including myself. I actually was a co-director of Forai's lab in computer science department for many years with Matthew Turk and Tobias Hollerer. I still technically have an appointment in computer science, so that's yet another connection. So back in July this year, InTouch was merged with or acquired by Teladoc Health, which is a much larger telehealth company. Prior to that, InTouch was private. So right now, the Teladoc platform, it's doing over 10 million consults per year. So it's quite a lot. And it spans lots of service areas like general medical, behavioral health, dermatology, and so on. It's about 2,000 employees, maybe a little more, and it serves over 130 countries. So at InTouch, I led the AI team. So we had a great team of engineers, and this is the small AI team, relatively small AI team. And these are the engineers that were responsible for researching and building many of the tools and demos that I'll quickly show you in this talk. What's exciting for us and our team is we've actually got the larger task of leading AI at this point for the larger telehealth network, which is potentially, after an upcoming merger, is potentially a telehealth entity with an almost $40 billion market capitalization. So it's a very exciting prospect for our team. So before I get into demos and so on, I'll give just a little background on virtual care. So the original challenge in virtual care was, to be able to create that connectivity, that remote connectivity between a patient and a provider. Advances in cellular data, networks, devices has progressed immensely, and that problem is largely solved at this point. The next challenge is to be able to look at these connected networks of doctors and patients and really start to ask questions about what's going on. And then the third step is, okay, now we know what's going on. Can we model it? Can we understand it? And can we use it to predict the future or to improve the present? And there's lots of interesting kind of research and practical questions along that whole spectrum. AI in healthcare is probably one of the biggest topics in the world at the moment. It's huge, and there's many sectors to it. And I just want to bring a little focus just to mention that we're interested here in the interaction between the patient and the physician. So let me put it this way with this graphic, right? If in a traditional kind of brick and mortar type consult where you go in and you sit with the doctor, there's definitely a lot of things the doctor can get that maybe wouldn't be there in a remote session. But if you think about it the other way, there's many things that many insights that we can provide by putting AI in this layer in between the physician and the patient. Simple examples. A doctor can't see if a patient is sweating, usually, can't see if a patient temperature changes, can't see the patient's pulse or respiration, or even there are neurologists and psychiatrists and so on are all trained to look for small nuances, things like lip quivers, eyebrow movements, these facial action kind of changes that can have medically relevant meaning. Sometimes these things can even change over time, or even in a consult, or even over a course of weeks or multiple consults. Sometimes those things are very hard to detect, and AI can be used to detect those in an automatic way and provide providers with better insight. And that can all contribute to better outcomes for the patient and better patient care. So, at the highest level, our mission is really to improve quality of care by creating these insights both before a consult, during the consult in real time, and afterwards as well, to provide data analytics and insights and follow-up mechanisms and so on. So to really improve that whole member journey. I have a background in recommender systems. I come from AI background and lots of work with kind of recommenders and intelligent interfaces for those. And that's not different here at Teladoc either. We're super interested in making recommendations to patients, for physicians they can interact with, and all sorts of other relevant recommendations. We're also interested in applying AI in novel ways to improve operational capabilities at our company. Obviously, it's a large company. We've got thousands of employees, and there's lots of efficiencies and things that can be optimized by leveraging models over the different data that we have. And obviously, large companies have lots of data. So, okay, quickly to show where we're working. We've worked on many projects. I can only give you a really high level, quick feel for some of them in this talk, but three broad areas. The provider augmentation, that's the window I just showed you. So, augmenting, giving that provider X-ray vision in a sense. Patient experience, that's understanding their flow through the telehealth framework and system, and making sure that that's an enjoyable or as enjoyable as possible user experience and straightforward, and where the next step is always clear. And then the operational context as well. Okay, so before I show demos and so on, I'm going to give a quick vision for the future. And so what you're looking at is it's a little bit of a busy graph, but I'm going to try to explain it quickly from left to right here. What you see on the left, the data flow goes from left to right. On the left, it's multimodal data that comes from, let's say, heterogeneous data sources in EHR records, patient notes, and so on. Data during a consult in the form of audio, video, and any other multimodal data. This could include sensor data, any kind of biometric data from sensors on phones and other devices. And the idea is we want to take this multimodal data and apply what we're going to call low-level AI. So these are simple reusable AI components like face detectors, pose detectors, speech to text evaluators, and so on. And then we want to apply what we're going to call like domain-specific or medically relevant AI models, which are maybe not even AI in the typical sense of a deep learned inference model. It would be more of could be a simple geometry or a simple set of rules that could be applied over the low-level AI. But the idea with this layer is that we end up with something that can really predict something and assess and monitor for something that's medically relevant, and preferably do that in a passive way that's not really invasive. So we're interested in building up this suite of AI sensors or detectors, and then leveraging the massive, powerful reasoning that we have from the expert doctors that are in our network that are looking at these real situations and applying labels to those. So, for example, a doctor comes in, has a dialogue with a patient, and then gives a diagnosis. And if we can collect and amass that data set of these different AI sensors that are detecting medically relevant signals, and we can couple them with these labels that the experts are providing, we can have something extremely powerful that's potentially capable of even doing these kind of diagnostics and so on in a more automated fashion. This is not something we've done. This is just a vision for the future, but it's something I'm very excited about. Okay, so I'm gonna just check my time here, just one moment. So yeah, I'm gonna speed up a little bit here. So I'm gonna give you a quick flavor for a couple of different projects we've been working on. So the first one up here on the left is kind of a thermal camera. So InTouch have developed we've installed thermal cameras in some of our medical devices that enable us to do temperature differentials. We've worked on projects that allow the remote users to see who's in the hospital or ER that they're beaming into. This one is really critical because in high acuity situations like stroke, when a doctor beams in and spends 5 minutes talking to the different people in the room to find out who they are, while the patient is sitting there potentially losing millions of brain cells, that's not a good situation. And we did notice that this happened in some of the consults that we analyzed. And the proposal here is to use simple face detection and recognition technology, and to apply a workflow behind that allows a doctor to come in, push a button, and see who's there and what the roles are, so they can say, Nurse Jane, apply this, and or give the treatment and so on, without the who's who at the beginning. I'll talk a little bit in my conclusion about why, some interesting stuff that happened around this project and some insights and lessons learned. We're also interested in doing non-contact vital signs monitoring. We can do this on our endpoints on the in-hospital devices that we have here. I'm also going to show you a demo of it on a mobile platform in a little bit. We're also, we've done some work on AI sensors. So thinking back to that slide I just showed with the vision for AI sensors, the one on the bottom left here is a sensor for stroke, which detects first of all, detects a set of features in the face. And then once the face is detected, computes a bunch of different geometry over the face using the rigid fulcrum of the nose, the rigid bridge of the nose as a fulcrum. And what it does is over time, it detects increases in facial asymmetry, which can be very relevant for stroke. For example, if a patient is, let's say the patient gets seen for 8 minutes by a doctor for a consult and then not again for another hour, potentially an algorithm like this could look at the patient, monitor for an increase in that asymmetry or hemiparesis, and that could be an indicator that that patient really needs to be seen again by the doctor. Okay, we've also done a bunch of work for in behavioral health space as well, detecting things that are relevant potentially in behavioral health. I'll get to that in a bit. Okay, there's a marketing video that I'm going to skip. Okay, I'll go straight into this non-contact vitals detection for mobile devices. And this is pretty recent work and designed fully for the Teledoc platform, the mobile-to-mobile context.
Good morning. Good morning. I am a doctor, probably not the kind you want to get medical advice from, but let's go through this anyway. So here we are on a cell phone to cell phone platform with two different apps, one for a provider, for me, one for the patient, and that's you. And today we're just going to do a quick test of the cool technology that the team has put together. And here we're going to show a demo of assessing remote vitals in a non-contact way. And what I want to show you is this top line up here that says pulse. This is reading your pulse from the area of your detected face, and it's looking for small changes in pixel values and mapping those to a real pulse value. The respiration value below that shows the number of breaths per minute, and that's taken from the box on the lower area from that bounding box that shows the chest. So what I'm going to ask you to do, John, just as a kind of a metric here, is to lift up your hand and show us that smartwatch that I know you're wearing because we prepared it beforehand. And we're going to just check and see, how accurate this is. And if you can just hold it there for a minute, I want to just mention quickly that this will obfuscate the chest area. It will stop the respiration from working. But just for the purpose of this demo, we can see that the pulse is tracking around 54, 55. Which shows A, that our technology is extremely accurate, and B, that you've been out running a lot. So congratulations.
There you go.
Awesome. So I think we can leave our demo there. I appreciate your time. And
Okay, let me move on quickly from there. I only have a minute or so left. So I want to mention quickly that, we're not just interested in the real-time stuff. I know this is a seminar about COVID-19, so I just want to mention, I'm not allowed to say too much about this data, but I want to just mention that Teladoc is collaborating with the CDC. We are collecting data at scale and analyzing these signals in the data, and that we do have preliminary work. And I'll say preliminary, it's not fully vetted and published yet, but there are indicators in this that we are able to see trending of terms like cough, fever, sore throat, and so on, that correlate geographically and so on, and can do that up to 3 days prior to us seeing confirmed cases by public health departments. So we really want to continue to work with public health departments and with the CDC to ensure that this data and this insight can get used to basically help society by allowing public health departments to take appropriate action based on the insights provided here. Okay, we're also interested in things like AI for maintaining clinical quality. We're interested in AI for patient triage and improving the patient member experience in the system. So to wrap up, I want to just mention really quickly, good AI is more than just AI, right? It's not just the model. It's not just training the model. We need the whole pipeline that goes along with that model, and that includes if data collection or whatever other aspects are needed, and usually a lot of logical rules that are applied over the output of a classifier. And I think that's a really important point. Reality and the lab are not always well aligned. So, with that name tag project, we didn't know that COVID was going to come, and that all of a sudden everybody would be wearing PPE, and then that faces would be completely obscured. We were actually ready to go test this in a clinical trial at Yale University right before that hit. And of course, we had to change our plans. And, no matter how much you plan, stuff can happen that causes problems. And I think to survive in a kind of industry, you kind of need to be dynamic, and you need to be able to adapt your plans to meet reality. But I think to conclude, I think data here is the differentiator. Teladoc is special in that it has a consult data that nobody else has. No one else has this kind of data at scale that represents, interactions between patients and providers. And I'm excited about using that data to change the world for the better. So if anyone is interested in working on our team, please get in touch with me. My name and contact should come on the next slide. Cheers.
Thank you, Florence, Luca, and John, for very interesting talks and very, very related, but also very different work. I'm going to just ask questions as they come in over Zoom chat in the order they come in, and we'll go from there. All right. I see a question. I believe this is for Luca, and talks about, it says, a question from Ivan says, athletes without any apparent symptoms seem to still be at a risk of heart damage under heavy exertion. Have you looked at heart rate changes during physical activity, not at rest, to identify that risk?
Hi, everyone. That's a great question. We have not looked at that. We have some in-progress work to look specifically at that signal. To give a little bit more context, yes, it's known that COVID might cause myocarditis, which are inflammation of the heart, and they have been found through MRIs in athletes that had no or mild symptoms. So it seems to be, a thing out there. It's unclear if it's related with changes in performance and heart rate, and we're definitely looking into that, but we haven't done any work on that yet.
How about heart rate variability instead of just resting heart rate? And that is also quite telling of a lot of different things over time.
Absolutely. So heart rate variability is this signal that's been seen almost like as the holy grail of many things, both in the medical and health science domain, the sports science domains. It is the variability between any two consecutive beats. So very counterintuitively, actually, if your beats are very regular, it means that you are not doing well. It means that you are, homeostatic response to stress is not kicking in as fast as it should due to all the changes that we have when we talk and when we move. So higher variability is good. Lower variability means that you might have health conditions or stress, and it's used actually by athletes to modulate overtraining. I can tell you that specifically for the detection of COVID, HRV, heart rate variability, is not one of the signals that pops up as the most important one. Really, changes in resting heart rate seems to be the most important one for us. And to a lower extent, respiration rate and SpO2, oxygen saturation, seem also to be informative there. But really, resting heart rate is the key, at least for us.
Okay. Speaking of resting heart rate, right, that can change due to many other factors as well, comorbidities that people might have, maybe thyroid or any other concerns. So I'm assuming you're taking resting heart rate with, as you pointed out, with other factors, self-reporting and some other parameters that people are talking about, right?
Absolutely, that's a fundamental point. Resting heart rate changes are very non-specific, like they say in the medical world. Like they may occur because of many reasons, even different viral infections that are not COVID. So it's really important to understand systems that are based on wearable triggers as, early warning system that needs some sort of confirmation right after. So, part of it can be done by the machine learning and trying to understand the context, as you said. But even in that case, you never get to a level of specificity that can tell you, that can grant a next action without having a confirmation, direct confirmation from the user.
Got it. Thank you. I have a question coming in for John from Christine. Says, has there been work done on over-the-counter versus prescription pharmacy data as predictor data points to surveillance data as another layer? And this was in reference, I believe, to your work with CDC.
Yeah, it's a good question, and I'm afraid I don't have the answer to that one. So I actually had one of our chief medical officers prepare that slide for me, and so the only information I have about the collection was what was on that slide. I can tell you that the data that I referred to when I talked about the preliminary predictions and 3 days ahead, that's based on just dialogue that happens between doctor and the patient, and terms that are uttered in our forms and also in the dialogue as well. I don't think that is tracking over-the-counter information.
Cool, thank you. There's another question for you, John, from Shipeng. Says, has Teladoc started to consider to put multimodality data all together to do analysis and assist doctors, like medical records, time series, images, etc.?
Hi, Zifeng, nice to hear from you. Great question, and absolutely. So this is something that we're it's kind of a holy grail for us as well. So obviously, there's a lot of insight that's can be spread across heterogeneous data sets, and there are some pieces of insight that we can glean from an image of a person's face, from sentiment, from expression. That could be coupled with things like speech to text. Let's say, for example, in a behavioral health session, if let's say a doctor asks a question about a patient's, let's say, I don't know, personal behavior or whatever, and then there's a sentiment response shown in the face. That kind of scenario spans multiple modalities, but can reveal things that are extremely relevant from a medical perspective and a diagnostic perspective. And even the probabilities of detecting those things can be adjusted and reflected based on like past history that might come from an EHR and so on. So to answer that, yes, absolutely, that's something we're really interested in.
All right, awesome, thank you. I have a question for Florence. The CIC, I should say, website and everything else, providing information to all that data is super cool, especially through the visualizations and allowing you to drill down to figure out who's working on what and what grants are happening. I was wondering if there are any plans to sort of have a related thread on potential related grants to apply for, sort of like a one-stop, and everything is related to COVID in this case, as opposed, that could be both, industry, NSF, NIH, any other agency, but sort of in that same place, which could be potentially searched by topic of interest or something like that?
That's a really good question. So the research funding opportunities that are listed as well as the data sets are really just a list now with links. But we were actually just having a discussion today talking about what could the future of the COVID information commons be. So we're starting to dream and think about how we could create search mechanisms that either could provide recommendations, based on your current research, based on your topical area, based on your data, that might be interesting. Finding data, humans finding projects, humans finding research opportunities and funding opportunities. So we're starting to think about how we can make this a more technologically integrated capability for the COVID information commons. And we're even envisioning, can we actually do some type of search actually into the data sets that we find, the open data sets, so you can find, data that might be interesting for your research as an example, and find the humans. And then the funding opportunities could be similar. My guess is that there may be some new funding opportunities, because a number of them have expired already, because this was like, oh my gosh, we have a problem, Houston, everybody on board. And so some of them have expired. The COVID rapids are basically all spent, at NSF in the US, and some of the others have expired as well. Some of them are still open, some of the industry ones in particular, because they have an ongoing budget, I guess. But I'm wondering if there are going to be some new ones in the new year, if we're still having this problem, which we could be. So I think there'll be further opportunities as well. So we're envisioning now what we can do in the next stage. So thank you for bringing that idea up. I really like it.
Yeah, no, thanks for answering. And I guess by the same token, I was wondering if there's a way of, as John was talking about recommender systems, and thinking about if PIA is working on, let's say, machine learning, but looking at social distancing, and PIB is doing the same thing, but they don't really know each other or about each other's work. I wonder if there's a way to sort of figure out who's working on something that's related to you, who might be a potential collaborator, and to work on bigger things, past COVID rapid.
Yeah, currently we're doing that through human intervention, kind of like, I'm like the Rosetta Stone right now. So, I heard from a University of Florida mechanical and aerospace engineering PI, and that's my field actually. And he was looking at, aspiration and, 6 feet really work. No, as a lot of us know. And so I said, oh, do you know Howard Stone at Princeton? We just had him present. And he said, oh yeah, actually we are collaborating, but that's a great idea. So what we're looking for is a system that can do that. It doesn't have to be me because I happen to know the humans, or we do, PI lightning talks and they find each other. So we are looking at how the humans can find each other as well. And I think, what we were talking about is it could be based on their research. It could be the title or the abstract of their award. It could be based on their data. It could be based on their role. So in this situation, he said, I'd like to do this. And I looked, I'm like, oh, he's a mechanical engineering and aerospace engineering professor. Oh, so is Howard. Oh, I wonder if they're working on something similar. So there are a number of facets you can look at regarding the humans, perhaps even, looking at their ORCID ID, and looking at some of their past publications. Because what we're doing this month in October of 2020 is to add the PI information from about 170 of the COVID rapid PIs have sent us survey information on, collaboration opportunities, keywords they use for what they're doing. It might not be exactly the award keywords, it might be different how they see what they're doing. And also their ORCID ID and things like that. And then links to their websites with their research results or models or data or whatever. So we're starting to think about how we can crawl through this data at the data and the metadata level potentially. And there are also some networks of the HPC, the COVID-19 HPC consortium in the US, where there are a number of NSF and DOE and a number of facilities that exceed facilities that are working together, and there are data sets there as well. So we're starting to envision what the future could be. So those are really good questions.
All right, wonderful, thank you. I have one last question for John. I'm wondering what you found in your interaction maybe with medical practitioners when it comes to the level of trust related to AI, I guess black box systems potentially telling the doctor what possible diagnosis could be, and maybe challenging the doctor's own personal diagnosis at that point? Like, how is that relationship? Because I can imagine it being fairly complex.
Great question. Great question. So there's, I could spend an hour answering this question. There's a few different perspectives. Obviously, nobody likes AI to be a black box, right? There's huge push across the world to make AI more transparent, more understandable, more accountable, and that's happening from the legal perspective. It's happening from GDPR perspectives, and it's nowhere more intense, I think, than in the medical field. But I think doctors are even an even more special case. The last thing that we want to do is build a tool that pushes the doctor out of the way and says, hey, no, we can do your job for you, right? These are tools that we're very cautious to and careful about presenting these tools as advice givers and assistants. These are not tools that we're aiming to be like diagnostic tools to in any way replace a doctor. These are only maybe flagging mechanisms, reminders, cues that help a doctor perform their task better. And we're really careful to not say that the doctor is being replaced, because in general that's not well received from our experience.
All right, thank you, John.
Very good point. If I can make a complimentary comment to that, and then if I may ask a question of my colleagues, Nisha?
Sure.
That would be great. So John, I totally agree. I worked on the Watson strategy at IBM, actually before he won Jeopardy. And then when we were developing the healthcare life sciences strategy, and it's exactly the same ideas that what we're trying to do is to augment some context and some information for the doctor to actually help them make the correct diagnosis and decision, or the best diagnosis and decision. Even though doctors are brilliant, there's clinical research going on every day all around the planet, and they don't have time to read all that stuff. And it might be in different languages. And, is there more that you can provide that they can't get to themselves, even though they can obviously ingest it and digest it very well? So I totally agree. Now I have a different question for both of you, Luca and John. And you both kind of touched on something else that we're doing in this space regarding AI and connected healthcare. And I'd like your thoughts on this. So I actually lead a global working group for IEEE and Underwriters Laboratories. It's a joint working group to create a standard around clinical Internet of Things, data and device interoperability, with something we call TIPS, which stands for Trust, Identity, Privacy, Protection, Safety, and Security. And it's a framework we've been building with IEEE for about 4 years. And now we have over 240 people from 22 countries and 6 continents in this working group, because we all know all this stuff is hackable. And we know that trust and identity at the device level, we don't have a device registry. We don't have a way to do that yet. And then AI and ML on top of that, what type of things should it be looking for to protect the humans? How do we, make sure we're providing privacy, security, and safety? So have you all thought about this and, standards we can put in place, or would you like to participate in this working group? So I'm wondering what your thoughts are on this.
Happy to go first.
Well, I obviously. Oh, so go ahead, Luca. You go first.
Oh, yeah. I mean, let's go alphabetic. Definitely, that's very interesting in participating. We've been working at Aviation and with other company in the health tech space in trying to understand this problem of lacking standards when it comes to PGHD, person-generated health data. I think that the problem of lacking standards is really across the board, is the device itself, as you're saying, and the security perspective, which I think one great link for that will be the DIME Society, the Digital Medicine Society has a whole chapter devoted to, even in collaboration with white hat hackers at the Biohacking Village in DEF CON. Really, they do competition on trying to hack Internet of Things for medical purposes. So on the device side, definitely there is a need for that, but also on the data quality and data verification side. Like once you collect the data, how do you store it? How do you transmit it? What are the checks that you want to do? It is, you know, Wild West, because, you know, the devices are being developed on a daily basis. So happy to help with that. I know that there are a few different efforts, even within IEEE. There are some subsets that are working on health specifically, and NIST is doing something in that direction. It would be nice to have, you know, a higher level coordination. And so if there's something that you're interested in, I'm happy to reach out after this talk and you know, see how to make that happen.
Excellent, thanks. I just chatted you my email. And anyone else that's interested in this too, I actually spoke at DEF CON this year in the Biohacking Village, and I talked exactly about this. So, and I was there last year. So this is a very important area, and we're working with a lot of people. We spoke about it at the Engineering and Medicine and Biology Conference for IEEE this past summer as well, with people from all over the planet. So, well, thank you, Lucas. And John, you don't have to answer, but I think it's related to what you were talking about. I was looking at your picture of all the different pieces working together and thinking, yep, sensor data. Okay, yeah, there we are. You know, so I don't know if you have any thoughts.
Well, just that, you know, PHI, personal health information data at scale carries you know, just a huge amount of risk. And, you know, it's such sensitive data, it needs to be protected at all costs. And, you know, at Teladoc, we're super careful to make sure all of our data is correctly anonymized. We're careful to make sure that it's encrypted at rest, that it's encrypted at scale, that access is provisioned properly by committee, that monitoring for compliance and access is done on a regular basis. And for our machine learning capabilities, we're interested in things like federated learning, which is the process of bringing a model to the data with tools like PySift and things like that, that really leave the data where it is and bring a trained model and take the model away. So we're highly conscious of the importance of data privacy, and we keep things as tightly wrapped down as possible.
Yeah, I think federated learning is very important. And also federated identity management is what I'm thinking about at the device level. We do that at the human level, but I think at the device level will be interesting as well. And that would actually play into your scenarios, I think.
Right. And yeah, please add me to the email as well. I'd be interested in the working group too.
Okay, great. I will, I'll ping it to you.
Awesome, everybody. Thank you very much for the wonderful talks and the conversation, and to the audience for participating, and to our presenters for responding. I think we're going to move on to our next session, which is the afternoon keynote. And everybody stick around for the keynote. Thanks very much.
Thank you.
Thank you.
Thanks, everyone.
Hello, my name is Ryan Tibshirani. I'm a faculty member at Carnegie Mellon University in statistics and machine learning. I'm also an Amazon scholar. I'm one of the two leads of the Delphi group, which is a research group at Carnegie Mellon focused on epidemic tracking and forecasting. And I'm here to talk about Delphi's COVIDcast project, which is, not surprisingly, a project about tracking and forecasting the COVID-19 pandemic. So I figured I'd start by telling you a bit about Delphi pre-pandemic. It's been around since 2012. Roni Rosenfeld and myself, Roni's a colleague of mine in machine learning at Carnegie Mellon, founded the group in 2012 to develop the theory and practice of epidemic forecasting and its role in decision-making. From 2012, up through the time pre-pandemic, our focus was on seasonal flu in the United States. And at the kind of center of our efforts were flu forecasting systems that we developed over the years. And we submitted those forecasting systems to the annual CDC flu forecasting challenges starting in 2013. And in many of the years, our systems earned the top spot as being the most accurate forecaster. And in 2019, we were awarded one of the CDC's 2 centers of excellence for flu forecasting. So fast forward from then till now, actually around maybe February of 2020, our group went from 7 or 8 members to over 40. And it was all in response to the COVID-19 pandemic, to support the COVID-19 response that is in the United States. We've been super lucky to add many smart folks, not only from Carnegie Mellon, but also from Stanford, UC Davis, USC, and most recently from Google. And it's with the addition of all these new smart folks and also the hardworking, core 7 or 8 that've been around all along that we've been able to even attempt to build what I'm calling an ecosystem for pandemic tracking and forecasting, which I'll share with you just in a second. So one focus point of ours which has always been a focus even back to our days working on flu, but really now has become a really central point of our effort, has been the focus on securing important data streams. And the idea behind that was that, we looked at the pandemic forecasting problem, and the first thing we thought was, this is such a hard problem that our best weapon is a diversity of data sources. So that led us to start developing what we call the COVIDcast ecosystem. Of course, ecosystem is a very ambitious term, but let me lay it out for you in terms of the scope of our project. So at the bottom floor is what I call the data floor. And this is supported by unique partnerships with many players in tech and healthcare. And so I've just named 5 here that we're working with more than just these 5, but these 5 have been huge supporters so far: Facebook, Google, Change Healthcare, Quidel, and SafeGraph. The next layer up is a database of what we call COVID indicators, which are basically statistical signals that we produce based on the data sources that come in through the data floor with partnerships in tech and healthcare. And each COVID indicator is a real-time, geographically detailed, so think county level indicator of pandemic activity across the US. And it points to, maybe a different picture of the pandemic, or it gets out a different slice of the pandemic, I should say, than what typical public health reporting metrics like confirmed cases and deaths provide. Our database also includes all common public data sources like confirmed cases and deaths, as made aggregated and available by, for example, groups like Johns Hopkins and USA Facts. And importantly, our database also records all previous data revisions, which is a point I'll return to a little bit later in the talk. The next level up from the database is our access point that we provide to the public. And this is our public API, which we call the COVIDcast API. It serves new indicators daily. And we've written client packages in R and Python for those who are familiar with those languages for easier data access and utilities like plotting, processing, computing correlations, etc. So the next layer up has a couple different focuses in different directions. In one direction, we've built some interactive maps and graphics on top of our API to provide more kind of point and click visualizations and data fetching tools for end users that are, let's say, less programmatically inclined. And in a different direction, we've been pursuing all sorts of modeling work building on top of our indicators and our API, with the focus currently being short-term forecasting, nowcasting, and hotspot detection. And the latest, let's say, arm of our effort, which I wanted to highlight, is that we've begun to make a lot of our modeling tools public, in the sense that we're actually releasing packages that reflect the whole process that we went through at arriving at the models that we produce. And so one thing that we're quite proud of is a package for forecast evaluation that we just made public very recently, which provides an extensive suite of tools for evaluating forecasters, for modelers who are also pursuing forecast development. So in this talk, I'm going to just focus on a couple aspects of what I'm calling this COVIDcast ecosystem. I, of course, can't cover all of it. I'm going to focus on a few of our data sources, giving some examples. I'm going to talk about the API and how you can access the data yourself, and then give some basic demos of what you can do, or what is provided by one of our data sources, which is a massive survey that we're running in partnership with Facebook. So unfortunately, I have to skip our quote unquote real modeling work, and that'll have to be found in another talk. So the last thing I wanted to highlight was actually all of the examples in this talk can be reproduced with the code that's provided in the talk. So this whole talk should be reproducible. And the link for the talk itself is found in the footer, but I'll also make that available to all the summit attendees in case it's too small to read that link. Right, so to lay out the data sources we have in the COVIDcast API, I like to think about them, our group likes to think about them categorized according to what's called the severity pyramid. So this is building off of a classical concept in epidemiology. We just add maybe a bit more layers of detail on top of maybe the more traditional view of the severity pyramid. So these are different categories that reflect different, let's say, levels of burden and different degrees of lead time versus lag time at pandemic activity. And let's just start at the top. So at the very top of the severity pyramid are deaths. So these would be deaths that are due to infection, in this case, COVID infection. Below that would be ICU admissions or ventilator usage, other let's say aspects of critical hospitalizations. Below that would be hospital admissions. Below that would be confirmed cases. Below that would be doctor's visits. So these are people attending the doctor with, let's say, COVID symptoms, but who have not potentially yet been tested. Below that would be symptomatic infections in the population. Below that would be all infections in the population, so including asymptomatic and symptomatic individuals together. And below that, relevant aspects of a population's behavior. So things like mobility patterns, mask wearing, social distancing, etc. So you might imagine that for some of these data sources, for some of these categories, some of these rungs on the severity pyramid, if you're interested in getting data sources that reflected them, it could be more straightforward. So for example, thanks to heroic efforts by groups like that at JHU and USA Facts, we have very nice public access points to the public health reporting data on confirmed cases and confirmed deaths. But for other ones, it would be much more difficult because they'd be based on, maybe say the data sources that would reflect that rung would be not, typically reported through public health reporting channels, but available in something like medical claims. So that would be referring to outpatient visits, for example. And then, of course, getting good data on symptomatic individuals in the population or a population's behavior is just very difficult. So backing up a bit, what is this used for? I imagine actually that a lot of the listeners of this talk already have ideas for what this could be used for. So I'm going to be pretty brief about this. But if you want to see more details, you can just return to this slide and take a look at it in more detail. Same with the severity pyramid. I went over it quickly. You could just look at that in more detail, of course, by referring back to the slides. But the basic idea, I guess, is that to understand one rung in the severity pyramid, it typically helps to understand the rungs that come below it. So if I want to understand, for example, deaths, whether it's through forecasting or for some other purpose, it's helpful to understand ICU admissions and hospitalizations. And if I wanted to understand confirmed case counts, it's helpful to understand outpatient visits and, let's say, symptomatic infections in the population. So there are a variety of specific use cases, but that's the general idea. So let's jump to the indicators that we provide in the COVIDcast API. So I've written them here, I've attached them to different categories or different rungs of the severity pyramid, and I've labeled them in two colors. In blue are the data sources that are publicly available elsewhere that we just mirror in our API for convenience. So for example, the JHU CSSE confirmed cases and deaths, and same with USA Facts. The ones in red you can think of as more or less COVIDcast original indicators. So these would be indicators or data sources that you can't find anywhere else and that are made available through partnerships that we have with different entities in tech and healthcare. And I'll just highlight kind of two categories. I can't, like I said, go through everything systematically just because I wanted to save some time to talk about some of the interesting use cases. But I'll just highlight the data sources based on, or the indicators based on medical claims, which we have access to based on partnership with different national health systems, and also the data signals or the indicators that we have based on a massive survey that we're running through Facebook. So these are all available through our COVIDcast API, which is updated daily. Most all of them are available at the county level. And if you're curious about the technical details behind how we compute our indicators based off the data sources that we have, you can take a look at our signal documentation site. And also, I'll just reiterate that we have R and Python packages available that make data access easy. So if and when you find these slides, everything in purple are links. So you can just click through to get to the relevant pieces of information. So now I'm going to walk through very quickly, just as real basic demos, examples of some indicators that we have in our API and how you could access it, and just to try to show you that it's actually quite easy with the setup that we've provided. So suppose I wanted to know how many people have died from COVID-19 per day in my state, which is Pennsylvania, since March 1st. So here's the code for that. If you use our COVIDcast R package, it's just 3 lines. One line is to load the package. The other line is to fetch the data from the API. So I have to point out the data source, which is, in this case, USA Facts, and the signal, which is the 7-day trailing average of incident deaths. And I want to pull data for Pennsylvania over this period. And then the third line is just, calling it a simple plot utility that we provide. And that's what you get. Marching down the severity pyramid, I'm just going to go through kind of one or two examples per rung. Let's look at hospitalizations. Suppose I wanted to know what percentage of daily hospital admissions are due to COVID-19 in my state, but also in New York and Texas. So this is an indicator that is one of those COVID-CAST original indicators that I referred to. So it's not available in typical public health reporting records, but it's something that we produce based on aggregated medical claims. And it's just, again, 2 lines of code, one to fetch the data, the other to plot. And here's what it looks like for New York in red, Pennsylvania in green, and Texas in blue. So we can start to see interesting differences in both the timing and the intensity of these different time series. Another example is confirmed case counts. So here is a 7-day trailing average of incident. This is actually case rates, so counts per 100,000 population. And it's at the county level. I think this is, again, USA Facts. Yep. And it's, we provide heat map plotting functionality in addition to time series. So you can just very quickly get a global or national picture of the current case incidents. Same thing, but for cumulative case rates, just a couple lines of code. And here's an indicator that you can derive based on what's in the API. So here we just threshold at 2%, asking where is the current COVID-19 cumulative case rate greater than 2%, and plotting that in pink, everything else in blue. So you can see that a good part of the South is highlighted here. Okay, continuing down, here's a snapshot of doctor's visits. So this is comparing a few cities in terms of the percentage of doctor's visits due to COVID-like illness. Again, one of these COVID-CAST original indicators that's based on aggregated medical claims that we provide. So if I remember properly, this is, Pittsburgh, New York, San Antonio, Miami. So it looks like New York is in green. This would be San Antonio in purple, Miami in red. So you can kind of clearly see Miami's second wave, so to speak, with respect to this indicator being more significant than its first. And this is Pittsburgh in blue. And the last one, I think this is the last example at least, is something at this symptom rung, or the kind of symptomatic infection rung of the severity pyramid. So this is just looking at my county, which is Allegheny County, and one of my friends' counties. This is Fulton County in Georgia, comparing them in terms of COVID symptoms, another COVID-CAST original indicator. This is an indicator that we compute based off of a massive survey we're running through Facebook. So we ask people whether they know somebody in their local community that has COVID symptoms, and we compute an indicator based off of these survey responses. And this is what we're plotting: the percentage of people who know somebody locally in their community with COVID symptoms. This is Fulton, and this is Allegheny. All right, so that was a whirlwind, but hopefully it gave you, a snapshot of what's available and how to access it. And let me dive a little bit deeper into the API and the. I'm just going to talk about the R package, but actually the Python package has all the same functionality. So everything I say for the R package is also available in the Python package. I think for this part, I'm also going to go pretty fast so that I can spend a bit more time in the third part of the talk on a couple of the indicators that we compute based on the survey we're running through Facebook. So the COVID-CAST API has the following specification format. You can construct a query string at this base URL, and you have to specify the following parameters in the query string, and it returns data in JSON format. So here are the parameters: data source and signal, which is the name of the data source, like, for example, Facebook survey or doctor visits, and then the signal, which is a particular indicator or signal that is computed based on this data source. So, for example, smoothed CLI, which CLI stands for COVID-like illness, or smooth adjusted CLI would be two signals that we provide with respect to the doctor visits data source. Time type and geotype. Time type specifies whether you want data at the weekly or daily resolution, and geotype is whether it's at a county level. HRR, which stands for hospital referral region. MSA, which stands for metropolitan statistical area or state. Time values is the range of time over which you want data, and geo value it specifies the locations over which you want data, which depends on the geotype. So here's just a very simple example of a query string that allows us to get data for one signal, for one day, for one location. The details aren't important. I just wanted to show you that this is how you could construct it and this is what you get back, which is a data in JSON form. More commonly, at least for people like me, I would say the R or the Python package would be a more convenient way to access the API, which I'll get to in just a second. And all the examples you saw actually previously were all accessed to the R package. If you want full details on the API beyond this, we have a pretty detailed documentation site, and there you'll also find details on all the different data sources and signals, how you can get access to the metadata, and the geographic coding that we use. So one thing I wanted to highlight was that the API actually also provides access to all data revisions, not just the most current issue of each data signal. So by default, you get the most recent data for each time value that you specify, but we also allow you to access all previous versions through different optional parameters. And let me just point out maybe one of them, which I think is the most intuitive, which is the as of parameter. So by default, when you query the API, you query it as of today, the day that you're calling it, but you can explicitly specify a previous as of date, and you can think of it as, what if I rewinded the clock and actually fetched data from the API, so I pinged the API, as of a previous date. So I could look back and I could say, if I were to have pinged the API as of a week ago, what would have the data for confirmed cases looked like on any particular day? And it would be different because of revisions, if to what I would have gotten if I queried the API as of today. So to dive a little bit deeper into that point, the reason that this is so important is that many data sources that are critical to understanding the current pandemic, but more generally would be critical to understanding a seasonal epidemic like influenza or otherwise, many of these data sources are actually subject to revisions. So some examples are that case and death counts are frequently corrected or adjusted by public health authorities. Medical claims data can sometimes take weeks or even months to be submitted or processed, so it can be backfilled substantially. Testing and lab data can also be backlogged for a variety of reasons, and so on. So one really important point to anybody pursuing modelers is that you have to pay attention to all this in order to do rigorous and truly, let's say, retrospective model evaluation. So suppose I was building a forecaster and I wanted to do retrospective testing. Then I'd have to, let's suppose I wanted to rewind the clock and say, let me consider all data available, up to September 1st. I'll build a forecast available and I'll test it out of sample on what comes next after September 1st. So when I go to do this retrospective exercise, if I ping the API today, the data that I would have gotten for September 1st would have been subject to potentially many revisions, and it would not have been what's available as of September 1st. So I really have to call the API and ask for data that was available as of September 1st, and then it would be truly unstable, and it would be it would actually reflect the more realistic picture, which is going forward. Anytime we make a forecast, we do so based on the data that we have as of the forecast date. So the COVIDcast R package, it has different utilities that it provides. Maybe the first and foremost is that it allows you to query the API with the same specification structure that I told you previously, but it just makes it easier because a lot of the parameters have default values that would be reasonable for most applications, and it provides you with full support for data revisions. There's also a bunch of plotting tools and signal processing tools. There's much more to come, and if you have an idea for something that you want to see, go ahead and file an issue, or even better, contribute a pull request on our GitHub repo, which is public, and it's linked here. So let me give you an example that just illustrates what I described previously with forecasting, why it's important to pay attention to revisions with respect to the forecasting problem by looking at one particular indicator, which is based on doctor's visits. And again, we're looking at here the percentage of doctor's visits due to COVID-like illness, and I'm looking at California in the last 2 weeks of August. So suppose I wanted to build a forecaster which took this doctor's visit signal and maybe other data sources in addition, and it predicted, let's say, case counts to come in the ensuing weeks. And this is a natural thing to try, of course, because we think, before people go and get confirmed, and they go get confirmed via a test for COVID, they may have been visiting the doctor with COVID symptoms. So I say, okay, I have my forecast model that I've settled on. Let me do some retrospective testing. I want to see, if I only had the data available before September 1st, how would my forecasts have done after September 1st? So if I go and I ping the API, let's say as of the end of September, this is what I see for data prior to September 1st. But that's not really what's relevant for this model evaluation. What's relevant is actually what data would have looked like as of September 1st. And if I ping the API as of September 1st, I get a very different picture. Okay, so there's two important aspects to point out. The first is that this red curve, which is the doctor's visit signal as of September 1st, it's actually lagged 3 days. So the 3 most recent available data points are not even available because that's just the lag in this data signal. And the second point is that there's a huge difference in what the signal is somehow showing or telling, right? This is systematically upward biased from the eventual kind of finalized signal after many revisions have been issued. And it looks like what's happening is that, as let's say claims get submitted late or are processed late, they get put into the denominator typically in this percentage, right? So we basically see a lower and lower fraction of doctor's visits due to COVID-like illness as time passes for the last 2 weeks of August in California. Okay, and this is what it looks like if we, ping the API as of intermediate dates. So there's still quite a bit of variability, and we have to pay attention to this if we're going to be doing rigorous forecast development. We can't just look at finalized data, as of the time we're doing development. And this is what the API provides for all data sources, not just for the data sources that actually themselves log revisions. We on our side log revisions for everything that we collect. Okay, so I've left a little bit of time, hopefully, to dive into symptom surveys. This is just one of our data sources that I wanted to tell you about, a couple of the indicators we compute and why we think that they're useful, and maybe encourage you to go check it out yourself along with our other signals that we have in our API. So since April, we've been running a survey through a recruitment partnership with Facebook that gets about 75,000 people per day as respondents, and over 10 million since it began in April. And the survey is US-based, and it asked questions about COVID symptoms, both common and rare, both that the individual is facing or is experiencing that is being experienced by a member of their household, questions about COVID testing, access to tests, questions about mental health, how the pandemic is affecting their mental health, their social contacts and behavior, mask wearing, demographics, and so on. And there's a parallel international effort that's run by the University of Maryland, which asks pretty much the same questions, but does so globally. And at this point, it reaches over 100 countries and 55 languages, and it's gotten 20 million responses so far. Bit more info on the survey. It's actually implemented through Qualtrics. We implemented the survey through Qualtrics, and it's run and managed directly by our team at Carnegie Mellon. Facebook never sees any of the individual survey responses. It just advertises the survey on Facebook to a user, and the person clicks out of Facebook to take the survey on our Qualtrics site. It's designed to take about 10 minutes. It's about 35 questions. Originally, we selected a core set of questions because we thought they'd be relevant to forecasting and nowcasting. But as I alluded to, in the list in the last slide, this list of questions grew to support, a broader kind of scope of research in public health, trying to understand how the pandemic is affecting people, not just, improving our ability to forecast or nowcast. The respondents provide their zip code, so all the aggregates that we compute based on the survey, we can make available at the county level. And as far as we know, this is the largest non-census research survey that's ever conducted. So let me tell you about 2 indicators that we compute. I mean, as you can tell, there's many questions, so there's many indicators that, we could compute, and actually many more became available recently. I just want to talk about 2 indicators that we compute that are relevant to nowcasting and forecasting, which is our original intention with the survey. And that has to do with what we call COVID-like illness, which is a condition defined by symptoms, not COVID diagnosis through a test, just symptoms. And it's defined as a fever along with a cough, shortness of breath, or difficulty breathing. So we ask people to report on their own symptoms and also on the symptoms of people in their community, and we compute 2 indicators. One is that the percentage, we call percent CLI, percentage of people in a given county on a given day that are experiencing COVID-like illness. And the other we call percentage CLI in community. It's the percentage of people who know somebody in their local community with COVID-like illness. So you could ask, why do we bother asking this proxy question? Why don't we just measure percent CLI directly? And the answer is that it empirically actually tends to perform quite well, and it looks to be a more stable and in many ways more meaningful signal than percent CLI, which for nowcasting and forecasting, that is, which surprised us. And here's a couple of plots to try to convince you of that. So this is a correlation between the percent CLI in community and the percent CLI indicators that we compute at the county level with confirmed COVID case rates at the county level over time. So this is at each time we take correlations between the COVID case rates across all the counties and the percent CLI and community indicators across all the counties, and we plot them. And you can see that the red curve, which is the correlations for the community signal, are generally much higher, and actually they reach, even in absolute sense, they reach quite a high number. They reach above 0.8 for a period between July and August. And this is sliced a different way, sliced by county, taking the time series, the correlations between two time series curves, for one for the signal and one for the COVID case rates. We see the same story. I'm going to skip this just because I want to try to get to a small forecasting demo, but we put a bunch of data streams in our API, a bunch of new indicators in our API really recently that hit at different questions in the survey, so you can check that out if you're interested. So here's a more specific look at how the percent CLI and community indicator could be useful for something like nowcasting or forecasting. So here I'm looking at Miami-Dade County between June 1st and July 15th, and I'm comparing the CLI and community signal to the COVID counts in that county. And the percent CLI and community signal is shown in red. The COVID case count curve is shown in blue. And we see two things for these two time series curves for Miami. The first is that it's just reassuring that they have a similar trend. That is, more people report that they see or they know somebody with COVID symptoms in Miami when we actually know that case counts are rising in Miami. It's just it's a reassuring trend. The second is actually more exciting, and you have to look more carefully to see it. And it's that if you take a look at the inflection points in these two curves, so this is the point at which, let's say, the uptick in that signal begins, or percent CLI in community actually starts to rise steeply. That occurs about 6 days before the uptick in COVID cases. So before people actually start, or the tests eventually, let's say, report that COVID cases are increasing, people are reporting that they're seeing more and more individuals in their community with COVID symptoms. So you could say that's just one county. Let me see what it looks like in others. And so here I pulled the top 20 counties in terms of the rise in case counts between June 1st and July 15th, and plotted again the CLI and community signal along with confirmed case counts. And overall, the trend is very similar. We see many instances in which the CLI and community signal is an early indicator, and in some cases actually by quite a large lead, even a week or more, over confirmed case counts. So one last plot to formalize this just a bit, and I see I'm over time, so apologies to you all, and thanks for staying a couple minutes over. I'm just going to walk through a very simple forecasting demo. Basically, I'm going to deploy two forecasting models that are very simple autoregressive models that try to forecast incident cases D days ahead based on either lagged cases alone, and that's the first model, so lagged previous cases alone, or based on both lagged cases and based on the lagged values of the CLI and community indicator. So to predict case rates next week, I'll use case rates this week, and case rates the week before, and case rates the week before, or I'll use that, and in addition, I'll use the CLI and community signal today, and that signal of the last week and the week before. Those are the two models we're comparing. And for each forecast date, we train the models dynamically just on the most recent 14 days worth of data to try to account for non-stationarity. So here's the results from forecasts that were made from early May to late August. And if you want to get details, you can take a look at this blog post I've linked. And I'm plotting the forecast error from these two models over this time period and over all the counties over which we made forecasts as a function of the number of days ahead at which the forecast was made, so 5 through 20. And we can see two things. The first is that the model that uses the community signal, the CLI and community signal, just generally outperforms the model that uses lagged cases only, which is encouraging. But if you want to get a sense for whether these differences are meaningful, you can actually look at it a different way. You can look at it by horizontal slice, and you can try to interpret what these magnitudes of differences buy you. So for example, if I look at the error of 7-day ahead forecasts, if I trained that forecaster based on lagged cases alone, that looks to be just about as accurate as 12-day ahead forecasts if I had trained the model on lagged cases and the lagged survey signal. All right, so to wrap up, and again, I'm sorry I'm over time. The COVIDcast ecosystem has many parts. I've walked you through just a few of those parts. Really, we didn't build this for ourselves to use alone. We certainly can't, find answers to all the important questions alone as a group. We built this to be useful and so that others could build on it as well. So it'll take an entire community to find all the answers to the important questions. We really encourage you to join ours. Thank you for listening, for staying over, and thanks to the whole Delphi team, many of our partners, and especially the CDC for the longstanding relationship and support we have with them. So thank you.
All right. Hello, everybody. My name is Yushan Wang. I'm a professor in the computer science department in UCSB. I'm also the co-director of the Center for Responsible Machine Learning. So I'm going to be our host for the rest of this afternoon, handling all the Q&A sessions. First of all, thank you very much, Professor Ryan Tishrani, for this wonderful keynote. So I'd like to open the Q&A session with a simple question to start, and then other panelists and attendants, please key in your questions in the chat, and I'll go down the list accordingly. So let me start. So this is a wonderful initiative that provides a lot of new indicators that I have never heard of before on the COVID-19 situation, with very fine geographic and temporal differences. So I'm wondering, like, how many of these are produced as raw data, and how many of them have been cleaned and produced by some kind of statistical computation, and what's the corresponding implication of that?
Thanks, Yushan. Can everyone hear me okay? Can you guys hear me?
Yes.
Yeah. First, I should proudly announce that Yushan was my student, and so I'm very proud to have him now, turning the table on me and asking me questions in front of everybody. So the question was about the indicators. So there's a huge variety in terms of how much computation each one entails. I would say no indicators that of the ones that I called Delphi originals that are listed in red on the slide with all the indicators are like raw data. They all involve some amount of computation and some amount of cleaning. And in some cases, like there's a huge amount of cleaning and I guess I wouldn't say a huge amount of computation, but typically a huge amount of cleaning that goes into it. It just varies. So for example, for some of the testing signals we produce, like we produce a test positivity ratio that comes from Quidel data, that involves a really simple aggregation and then just dividing, for a particular geographic unit, total number of positive tests divided by total number of tests. So it's pretty simple. For other indicators, like even for the survey signals, actually, there's adjusting for survey bias that we do along the way in terms of, we try to reweight for the fact that we aren't actually surveying from the US population directly. And then for things like the medical claims indicators, they're even more complex. We try to adjust for things like weekday and weekend effects. So less people go to the doctor on weekends. So we try to actually estimate through kind of like a simple log linear model what the weekend effect would look like and remove it. And all of the indicators pretty much involve some kind of smoothing, right? So some kind of simple to less simple temporal smoothing.
Yeah, thank you very much. So William Wang has a question. What's the difference between COVID-19 forecasting and nowcasting comparing to other time series prediction problems, let's say in the financial domain?
That's a great question. So yeah, I don't know, like, let's say time series forecasting in finance, like as a true developer of models in that area. So it's kind of hard for me to comment about, that area in particular, but I guess I can say that there's maybe 2 reasons that make COVID forecasting really hard, or maybe 3. And I think only one of them is probably really common in other areas. So the first is non-stationarity. There's a huge amount of non-stationarity in terms of how it looks like, let's say, the targets of interests are either related to their own past values. So like in even autoregressive models, there's a huge amount of non-stationarity. And there's also a huge amount of temporal variability. So what it means to, and I kind of hinted this in one of my examples. If you look at, for example, how much lead time some of our survey signals give you in terms of predicting COVID cases, it really varies a lot by county. So in some counties, you may actually see it giving you like a week's lead time, and others, it looks like maybe there's no lead time at all. So there's a huge amount of variability temporally and spatially. That may be common in other forecasting problems. In fact, I would not be surprised if that was common in finance, although the spatial aspect doesn't really make sense in some sense in finance. The other two reasons why forecasting is so hard, if I'm allowed to like really simplify, are data quality as maybe the most important reason why forecasting is so hard, but I just listed it second in this list. And the third is the expectation from decision makers and from the public that we should be and can be making forecasts well into the future. So in finance, we don't make forecasts years out, or at least we don't trust those forecasts. We make short-term forecasts typically. And that's how epidemic forecasting really should be, in the sense that, we don't really know what's going to happen, let's say in January at this point with COVID, let's say with the COVID pandemic. But that doesn't stop people in public health and also in the news and the general public seeking these kind of forecasts. And so then incentivizes modelers to try to make them. And that's like extraordinarily difficult. I mean, at that point, you're actually asking questions that border more on, can you predict people's behavior rather than can you predict, or the way like certain, let's say, pivotal events will play out that would affect the pandemic. Behavior is one of them. And not even really talking about statistical modeling. So yeah, that's just the way I see it, basically, in terms of those three aspects.
Awesome. There's a very interesting question from Ambush. About the COVID-like illnesses symptoms in community predictor. So Ambush asks, is it success based on the fact that these nodes have a high degree and also likely to get the illness first, and therefore can serve as an early warning?
Yeah, I think you're asking, is the success of the, like, let's say the predictor that measures disease in the community versus the predictor that measures whether or not somebody, I shouldn't say disease, COVID-like illness in the community versus the one that asks somebody about their symptoms individually. I think that's what you're asking. And yeah, it's a very good point that somehow by asking people how many people do you know in your community that have symptoms, you're all of a sudden basically not surveying one person, but maybe 50 or 100 people effectively. You're pooling the sample size because you're asking them to report on people around them. And so for a really sparse parameter, like let's say, symptom prevalence, which still is not going to be super high, like the numbers we see for percentage of people with COVID symptoms in terms of survey results are still around 1 or 2%. They're not very high. So for a sparse parameter like that, if you can hit nodes of high degree, as you're saying, or really maybe like you use a person to pool, basically as a pooling effect, reporting those around them, it tends to be very useful.
Indeed, it's just interesting that if you change your way of asking the question, you suddenly gets better performance and higher quality data. So Luca has a question related to, I guess, non-stationarity. Suppose that there are some tail event that fundamentally changes, like in the near future, where this pandemic is going to go. From your perspective, what are the easy questions and what are the hard questions in the forecasting problems?
Yeah, that's a fantastic question. So maybe I can back up again and just speak up a little bit about what kind of forecasts people are looking for and expect. And there's actually there's two different dimensions. There's short-term and long-term. But there's also what I would call forecasts versus scenario projections, or forecasts versus counterfactual forecasts. And those are often really mixed in terms of what kind of forecasts people are producing, or what their metric is for success isn't made clear all the time in terms of when they're describing their forecasts, but they're really separate. So to answer your question, the easiest type of forecast, which is I think the only one that's tractable, in some sense, is to make short-term forecasts that are not counterfactual. So these are forecasts that are supposed to be actionable by people in public health. So for example, forecasting, let's say 1 to 4 weeks ahead, the number of hospitalizations we expect due to COVID. And if that number exceeds some threshold for what they would be able to handle, then they can, let's say, start with preparedness and planning. Or the number of cases to expect 1 to 4 weeks ahead. And if somehow that would exceed their testing capacity, then they would go and they would all of a sudden, invest in securing more tests. Those are short-term forecasts. Forecasts that are long-term, like what's going to happen 6 months from now, well, that's important for the economy. That's important for all sorts of things. But to me, like you cannot make forecasts without quantifying uncertainty. I think that's just not something that is nearly as useful. And once you start talking about uncertainty quantification, 6 month ahead forecasts are pretty much useless, because my prediction band around whatever's going to happen is going to be so big that it'll include basically all cases. So I think that's a very, very hard problem. Sorry, the very last thing I'll say is just about counterfactuals. Counterfactuals are, you could ask, if people, let's say, started going out more, what would happen? Or if people started wearing masks more, what would happen? So that's a causal question you're asking, which is, again, very, very hard, because it requires controlling for all confounders. And that's very, very interesting to people in public health, but I just will urge caution about, that's a hard problem.
Yeah, thank you so much, Professor Tibshraeni, for the Q&A session and for the great talk. We unfortunately, due to time constraint, we won't be able to get to all the interesting questions in the chat. Ryan, if you'd like to, you may still just answer those questions in the chat directly to the people who ask. So coming up next, we'll have 2 very interesting talks on COVID-19 forecasting from Professor Quanquan Gu from UCLA and our own Professor Xifeng Yan from UCSB.
Thank you for the invitation. It is my great pleasure to have this opportunity to talk about our recent progress on interventional COVID-19 response forecasting. We have built neural network models to forecast COVID-19 hospitalizations and deaths, which has achieved state-of-the-art performance. This work is collaborated with my PhD students, Xiaoyong Jing, Professor Yuxiang Wang, both of them from the computer science department at UCSB. These figures show you the number of daily new confirmed COVID-19 cases per million people in a few countries over time. As we can see that after the initial severe lockdown in April and May, the number of confirmed cases starts to increase again in recent months. So we should be concerned a little bit, and we do not know what will happen in the next months. Fortunately, the situation is not that pessimistic. The number of daily new confirmed COVID-19 deaths per million people has dropped a lot. Although recently we see it increases a little bit, but it's far less than the situation in March and April. And we hope that we can do some kind of forecasting, not only the number of new cases, but also the number of hospitalizations and deaths, which could be very useful for the local community decision makers for the next step decision making. In March, we looked at a figure provided by CNBC, and we see different countries have different lockdown policies, and the number of new cases change dramatically across different countries. And we got an idea, why not using other countries' experience and situations to help us to forecast the situation and the future situation in the United States. So we started this project. Before that, we have zero knowledge in epidemic forecasting. There are many factors that can influence the number of new cases, the number of hospitalizations, and the number of deaths in different regions. There are many factors. For example, demographic factors, age distribution, gender distribution, race distribution, population density, business structures, cultural difference, psychological factors, and interventional policies. These factors can influence the contact ratio among people, the infection ratio among people. And these two ratios, together with the dynamics of diseases, will influence the number of hospitalizations, and in the end, the number of ICU occupants, and the number of deaths in hospitals and communities. And we actually can model all of those factors using time series data, like infection ratio, contact ratio changes over time, the number of hospitalizations, ICU occupants, and deaths change over time. And furthermore, the characteristics of COVID-19 change over time dynamically. And we actually can view the forecasting problem as a time series analysis problem. And we know that time series analysis has been studied extensively in the past decades. The setting is very simple. Give you historical data. Could you help me forecast what will happen in future? Okay, there are a lot of work on it. And classic epidemic models have been applied widely. And you can see those numbers reported by CDC and White House and news media. Many of these numbers are estimates from these classical models. For example, the SIR model can model the spread of disease using differential equation. Today, we are not going to talk about these SIR, SEIR models. If you want to know suffix models, Google Cloud AI recently published a great article called Interpretable Sequence Learning for COVID-19 Forecasting. And it has a lot of discussion about how to model spread of disease. We are going to try another approach, a neural network approach, as we have seen the great success of neural networks in analyzing images and natural language sentences. We feel that it is possible to apply neural network models to analyze time series data. We have achieved initial success in forecasting demands and using convolutional transformers. Transformers are one of the leading neural network models to analyze natural language sentences. It achieves the state-of-the-art accuracies. Here I list 6 models. All of them are kind of neural network models, and they achieve great performance in predicting various kinds of time series data. And our idea is, why not use it in epidemic forecasting? So here is the intuition. And we actually found that the spreading of COVID-19 disease, the spreading rate, is determined by a few common factors, like race, social and cultural interactions among people, and protections taken by people. If you look at different countries and different regions, you will be surprised that their spreading patterns and the trend actually share a lot of similarity, because this is made by the same kind of diseases. So in order to forecast the number of cases in certain region, we actually can refer to other regions where pandemic starts earlier and borrow their numbers and using their numbers to do the forecasting. So this is the basic idea, okay? So there are 2 approaches to achieve this. The first approach is you can try to find similar regions. They share similar factors, like similar demographic factors, similar population density, similar business and social structures, and similar psychological factors, etc. But however, it could be very difficult to find the exact same region, because no region share the exact same factors. So instead, we go to the second approach. Find the regions whose trends look similar, because all of those aforementioned factors have been priced in the time series data. Okay, we don't need to find the 2 regions that share the entire similar time series. We only need to find the small segments that share similar trends, and then we can use these trends to do the forecasting. So this is our basic idea. For example, in July, like many countries, in the United States, Santa Barbara County experienced a new wave of COVID-19 cases. Actually, we are very worried. We were very worried at that time. And we checked the historical data collected from all the world, and we find that Mexico in early June actually shares a similar trend with Santa Barbara. It is amazing, of course, in different scale, but their curve looks very similar. So actually, we can use the number shown in Mexico to forecast the number of COVID-19 cases in Santa Barbara County after June, for example, June 15, and the result is quite good. So let me give you one slide to show the basic idea. We adopt the transformer neural network models, especially the attention mechanism used in the transformer. Suppose we want to forecast the target region, the red region. What we can do is we can take the reported number of cases and compare this number with the reported cases in reference regions and see whether they share some kind of similarity, and give those regions share the highest similarity with the highest weight. And then we can use these numbers to forecast the feature number in the target region, one piece by one piece. And in the end, we are able to build the forecasting for the targeted region without knowing the underlying disease spread models. This is a fully data-driven approach. And we can further add other factors into the model. Age, race, gender, mobility index. As you know that the mobility changes over time. And we can incorporate those index into the model so that the model can perform better. So for the Santa Barbara County, in the time period June 12th to June 22nd, we actually can find the most similar states in the United States that share the similar pattern with the Santa Barbara County. It is North Carolina during March 31st and April 10th. And furthermore, we can drill down and find the most similar counties in North Carolina share the similar pattern with Santa Barbara County. There are 3 counties in North Carolina. I show their curves. As you can see that the blue curves share quite a similarity with the red curves in Santa Barbara. Then actually we can use the green curves to forecast the number of new cases in the Santa Barbara County after June 22nd. So that's the idea. And we got this idea and developed quite complicated neural network models based on transformer architecture. And we start to forecast new hospitalizations and deaths in different states. And we believe that these numbers could be quite useful for the local decision makers. And specifically, we can further go down. If you want me to forecast the hospitalizations and the deaths in local counties, we can do that. Okay. So from the CDC website, we can see they collect various kind of forecasts delivered by different groups. Here we have multiple groups, like from Columbia University, Georgia Tech, IHME, Johns Hopkins University, UCLA, Army Research Center, etc. Okay. Actually, the forecast estimate, the range is quite big. Like they forecast that 1,500 to 1,500 new COVID-19 hospitalizations per day nationwide. Okay, so we run our algorithms, try to do the like 4 weeks forecasting for hospitalizations. And this number here show you the different estimates from different groups. As you can see that our model labeled UCSB actually can perform like quite well, outperform many existing approaches. And note that we do not use any epidemic knowledge. And furthermore, if you want to forecast the hospitalization situations in different states for the next 7 days, our models even performs better. So this is a great result. And we go one step further and try to do the death forecasting for 4 weeks per state. Okay. So again, it seems our models performs quite well in comparison with other models delivered by our peers. So this is great news for us, and we are currently in the process of sending our results to CDC, and hopefully it will be recognized by CDC. So here are a few key points I would like you to take away. It is possible to develop data-driven neural network models to do time series forecasting without knowing anything underlying mechanism. And it actually performed quite well in COVID-19 forecasting. And furthermore, it does not require manual parameter setting and tuning. And this actually is very important. For many SEIR model need parameter setting and tuning. And this will not be available for local communities because it will be tedious to tune those parameters community by community. Using our technology, you just input the historical data available into the model. And if you have the demographic graphic data available, like age distribution, race distribution, you can input them to our model. But if you don't have this data available, our model still works. And we see a neural network-based model work very well for demand forecasting and for this COVID-19 forecasting. So we have some confidence to see its broad application in other forecasting tasks. So this is our takeaway messages. And thank you for giving me this opportunity to introduce our recent progress. Any questions? Thank you.
All right. So thank you for inviting me to speak in this second annual Responsible Machine Learning Summit. Today I'm going to talk about epidemic model guided machine learning for COVID-19 forecast. This is a joint work with my students and collaborators. Since the original outbreak of COVID-19 in the United States, we launched this project using machine learning to combat COVID-19 on March 28, 2020. The goal of this project is to use machine learning techniques to build forecast models to help predict the spread of COVID-19 and enable the decision makers to make more informed decisions, such as allocating the medical resources. If you are interested in our project, you can go to this website. And on our project website, you will find the forecast of daily confirmed cases and deaths at different levels in the United States, such as national level, state level, and county level. You can also find such forecast for other countries in the world. So in this project, the first main task is to forecast the number of confirmed cases and deaths. So on the left side, you can see the number of cases in the United States, where the solid line is the historical data and the dashed line is the projected number of cumulative cases. In addition to the point estimate of these numbers, we also provide a 95% confidence interval, which gives you the upper and the lower bound of the prediction. In addition to the forecast of confirmed cases, we also provide forecast of deaths in the United States. Again, if you look at the figure on the right-hand side, the solid line is the number of historical data and the dashed line is the projection along with its 95% confidence span. In addition to the number of cumulative cases and deaths, we also provide a forecast for the number of daily increased cases and deaths. So here are two examples. On the left-hand side, we provide the number of daily confirmed cases forecast. The solid line is the historical data. We do 7-day average to make it more informative. And the dashed line is the forecast of number of daily increased cases. Again, we provide the 95% confidence interval, which gives you upper and lower bound of the prediction. On the right-hand side, you can see the forecast for the daily deaths. The solid line is the 7-day average of the reported daily deaths in the United States, and the dashed line is the projection, along with its 95% confidence band. For more information and also for the latest forecast in terms of confirmed cases, the deaths, you can go to our project website to find those information. Now the question is, how do we provide this kind of forecast for the confirmed cases and the deaths? In order to achieve this goal, we use the mathematical models, which is called the mathematical epidemic models. There are two classical epidemic models. One is called the SIR model. SIR model divides the population into 3 groups. The first group is called the susceptible group. The second group is called the infectious group. And the last group is called the removed group. So individual can be moved from the susceptible group to the infectious group if he or she get affected by the virus. And then he or she can be further moved to the removed group if he or she recovered from the disease or died from the disease. And the individuals in the susceptible group will be exposed to the virus and can get affected by the individual in the infectious group. So there are 2 parameters in this model. One is beta, which is a contact rate. The other is gamma, which is a recovery rate. So overall, this model can be described as a system of ordinary differential equations. Each of these ordinary equations characterize the time derivative of the SIR, this 3 sequence, which is 3 time series. The second classical epidemic model is called the SER model, which is an improved SER model by adding another additional compartment called the exposed group, which is in between the susceptible group and the infectious group. So this group is introduced to model the so-called incubation period. So when an individual is exposed to a virus, he or she may not immediately get infected. It may take a few days or even more than a week to get affected. And this exposed group can model this incubation period. It will also introduce another parameter called sigma, which is related to the length of the incubation period. And only the individuals in the infectious group will infect those individuals in the susceptible group. The resulting ordinary differential equations will be more complicated because now there are 4 variables in this model SER model. So we need to use 4 ordinary differential equations to characterize the dynamic of these 4 variables. However, neither SIR model or SER model can handle the COVID-19 disease very well because they do not take into account the unreported cases, which is a very, very common case in COVID-19. Because of the limit of testing capacity and also because of the existence of asymptomatic individuals, many people who got affected by COVID-19 may not be tested and therefore not reported and also, of course, not count in the number of confirmed cases. And in order to overcome this limitation, we propose a modified model called the SUER model. SUER model can be seen as a modification of SER model where we add additional compartment corresponding to the unreported cases. So here you can see that for those individuals in the exposed group, they can either be moved into the infectious group if they got tested and confirmed as positive cases, or they can be moved to the unreported group if they don't get tested and reported as confirmed cases. And in order to characterize the fraction of individuals in the exposed group that will be moved into the infectious group, we introduce another parameter called the discovery rate. This mu is the discovery rate. So as you can see, only a mu fraction of the individuals in the exposed group will be moved into the infectious group. And there's another difference between SUER model and SER model. because we assume that the individuals in the exposed group can also infect those people in the susceptible group. So this is consistent with our current observation and studies for COVID-19. Even for asymptomatic individuals, they can infect those healthy people. So the resulting model, we call it the ACU-ER model, can be described by this system of ordinary differential equations. Although there are 4 equations, but it is different from the ODE for ACU-ER model and can handle those unreported cases in the COVID-19 cases. So the resulting question is how to estimate the parameters of the ACU-ER model. And in order to do this, we make use of machine learning. We build a machine learning pipeline. The input of this machine learning pipeline is the data, the historical data, and also the initial estimation of S0 and E0, which correspond to the initial susceptible population and the initial exposed population. So both of them need to be learned. And once we have the data, we can build a model to estimate those model parameters, beta, sigma, mu, and gamma. And when the model is learned, we can use this model to predict the future confirmed cases and deaths. In detail, in order to learn the model parameter, we use ODE solver to unroll the ODE into 4 time series for each given parameter and initialization. Okay, and once we have this 4 time series, then we can define some loss function in terms of log loss, and we can estimate the model parameters by minimizing the following loss minimization in terms of log loss. For the state level and the county level models, we use the data from the New York Times the data repository as training data. And for country level models, we use the Johns Hopkins University data as a training data to train the model for the national level confirmed case and death forecast. And in addition to the forecast of confirmed cases and deaths, we also provide hospitalization forecast. In order to do that, we modify our ACU-ER model by introduce additional compartments. So here are 2 additional compartments. One is called hospitalized, which corresponds to the group of individuals who are hospitalized. The other is called ICU, which contains those people who moved into the ICU after they admitted to the hospital. So from the infectious compartment and the removed compartment, an individual can be directly moved to the removed group, or it will be first moved to the hospitalization or ICU before he or she got moved to the removed group. And because of this additional compartments, there are more parameters we need to learn in order to build up this forecast model. Another question is how to model social distancing or stay at home, this kind of public health measures in our model. The idea is very simple, because in our model, we need to initialize those 4 time series as EIR, and we need to assume the initialization value of S0, E0, I0, and R0. By default, we assume that they add up equal to N, which is the total population number. However, due to the public health measures, only a fraction of the population will be susceptible to the virus to get infected. So we introduce another hyperparameter delta. And this delta reflects the fraction of people that will be susceptible to the disease. So in our modeling, we need to treat delta as a hyperparameter, and we can also learn this delta if we have enough data. Once we build our model, then we can provide the forecast of confirmed cases and deaths. So far, our model has been used by CDC since early May. It is one of the 30 models, or more than 30 models used by CDC, and our model is often the top 3 models, which provide a very accurate and robust forecast for the national level and the state level death forecast. As I mentioned before, we can also provide a hospitalization forecast. And our forecast has been used by CDC among those 8 models for national level and state level hospitalization forecast. And in California, our model has been used by the California Department of Public Health, they built up a tool called the COVID Assessment Tool, or CalCat. CalCat provides nowcast and forecast in terms of the effective number and also deaths and hospitalization in different counties of California. And our model can generate very accurate forecast for these different nowcast and forecast. Finally, let me show some performance comparison between our model and the other models. We compare the prediction of our model with the predictions generated by other models, such as the model built up by Columbia University or the UW or MIT, UT Austin, and many other national labs and individuals. So before the resurgence, our model is often ranked as #1. And after the resurgence, our model is also ranked as the top 2 models among these models. And very recently, our model is also ranked #1 in terms of the national level death forecast. So our model performs consistently among the top and usually ranked #1 at different levels. So here's the takeaway of this talk. So I show you that by bringing academic models and machine learning together, we can provide very accurate and reliable predictions for COVID-19. And our model can predict the confirmed cases, deaths, and hospitalization, and also the effective reproduction number at different levels. All these kind of forecasts can be used to better understand the severity and the spread of the virus. And finally, within our model, we can evaluate those public health measures, such as reopening, social distancing, wearing masks. And this can provide very useful information to those policymakers and the local governors. So I would like to thank you, those collaborators and team members, and also Google Cloud, which support our research. Thank you.
All right. Thank you, Chuan-Chuan Qifeng, for the wonderful talk. That brings us to the state of the art for the epidemiology forecasting for the problem of COVID-19. So now we are entering the question and answering session. So we have time for questions to the speakers. So I'll start, and all the attendants, feel free to post your questions in the chat channel, and I'll post a question to the students on our behalf. Okay, so I'll start. So both talks are, so this is a question that's posed to both speakers. So both talks are about modeling of COVID-19 progressing predictions of the hospitalization, the number of cases, and number of deaths. The two approaches are however, like hugely different. In Qifeng's talk, the approach that like you took is a completely data-driven approach that uses all sort of time series data and trying to generate the most accurate prediction. In Chuan-Chuan's talk, the model comes from the more fundamental approach that deals with partial, like ordinary differential equations, and to model the progress of the COVID-19 cases and so on, and make it more and more fine-grained with the data-dependent components that learns the parameters. So what are the pros and cons of these two different approaches? So apparently both approaches achieve the state of the art and are ranked pretty high on the CDC benchmark. So could you guys also provide some more insight into like what contributed to the success, and whether there are things that the other approach could benefit from your approach?
I would like to say first to say hello to Chuan-Chuan. Actually, we graduated from the same group. It seems we are working on the same problem. Before the talk, I'm not aware that Chuan-Chuan is working on it. Otherwise, I will probably drop UCLA from the comparison sheet. Okay. But I think this is a very good question. That there are the two kinds of methods. One is like fully data-driven. You just use neural network, do not assume any kind of underlying mechanism. On the other hand, if you do understand the disease spreading mechanism, use those existing models with some kind of significant modification, you might achieve better performance if those models can fit the data. The problems we observed is for those COVID-19, we found that not only we have those like disease characteristics, we have many other factors, especially for example, psychology factors. It is very difficult to model this kind of factors in those ordinary equations or differential equations. I just tell you personal experience, right? In the end of June, before the end of June, everything's okay. And when I do the hiking, no one actually wear any mask, okay? But by the end of June, when those numbers spike, I can see that when people do the hiking, many of
Is it just me, or is Xifeng frozen?
Yeah, I think we lost his voice.
Okay, so perhaps Chuan, you can maybe address the question while Xifeng tries to get back online.
Oh, sure, yeah. I think that's a great question. So it's about the black box machine learning model versus white box machine learning model. So deep learning is definitely a very powerful black box machine learning model, and it has become one of the go-to approach when we are trying to do prediction, classification, or different kind of machine learning tasks. So the reason we choose those mathematical academic model instead of deep learning model is we want to make our model more interpretable and also explainable. So during my talk, you can see that there are a few model parameters like contact rate or transmission rate and also recovery rate. And if there's a exposed component, then there's additional parameter called the reciprocal of the incubation period. These parameters are very, very informative in terms of telling for example, the status of the epidemics or the spread of the virus. And in addition, if you want to also provide the nullcast, which refers to the effective reproduction number, or so someone call it instantaneous reproduction number, then we highly rely on these model parameters, because only we know what's the contact rate, what's the, for example, recovery rate, then we are able to calculate the effective reproduction number. So this is the main reason we chose to use those white box machine learning approach instead of the black box machine learning approach. But on the other hand, I also agree with Xifeng that deep learning is so powerful. And when we do COVID-19 forecast, there are many hidden factors which may not be reflected in those numbers, in those historical data. So we want to leverage knowledge from, for example, one country from the other country, or one county to another county. And in this sense, I think maybe deep learning or related machine learning method have the potential to do this kind of domain adaptation or transfer learning, which I believe is a very, very interesting approach. But for our forecast, because we started this forecast at the very beginning of this pandemic, and at that time, there's a very small amount of data. So if you want to train a deep learning model, maybe you can do it on the country level, but you cannot do it in the county level, because in many counties, there are just hundreds or thousands of cases, which shouldn't be considered as a big data if you want to build up a deep learning model. But at this point, I guess we have more and more data from different data sources. So perhaps it would be an interesting idea to somehow try more advanced deep learning model, or try something which combines the best of both worlds. For example, both deep learning model and the academic model driven machine learning approach. So I would be very interested in exploring this direction, and would also be happy to talk with Xifeng and many other modeling people to see whether it's a good idea and can give us better result.
Thank you. Xifeng, do you, looks like you're back online. Do you have some follow-up things to talk about?
Zoom dead. Yeah, I'm sorry about this. Yes, I think Chuan probably said what I want to say, that I think this is very good summary between the white box model and the black model. Yeah. And especially when you have a lot of data, then those neural net model might have good chance. But when you have few data points, then a model-based method might perform better.
All All right. Yeah, hopefully this forecasting is going to help our entire community to get fine-grained forecast. So we're ready for the next episode of this pandemic and be more ready than what we had been doing as a nation. So if there are no further questions, we'll move into the next very interesting section about another completely different way of using AI and machine learning for handling COVID-19. So previously we have been dealing with all the macro kind of information, like predicting the overall statistics per county for the number of cases, number of deaths and hospitalization and so on. But you can also use AI and machine learning to directly deal with how the virus interact with human beings to predict and diagnose such diseases for testing and potentially even for vaccine design. So coming up next are two very interesting talks by Professor James Zhou and Professor Liang Huang. And then we'll have the Q&A section after the two talks.
Hi, everyone. My name is James Zhou. I'm an assistant professor at Stanford. And I want to share with you some research we've been doing on how we can use machine learning to study the fundamental biology of SARS-CoV-2. So SARS-CoV-2 is the virus that causes the COVID-19 pandemic. It's actually quite important for us to just appreciate how little we understand about the virus. In particular, one of the big mysteries is where does the virus go once it gets inside the human cell? So here's a cartoon that we often show about the virus life cycles. Right? So we know that here's the virus on the left. Right? We know that it uses these spikes to get into the cell. And we know that after some time, it replicates itself and then it releases the offsprings back out into the environment. So we know the input and we know the output, but what really happens in the middle, once it's inside the cell, it's still quite mysterious. And that's where we like to use machine learning to help us to understand and to predict what the virus does once it's inside the human cell. And in particular, we want to understand how, where does the virus actually hide itself inside our cells? So the reason why this is quite important is that if we can understand where it's hiding, then we can better find ways to attack the virus, and we can also better understand the mechanisms through which the virus hijacks the cellular machineries. So here's a cartoon schematic of the different compartments inside the human cell. Right, so for example, here we have the nucleus, which is the operating center, or the sort of the command center of the cell. Right? And here we have the mitochondria, which is sort of the energy factories of the cell. And then there are also several other compartments. There are about 8 different compartments here that's illustrated. So the question we want to understand is, can we use machine learning to help us to predict which of these compartments the virus SARS-CoV-2 is likely to localize? And to do that, we developed a machine learning algorithm called RNA GPS to help us make those predictions and to model these localization patterns. This is a close collaboration with my colleague at Stanford, Professor Howard Chang, and the work is led by our student, Kevin, who's a fantastic PhD student. So I want to describe a little bit of how this RNA GPS algorithm works. Right, so the input of the algorithm is the RNA nucleotide sequence, so a string of the sequence. So what the algorithm does intuitively is that it first chops up the sequence into different locations that are relevant to different biological components of the RNA. Right, so there's the start of the RNA, the coding sequence, and there's the end of the RNA. And within each region, it captures different features that are biologically relevant. Right? And with these features, the algorithm that makes a prediction, the output is a probability vector over these 8 different compartments of the cell. So it predicts for each input RNA, what is how likely is the RNA to localize to each of these different compartments. So the algorithm is actually trained on some really exciting experimental data, and it's validated on this experimental data. It's generated from Howard's group, right, where we have some quite exciting technologies to, at high resolution, to identify where does each RNA actually physically localize. So it's trained on thousands of human RNA sequences. And if you're interested, we have a paper that's recently published that describes the RNA GPS algorithm and the experiments in detail. Okay, so how do we apply this algorithm to model SARS-CoV-2? So the reason why this algorithm is particularly useful for SARS-CoV-2 is that the SARS-CoV-2's genome is an RNA genome. So this is different from our human genomes, which is a DNA genome. So the material of the information of the virus is actually encoded in RNA sequence. So this actually makes it a perfect candidate to apply the RNA GPS algorithm. So here's the illustration of the SARS-CoV-2 genome. Right, so you see this one continuous strand. And once it gets inside the human cell, this continuous strand actually splits itself into different subcompartments. The different colors here in this initial strand corresponds to all the different compartments of the genome. Right? So after it gets into the human cell, it basically splices itself into about a dozen different subgenomic sequences, and each subgenomic sequence essentially operates independently. What we do is we actually apply RNA GPS to model and to predict the physical localizations of each of the subgenomic elements corresponding to SARS-CoV-2. The output of the models and the predictions are captured in this heat map here. So let me explain this a little bit. So each row of this heat map corresponds to one of the subgenomic sequences that's generated by SARS-CoV-2's genome. And each column corresponds to one of the 8 possible compartments inside the cell. Right? So the color of the heat map corresponds to how likely is this particular subgenomic element of SARS-CoV-2 to localize physically to each of these 8 compartments. So the darker the red color means it's more likely to localize, and the darker the blue color means it's less likely to localize to that particular location. So one thing that's actually quite surprising and really interesting to us is that if you look across all these different variants of the virus, right? So they're consistently localizing, as predicted by the model, to the mitochondria. Right? So this is really where the virus is targeting. And it's also a very strong, consistent signal of localization to inside the nucleus, in particular to these nucleolus, which are regions within the nucleus where a lot of the RNA processing is being performed. Okay, so I think those are really interesting. And the RNA GPS algorithm also enables us to more finely quantify where is this localization signal encoded in the genome of the virus. Right? So through the systematic analysis, the algorithm identifies that for localization to the mitochondria, most of the signal is actually contained in the 5' end of the sequence. Right? So that's the start of the genome of the virus. In contrast, the localization to the nucleolus is mostly contained in the 3' end, so at the end of the sequence. So in other words, right, so if you look at this whole viral genome, so localization is really contained in the start and the end of the genome, and information for locations is actually not really in the coding sequences or in the middle of the viral genome. So I think that's really interesting. One natural question is, how does the localization of SARS-CoV-2 compare with other coronaviruses, right, with its cousins? So we pulled together hundreds of strains of previously identified and sequenced coronaviruses, and we compare that by applying RNA GPS to each of those previous coronaviruses and compare that with the predictions from SARS-CoV-2. So the results summarized in this heat map here, right? So here the color, which is different from before, so here the color indicates how much more likely is the new coronavirus for COVID-19 to localize to each compartment compared to the previous coronaviruses. And one very interesting and striking signal is that there's a very strong signal that the new coronavirus is much more likely to localize to the mitochondrial matrix, right, to the mitochondria, compared to the previous, its previous cousins, compared to the previous coronaviruses, right? So I think that's a very strong signal, and it's also extremely interesting. So just to summarize the findings, right, so we've developed this RNA GPS algorithm, a machine learning algorithm, to predict how does each RNA sequence localize to different parts of the cell. And we apply that to SARS-CoV-2 as well as to previous coronaviruses. One really striking prediction from the model is that the SARS-CoV-2 virus, its genome, it actually has a lot of signals to localize to the mitochondria of the cell, which is the energy factory of the cell. This could be due to several reasons. One very intriguing reason, potential hypothesis, is that the mitochondria actually has a very unique feature, right? So it has this double membrane structure, which makes it quite safe as a hiding place. So one hypothesis that we propose is that the SARS-CoV-2 virus could actually be targeting, in particular, these double membrane structures as a place to sort of hide itself from the immune systems of the cell. And it might do this even to a higher extent than its cousins, than the previously identified coronaviruses. So there's some actually really recent, very exciting works that I think supports this hypothesis. Right? So here's a paper published in Science just a few days ago, right? And it actually takes these beautiful experimental microscopy images from cryo-EM, using cryo-EM techniques of the cells that are infected by SARS-CoV-2. So after the infection, so we observed these really interesting spherical structures as shown here, right? So these are actually exactly double membrane structures that are induced by the virus, right? These are structures that are created by the virus. And here is the three-dimensional reconstruction of what these spherical things look like, these double membrane vesicles. So these are the yellow spheres here. And we can see that the virus is actually hiding within those spheres. Right, so this, I think, quite supports and are consistent with our computational predictions, and also proposes a mechanism through which the virus actually uses these double membrane structures to potentially hide itself from immune response from different attacks. So I think understanding this could have quite strong implications for designing better treatments, vaccines for the virus. Great. So the remaining couple of minutes, I want to tell you about some of other resources that we created in case you're interested to learn more about how machine learning can be used to understand different aspects of the pandemic and of the virus. So in the spring this year, I taught a class at Stanford called Data Science and AI for COVID-19. It's a class that's designed towards AI researchers and computer scientists and data scientists. So we've made all of the materials for the class publicly available. So you can find videos of the class on YouTube, as well as slides and references and papers. And the class is also designed to really look at this pandemic and look at the virus from a variety of perspectives. Right? So we talk about quite a bit about the biology of the virus and how machine learning and AI can help to understand the biology. So the example from the research I showed you is one example of this. We'll also discuss how machine learning can improve the epidemiological predictions and to optimize hospital operations. And we also study how we can use these machine learning techniques to study the social behaviors in the general public, which could be changes in mobility patterns in social networks, in public perceptions, for example, as they measured through Twitter feeds. Right, so if you're interested to learn more about this, right, so you can go to the course website and you can find all of these materials. So hopefully this will be a useful reference for you. And I just want to briefly highlight a couple of projects that are really related to the class that looks at the pandemic from these different perspectives. Right, so one project that's led by a terrific student, Rishan, is to actually model the risk factors for this pandemic using large-scale medical claims data. So we have a close collaboration with Anthem, which is one of the larger insurance companies in the US, where we actually have insurance claims data from over 100,000 COVID-19 patients all across the country. Right? And Rishan has developed really nice models to analyze what are the specific risk factors which can be measured through the insurance claims for people who are affected with the virus before they're exposed to the virus and after they're exposed to the virus. Right? So this enables us to understand different aspects, different risks, both pre and post infections. Another project from the class that's actually quite interesting is on studying the quality of data reporting as related to COVID-19. So this is done by Varun and Abhinaya. So what we did here is to design a score metric to really quantitatively assess how reliable and how transparent is the COVID-19 data that's being reported by different governments and the different locations. Right? So this can be broadly applied to the US, but also can be applied to many other countries. So in particular, Varun and Abhinaya actually applied this to different states within India. So for each state, they actually created a report card to assess how good, how high quality, and how reliable, or how responsible is the reporting COVID-19 data reported by that state. You can find those information. There's also a paper that we've published on this topic. And I think this is also quite an important topic because we observed extremely heterogeneous qualities of data reporting, which could be quite detrimental or limiting for the public health efforts. Great, so I'll stop here. Thanks for your attention. I'm happy to take questions.
My name is Liang Huang from BioResearch USA and Oregon State University. And I would like to thank the organizers of this workshop for inviting me, especially William for inviting me to give this talk. So actually, I'm not a biologist. I'm not even a computational biologist per se. I'm a computational linguist by training, and most of my previous work has been in computational linguistics, also known as natural language processing. But in the past, like 5 years or so, I've been gradually adapting more and more of my algorithms from computational linguistics to biology, and especially RNA folding, because these two fields, even though they're far apart on the surface, they actually share the same mathematical foundations. So I adapted my linear time parsing algorithm from linguistics to RNA folding, which resulted in linear fold, published last year, which is the first linear time algorithm to do RNA structure prediction. And it's orders of magnitude faster than previous cubic time methods. Cubic time methods are kind of similar to our classical CKY style parsers in natural language processing. And when the pandemic strikes, you know that the coronavirus has the longest genome among all RNA viruses. Its genome length is 30,000 nucleotides. So N is 30,000, which is much, much longer than any sentence in, like, say, English or Chinese. So the impact of my algorithm is much more bigger in biology, and especially because of the pandemic. And we also extend it to do the partition function of all possible structures. And that's a well-known or widely used concept in classical structure prediction, like conditional random fields, for example, partition function, Markov random fields. But it's no longer being used very often in today's deep learning environment, unfortunately. And we also extend it to do conserved structure prediction, so that we can look at coronavirus genome and see which segments of the genome is well conserved among all the variations. So those parts are the critical parts of the virus and will be targets for drug design. So this is the first time that conserved structure prediction can scale to the coronavirus genome scale of 30,000 nucleotides. So those RNA viruses like HIV, Ebola, MERS, SARS, coronavirus require very fast, efficient algorithms. And it's lucky that I've been developing those algorithms from computational linguistics, and they certainly have a lot of usage in this pandemic. And these are my students and co-authors, and we also have a great collaborator, David Matthews, from University of Rochester Medical School. But pandemic changed everything. Since the pandemic, I've been asking myself, how do you do something more directly to help fight this virus? So we're thinking about vaccine design, and a professor in Stanford Medical School, Riju Das, told me something about the principle of vaccine design and the major challenge there. So it turns out that mRNA vaccine design has emerged as probably the fastest and safest route among all the vaccine types. It's much faster for mass production than the classical vaccine type, which is the protein vaccines like flu shots. But it's still a long way to go, with many challenges remaining. Especially the most important challenge, arguably, is the chemical stability, or instability rather, of RNA vaccines. And because of that, the immunogenicity, low immunogenicity problem. So you probably read the news that Moderna and Pfizer and maybe other mRNA vaccine companies need very, very low temperature, ultra low temperature, like maybe negative 50 Celsius, for the storage and shipment of those vaccines, which increases the cost. And also, you probably need larger doses because of low immunogenicity, and that would induce more side effects. And you can read it from Moderna's phase 1 or phase 2 reports. And our idea to solve this problem is to use some classical work from computational linguistics to design more stable mRNAs. And because of the stability, they will lead to also higher protein expression level, so that it will produce more antigens to trigger your immune response. So as we all know, there are 3 types of vaccines. Protein vaccine is the dominant one, and almost all the vaccines you have seen so far are protein vaccines, like flu shots. But it's very, very slow for mass production because you need a lot of eggs or cells to grow or replicate or cultivate the virus inside the eggs. So that's why you need a year for every year you need a long time to make a new flu shot. And it has also a small risk of infection. The DNA and mRNA vaccines are gene-based vaccines, also known as source installation instead of binary installation. So protein is like a binary installation. It directly installs the antigens, the proteins, into your body to trigger the immune response. But this DNA of mRNA vaccine injects not the proteins, but the genes, so that will be translated into proteins. So they are more like source table installation. And DNA vaccine and mRNA vaccine are much faster in mass production because you don't need eggs or cells. It's no risk of infection. But DNA has a small risk of integration to your genome because it has to enter your nucleus to be transcribed to mRNA and then translated here in cytoplasm to proteins. mRNA only enters cytoplasm to be translated by ribosomes to proteins or antigens. So it's probably the safest and fastest. But the problem, as I said before, is the chemical instability, because RNAs are mostly single-stranded. And because of that, it can easily be cut down in water or other molecules because hydrolysis or other enzymes are trying to degrade it, cutting down the single-stranded portions of the sequence, whereas the double-stranded pieces or segments of RNAs are more stable, just like a DNA, right? So DNAs are much more stable than RNA. So the question really is, how do you make this mRNA more like a DNA? How do you make it more stable chemically by changing the design of the sequence? And because of the stability, probably use higher amount of proteins or the antigens, so that will have better immunogenicity. So that's the question we're going to solve using computational linguistics today. So mathematically, the problem really has an exponentially large search space. So formally speaking, mRNA design problem is trying to exploit the redundancy in our genetic code, because each amino acid can be translated by multiple DNA codons or RNA codons, also called triplet codons. So there's 4 to the power of 364 possibilities, possible triplet codons, and only 21 amino acids. So each amino acid has, roughly speaking, 3 different ways to be translated, right? But if you list them down, and if you say, oh, this is the coronavirus spike protein sequence, and by the way, spike protein is the most commonly used vaccine target. So you want to kind of express or translate into this spike protein, which will your body will trigger or will recognize. So next time if the real virus strikes, you'll say, oh, I saw you before, right? So you say, oh, methionine, you have 1 choice, F, you have 2 choices, valine, you have 4 choices, blah, blah, blah. You times them all together, the product of all the choices, you got 2.4 times 10 to the power of 632 choices or candidates or sequences. So all these sequences translate to the same protein, which is the spike protein. So these are called synonymous mRNAs. And which one is the best? Well, according to the Moderna paper, you want the one that is most stable, in other words, the lowest free energy or the highest amount of secondary structure, because that stability also yields to high protein expression. But the question really is, how do you try to find the best one, the most stable one among this huge space? By the way, if you can enumerate them like 1 second a sequence, this will take more than the life of the universe. So it's definitely impossible to enumerate them one by one. So how do you do the search efficiently in this gigantic space? Well, it turns out that this is a classical problem that in computer science we have solved it in 1961. So this problem was given to us by Professor Rujudas from Stanford, who introduced us to this problem. But he thought this is like an NP hard, it's impossible to solve, it's way too big for combinatorial explosion. So he designed another game called Open Vaccine, which uses my linear fold, which I introduced in the first slide, plus cross-sourcing. So that he asked players to help design the vaccine and use my linear fold to score the energy, the stability. So my linear fold will report the stability very fast, in like 3 to 4 seconds, because it's the fastest folding algorithm. But I thought that would still be impossible for human beings to do a gradient descent in this kind of space. So human gradient descent might be more useful, more kind of intuitive than machine gradient descent, because machines are kind of blind. Humans have better intuitions, but this is still way too big for humans to search. So I would like to say use a direct optimization method. So how do we do it? Well, before I talk about technical details, I would like to show you the results. Well, so this is the wild type of the coronavirus. You can see that it has very bad shape, has a lot of single-stranded areas which can easily be cut down in water. So largely single-stranded, high free energy, and easily degraded. After about 10 minutes of optimization, we got something much better. As you can see, they're mostly double-stranded, and so it's no longer very easy to be cut down, and it has a much lower free energy and much more stable in water or other environments. And you're trying basically making an RNA into a DNA, roughly speaking. So how did we do it? Well, here's the optimization problem. Here's how we treat this. So we treat each mRNA as a DFA. We treat each amino acid as a DFA. So, for example, valine is an amino acid, has 4 different choices of triplet codons. So we represent them as a DFA. Serine has 6, we represent them as a DFA. And then you concatenate these little DFAs for amino acids together to organize into a protein DFA. And this very long protein DFA encodes all the mRNAs that can translate to the same protein. For example, all these different paths in this DFA translates to the same protein. So they're all called synonymous mRNAs. So in other words, we have a very compact space encoding all the exponentially many possibilities. So that's our first observation. Our second the great ingredient of our work is to represent the folding free energy of RNA as stochastic context free grammars. That's very old stuff. That's stuff dating back from 1980s, and that's something I talked about in the very beginning. Why these two fields share the same mathematical foundation. But the next observation, which is new, is to realize for the first time that mRNA design problem is nothing but CFG intersection with DFA. Why? Because how do you find the best path in this, in the exponentially many possibilities in this DFA? Well, we superimpose the CFG, the context free grammar, on top of this DFA to do the intersection, and we know that CFG intersection DFA you got another CFG, a larger CFG, and that's a classical concept in the theory of computation and computational linguistics, which dates back to 1960s. And dynamic programming can solve it in cubic time, where n is the RNA sequence length. So that's very efficient. So that's the kind of eureka moment that we realized this problem is actually solved 60 years ago. It's just another classical problem. So as we implemented it, and the speed results is that you have 2 versions. One is exact search, the other is approximate search. And the exact search can finish in about 1 hour, and you lower the energy by more than 2-fold. And approximate search is much faster, 11 minutes, and the energy is almost the same, only like less than 1% difference. And as you can see, the design structures, wild type is very, very bad in energy and shape, and linear design is much, much better, much tighter, so that it's mostly double-stranded and much lower in energy, so it's much more stable. But that's only half of the story. Well, the other half of the story is that you have to consider codon optimality, where human cells prefer GC-rich codons, and other like yeast maybe preferring AU-rich codons, but different codons for the same amino acid have a distribution, have a frequency or probability. So for example, if you want to encode leucine, you would prefer to use CTG. So you would ask your design to be using the frequent codons more and more, so that you can increase the translation efficiency. So that's why it's really a 2-dimensional optimization. On the x-axis, you want the lower the better, because the lower the energy, the more negative the energy, the more stable the structure. On the y-axis, you want higher the better. The high CAI means codon adaptation index, closer to 1 meaning more efficient, using only the frequent codons, very frequent codons. And wild type is very bad in both structure and CAI, in both energy and CAI, because it doesn't have enough time to evolve in the human organism. So it still is very kind of primitive from the virus. It's just recently jumped onto humans. So, but if you do CI greedy design, then for each amino acid, you choose the best or most frequent codon, and you got a CI of 1. And because human codons prefer GC richness, and GC richness gets lower energy or better structure, so you actually got a byproduct of lower energy. But it's only a little bit better, not too much better. And most vaccine companies are doing codon optimization like here, very close to here, which you get much higher efficiency and also lower energy and more stability. But the whole area left to this line is uncharted area. Nobody knows what's going on here. And there is also a kind of feasibility limit where above which it's impossible in feasible region. So lambda is a hyperparameter which controls the relative importance between CAI and MFE. For example, lambda of 0 means you only consider energy, no CAI, and lambda of infinity means CAI greedy design with no energy in consideration. With varying lambda, you got a curve, and beyond this curve, everything is impossible, right? So these areas will be too good to have because the optimization direction is towards the top left. But the lower right of that curve, everything is possible. So the feasible region is huge, really. So every point is a sequence, 2.4 times 10 to the power of 632 candidates. And all these candidates left to this line are uncharted region. Like even Moderna people didn't explore because they didn't have a way to optimize, to do the combinatorial optimization of energy. So just to summarize, mRNA stability is a major challenge for vaccine development. And if we can solve it, we can reduce the cost and we can reduce the dosage and to make it more usable for the general public. And we proposed efficient algorithm for optimized mRNA vaccine design. It turns out this problem was solved 60 years ago. We just rediscovered it. And we can design very long mRNAs for the spike protein in just an hour. By the way, this is also the target for Moderna and many other vaccine companies. And the codon optimality can be jointly optimized in this two-dimensional way. And this is useful not just in vaccine design, but also in like antibody design, cancer treatment, gene therapy, synthetic biology, and so on and so forth. And since the release of our preprint, several major vaccine companies from the US, EU, and China have been in contact with us, and some of them are doing the wet lab experiments to verify whether our designs, in silico designs, are actually useful in practice, like in vitro and in vivo. So those are wait to be seen. So we are only doing a hypothesis. So with that, I would like to thank you, and please try our web server and our preprint here, so you can upload any protein sequence, and within this very short time, we can return you the best vaccine mRNA vaccine sequence. And these are our co-authors and collaborators, and our general manager of battery research, Julia Lee, and we thank Professor Vijay Das from Stanford for giving us this problem to work on. I would like to thank you again for your attention.
Thank you very much. Let's thank James and Liang for the great talks. So we're now entering the question and answering session for the third afternoon session on AI and ML for the virus behaviors and vaccine design. There is a question from Paz. If we're modifying the shape of the spike for stability, how do we know it would be close enough to teach our immune system to recognize the original?
Oh, hi. Can you guys hear me?
Yes.
Okay, great. So that's a great question. But actually, we don't modify the spike protein sequence. We modify the mRNA sequence that can translate to the protein. So as I said in the talk, there is a genetic redundancy in the genetic code, so that there are multiple different ways to encode the same protein from DNA or RNA. So in other words, we don't do any engineering or design on the protein part. We keep it the same. So otherwise, you change the shape of the spike, it probably won't be good. But we can change all kinds of, we can design the mRNAs. Then there are kind of billions, trillions of different mRNAs that can translate to the same protein. And hopefully that answers your question.
Great. I have a question to James, but also perhaps the same question can be posed to Liang as well. So you guys are solving the problems that are extremely challenging, that require both expertise in AI and machine learning, but also have a certain domain knowledge that allows you to formulate the problem in the first place. What is the role of the AI and machine learning techniques that they play, like in this problem? So do they only come as a technical tool for you to solve the concisely formulated mathematical problem and computational problem afterwards, or can they also somehow help you to discover the problem and the right way to attack these problems in the first place? So maybe we can start with James first and then get back to Liang.
Yeah, thanks for the great question. I think it's certainly very interesting. In our experience, we found it's very helpful to work closely with experimental collaborators. And it looks like from Leon's talk, that's the case in his experience as well. So for the RNA localization project, to figure out where in the cell the virus actually go to. So we collaborated very closely with my colleague, Howard Chang, who's really an expert in studying RNA localization. And for that, we found it's actually very useful to have this feedback loop where we have the computational algorithm that had these suggestions. Howard's group actually generated experimental data to train and to validate the algorithm, right? So they have some of the first techniques that can tell you which compartments, is it the mitochondria, is it the nucleus, nucleolus, where is the RNA actually physically localizing to? And then that ends up becoming very useful because then we identify additional sequences that that we haven't tested before, right? So we can also generate those and then experimentally test those. So I think having that feedback loop through this this close collaboration with the experimental colleagues is probably one very powerful way for machine learning to make contribution.
Thank you. That's great. Liang, do you have any comments to this
question?
Sure.
So as I said, I don't know anything about biology. I don't know anything about vaccines. There was Richard Das, who James knows, James' colleague at Stanford, who taught me all these kind of vaccine biology and stuff like that, and that gave us the problem, and then we formalized it as a mathematical problem, optimization problem, and then from that point on, it's totally we can reduce it. We realized that it can be reduced to a classical problem in computer science that was solved 60 years ago. But that was kind of very coincidental. Something completely unexpected. But that's still in silico work. So that's why vaccine companies are doing kind of wet lab experiments right now to verify if our designs are actually good. And that will take a long time actually. So the wet lab experiments are much more costly and time consuming than our kind of computational work. But still we need those verification, because otherwise there are a lot of kind of features or factors that we didn't consider in our work. For example, the pH level, the temperature, the existence of magnesium or other kind of atoms in the cell environment, whether it's in vivo or in vitro, blah blah blah. So all those things that are much more complicated than we can model in our algorithm. So maybe some of them are actually important. So we don't know. That's why we would need to wait for the wet lab experiments.
Yeah, that's indeed very interesting that you guys can reduce the problem into a computational problem where you can solve with dynamic programming in O cube time. So I have a question related to that. Is like the cubic time sufficiently efficient for practical application for this? I thought N could be actually quite large.
Yes, that's a very good question, Yushan. So cubic time is kind of slow for very long protein sequences, but our code is pretty fast that it can work in like an hour for spike protein. And an hour is kind of slow for computer scientists, but it's extremely fast for biologists. Like even if you take a day, that's much faster than their wet lab experiments. But we also talked about in my talk a linear time approximation version of that, which runs in only like 11 minutes. Which is approximate, but it's almost as good as the exact search because the energy is only like less than 1% worse than the exact search. So if you have a much longer sequence that you want to design, you can use the linear time one. But yeah, that's a very, very good question. But the short answer is these algorithms are faster enough for biologists. Thank you.
Awesome. And James, yes, please go ahead.
Okay, so I also want to ask actually a follow-up question to Leon related to that. Sure. Sorry to interrupt, Yushan. So first, very interesting work, very nice work. So you mentioned that there are all these approximations. I'm curious to also what your thoughts are on how good the energy function itself is an approximation for the real physical environment inside the cell, because as you mentioned, there are all these other interactions and different, the cell itself is a very complex environment. So how good do you think the energy function is?
Yeah, that's a very good question. So energy functions is actually not very good. The state-of-the-art energy functions that we use are far from accurate actually for RNAs. They have been developed in the past 20 years or so, without using machine learning too much. But recently there have been more like deep learning or machine learning based approaches. Some from Richard Dass's lab or Howard Chang's lab, but so far we just use the standard energy models, thermodynamic energy models, and they're not ideal, but they're probably good enough in the sense that we designed the sequence to be so complementary so that it's really like a DNA instead of RNA anymore. So it's mostly double-stranded anyways. So if we have a better energy model, I'm sure it will be better in terms of the real stability. But yeah, but we need to improve the energy model as well. So yeah, that's a very, very good question. Thank you, James.
Great. I have a different question to James, but let's first address this question from the floor. So Carl posed a very interesting question. I think this one is to Liang. So was there an eureka moment when you found that you could reduce to the classical problem? Were you actively searching multiple classical problems, or did someone in the team have a hunch to investigate based on past studies?
That's a very good question. Yeah, so when Richard Das taught me this problem, I was initially thinking like this might be solvable, but then after several weeks, I realized that it's just reducible to a classical problem, and that was indeed a real eureka moment. But for some reason, Richard didn't believe in me in that. He thought this problem is still NP hard, so he went on to do the human kind of core sorting game. But then we worked it out and showed him the paper. Then he was convinced that this is totally solvable mathematically. But we didn't actually research for the classical problems because it's just something that is taught in undergraduate computer science curriculum, the theoretical computer science classes that I always teach in my teaching career. So this is something like this, like very classical in computer science and computational linguistics as well, because the original paper 1961 is actually from computational linguistics, but it became some kind of cornerstone of theoretical computer science. So it is kind of a eureka moment, and yeah, I was really glad about that. Thank you.
All right, I'll ask one last question to James. So in the second part of our talk, you talk about first of all the data collection by working with the insurance company. Like, were there any challenges there that's worth mentioning next time? Like, we're collaborating with partners like that. Like, were they willing to share such data? So what are the privacy constraints? And then the other thing is that you have organized this very nice course at Stanford that brings together brought together domain experts and also graduate students focusing on machine learning and AI. Was there any challenges that you encountered in getting like these people with diverse background to start talking with the same language? Like, do people understand each other from the very beginning, or there were some challenging moments that you wanted to share?
Yeah, thank you. Both are great questions. So for the first one, for working with the insurance company, I think we both quickly realized, both us and the insurance company, that they probably have actually the best data sets, some of the best data sets to study COVID, even compared to the CDC, right? Because the CDC or even the hospitals, they only have data from within a few hospitals. But the insurance company actually covers like 40 million, even a larger number of Americans. So they actually have data for hundreds of thousands of COVID patients. So I think just from a data research perspective, I think they're actually the best people to work with. And especially one of the projects I'm super excited about now is look at what happens to people after they're infected with COVID, right? Like Trump and others, right? So what happens to their other physiology in a month, even after they have recovered? Yeah. And I think the insurance data, because they continue to get claims back from the patients over time, I think that's probably maybe the most exciting place to leverage the kinds of claims data. So there are certainly a lot of challenges in working with these insurance companies. I think right now, my sense is that they're very willing to work on these kind of problems, even more than before, just because of the urgent nature of this crisis. But there's certainly lots of challenges in terms of privacy. So when we work on these data, we have to make sure that we're essentially only working on fairly large aggregate statistics. So we haven't used sort of differential privacy type techniques, but we try to make sure that we're only working on large aggregate statistics. And in some sense, we'll have to coarsen the data into like weeks instead of individual days, right? So sort of various ways to coarsen and to aggregate the data to make sure that things are relatively kosher. But I think it's certainly worth the effort because these are some really exciting data sets. And then for the class, I think it's certainly been a really interesting experience for the class. What we found to be very useful is to have these tutorials, weekly tutorials on quite diverse topics to bring everyone up to speed. So we had tutorials, for example, on the biology, the DNA sequence of the virus. So how does the virus actually work? So that's actually quite important to explain that to the computer scientists. And then to the biologists, we also have to explain things like how does the emergency room in the hospital actually work, right? So what does it mean when someone actually goes into the emergency room? What are the procedures that happens there, right? And then to everyone, and so ends up being very important to explain what are the public policies involved across different countries, right? So and I learned a lot about all of those from our guest lectures and tutorials. So I think having these tutorials to bring everyone up to speed it ends up being very useful.
Awesome. Yeah, let's thank our two speakers again. And now it's our time to move to our last and final session today. So I'll hand over to Professor Ambuj Singh to introduce our third keynote speaker.
Thank you.
Thank you, Yushang. It's been a wonderful day, and who better to bring it all to an end than Jeanette. So she is heading data science at Columbia right now, and she had a long career that has spanned the public, the private, NSF. Personally, I knew of her work when I was doing my PhD. I was trying to atomic registers, and Morris and her worked on this theory of concurrent objects. And what was this at that time? Linearizability theory. We didn't know about the formal aspects of concurrent objects. So I have followed her career since then. She received a PhD from MIT. She served on the faculty before she got to Columbia at USC and CMU. She was the department chair there. Her research, as I mentioned, spans formal aspects and now data science and trustworthy AI, which is the focus of her talk today. She served as the assistant director of the NSF. So she has had contributions in terms of trying to understand what kind of research ought to be funded and that it should be funded widely. She took leave and went to Microsoft Research, and she was heading Microsoft Research there. So she understands what happens in the private sector too. And one last bit that I would like to point out about her work is very early on, she inspired this idea of computational thinking, which I think has been around and which is something that I really think about a lot, is not just this aspect of how do you think in a computational manner and solve problems, and how do we teach others, not just computer scientists alone, but others about this paradigm of solving problems. So I have followed her career. She has affected my research, my teaching, and it's a great pleasure to have Jeanette Wing tell us about trustworthy AI.
Thank you so much for that introduction. That was a wonderful overview of my life, I feel. I actually have a confession to make to this audience. I know that you've been talking about COVID all day, and but when I was invited to talk to this conference, I was quite impressed with the title, Responsible Machine Learning. And I said, I am not going to talk about COVID. Florence can talk about what we've been doing with the COVID information commons, and I know she did a great job. I want to talk to this audience about responsible machine learning. Can I do that? And I guess the organizer said, okay, well, we'll let her talk about that. She doesn't have to talk about COVID. So I also know that I'm at the end of a full day, and so I will try to keep this high level enough so that people can appreciate what message I'm trying to convey, but give some details about my thinking about how to approach trustworthy AI. So I will share my screen and I really do want to thank the organizers for letting me basically get on a soapbox and promote what I think is a very important research agenda for the computing field. And by computing field, of course, having been at NSF, I really mean the breadth of computing from computer science, artificial intelligence, data science, really the whole gamut. The work I'm going to talk about is partially funded in spirit by the Sloan Foundation, the National Science Foundation, and the Columbia University Data Science Institute. But I'm not actually going to show any results, maybe one little result, but I'm really going to try to encourage all of you, all of us in the computing field to think about what it means to make AI systems trustworthy. So I'm going to go through this intro very quickly because I think for this audience, you've not only heard this, but you've probably seen the same old pictures. So AI achieves or exceeds human performance, whether it's computer vision systems driving our cars, speech recognition systems talking to us in the living room, or beating the best Go player in the world. AI, I believe, can benefit humanity and society. That's why we're so keen on building self-driving cars to save traffic deaths. We are seeing the use of deep neural networks in radiology, and in this particular example from the Cleveland Clinic, the AI system outperformed the neuroradiologists. There's a hope that by using AI systems, we can be fairer and more uniform in our judgments in the court system. And as you know, AI systems are also being used in the hiring process. And again, the idea is not to be subject to the whims of the human who is interviewing us, but be fair and uniform in our judgment. This is the hope. And of course, the next slide is what has been shown to go wrong. Why should we trust these AI-based systems? We know it's very easy to fool a classifier into thinking that a stop sign is not a stop sign by just adding some duct tape. We know just by adding noise, we can fool the classifier into classifying what is benign to be malignant. We have loads and loads of popular press stories and academic stories now that show that the machine learned models that we produce, if trained on biased data, will produce biased results. And the whole issue of what fairness means was raised by the ProPublica analysis of the COMPAS data on risk recidivism. And of course, we also know that as much as companies want to hire in a fair manner, again, if you're starting with biased training data, you're going to get biased results. So the question I want to pose this community, and by this community, I mean not just the audience here, but the broad computer science, data science, AI community, is how then can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? Now, this notion of trustworthiness is definitely not new. For those of us who have been in the trustworthy computing research area, I would say the whole area started at least 2 decades ago with the Trust in Cyberspace National Academies report that Fred Schneider edited. That helped inspire the National Science Foundation to start what was then probably a cyber trust program. It was within one directorate at NSF. By the time I got to NSF, it was cross-directorate, and what I helped do was make it cross-foundational. And right now, the Secure and Trustworthy Computing Program continues the march forward in trying to make computing systems trustworthy. And also at the same time, and not coincidentally, I suppose, Bill Gates put out the 2001 memo called Trustworthy Computing at Microsoft. And that stopped coding within the company for 9 months. Because at the time, and this might be something that the young people in the audience never experienced, but at the time, it was pretty par for the course to get blue screens of death if you're using a Windows machine. And Microsoft knew that it had to make its software more trustworthy, otherwise it would actually lose customers. And that was one reason for Microsoft to stop coding for so long. But trustworthy computing has come to mean a certain set of properties. For the Bill Gates memo, it was reliability, security, privacy, and what they called business integrity, later replaced by usability. The general community has attributed these properties to the notion of trustworthiness. Reliability, does it do the right thing? That's often couched as a correctness property, and I'll get to that when I get to formalism. Safety, does it do no harm? Security, how vulnerable is it to attack? Privacy, does it protect a person's identity and data? Availability, is the system up when I need to access it? This is really characterized as a liveness property. Usability, can a human use it easily? And the kinds of systems that we care to make trustworthy are computing systems made out of hardware and software. And later, when people started talking about usability, they kind of added people into that. So from trustworthy computing, how about AI? What does trustworthy AI require? What properties would we associate with trustworthy AI? And this is where I really want to emphasize that we still are trying to build trustworthy computing systems, but the AI systems that we are building today and deploying today are basically requiring us in the trustworthy computing community to up the ante. It's not just the properties that I list on the left, but it's also properties that I list on the right. And let me just, analogously ask, what question does each of these properties try to answer? Okay, my advanced button is not working. Sorry. Okay, here we go. So accuracy. This is, of course, the gold standard for AI systems, machine learning, prediction, and classification models. How well does the AI system do on new unseen data compared to data on which it was trained and tested? Robustness. How sensitive is the outcome to a change in the input? Fairness. Are the outcomes unbiased? Accountability. Who or what is responsible for the outcome? Transparency. Is it clear to an external observer how the system's outcome was produced? Interpretability or explainability. Can the system's outcome be justified with an explanation that a human can understand and or that is meaningful to the end user? and ethical. Was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And then there are properties yet to be defined, yet to be even thought of in the realm of trustworthy AI. So we are upping the ante in terms of the nature of the properties and the number of properties that AI systems have to satisfy. So how can we achieve trustworthy AI? This seems to be a really tall order. And the reason I'm so excited about this is this is going to be a research agenda probably for the rest of my life. Because if it's been 20 years and we're still chomping away at trustworthy computing, then I think we'll be chomping away in the next 20 or 30 years on trustworthy AI. So one approach, and I really want to emphasize, this is just one approach, and I think there are many, many approaches that have to come together to address trustworthy AI, much like many, many approaches are being studied and coming together to address trustworthy computing. And again, it should be probably of no surprise to people who know me, know my background, that I'm going to suggest that one approach be formal methods. And again, I don't want to say that this is the silver bullet, but I want to actually argue that the AI community is not as familiar with formal methods as perhaps they could or should be. And similarly, the formal methods community is only beginning to start to think, what would it mean to prove an AI system correct, or let's say prove that an AI system satisfies a trustworthy property? So one of the reasons I wanted to give this talk to this audience was to try to bring these communities together. And I'm coming obviously from the formal methods side of the world. So let me just characterize what traditional formal methods and formal verification looks like, and show again how AI systems are going to require us to up the ante. So in traditional formal methods or formal verification, this expression in the red box basically frames the entire enterprise of formal methods. I have to get rid of that E for now. Does a model M satisfy a property P? So that double turnstile is read as satisfy or satisfies. And M can stand for a piece of code, it can stand for a protocol, it can stand for some abstract description of a concurrent distributed system like a state machine. And we're many, many languages, tools and languages to express what M is. And so it's given an M and then given a P, some property like safety or availability, which would be characterized as a liveness property, formally written, expressed in some formal logic. Then we use our logical framework that gives us a semantics for satisfies to determine whether M satisfies P. So satisfies, we have many, many logics and tools. We have model checkers and theorem provers and SMT solvers now that are really sophisticated. They scale up, they can, really crack some of those tough distributed consensus protocols and allow engineers, but certainly I would say people in industry, allow them to actually prove properties about their code or about some protocol correct. And this has been, I've been in this business since the 80s, and so it's been really heartwarming to see how much progress has been made in formal verification. And so we really are at the point where these methods are used in industry, not pervasively, but for safety critical systems or for critical, complicated parts of a large software system. So from traditional formal verification, oh, by the way, sometimes we actually do want to make explicit the environment in which the system is operating. And we make explicit this environment by writing down a description of E, the system environment. And again, this description of E could itself be a piece of code. It could be, you know, an abstract process that's run in parallel with the system. There are all sorts of ways to describe what E is and to describe what the comma means. And that's, again, many formalisms speak to this general expression of E comma M satisfies P. So from traditional formal verification to verifying AI systems, I argue we have to up the ante. So now I want to interpret M here to be a machine learned model. By the way, these models, in the end, they're just a piece of code. So it's not a piece of code that any human being would write. That's why it's called machine learning. But it's a piece of code. So you'd like to think that the apparatus that we have for formally verifying a piece of code could also be applicable in this setting. It's just that the piece of code that we're talking about is, again, as I said, not something human beings would write. And so I think there's an opportunity here to think of new analyses and techniques, languages and logics and tools that would allow us to, say, prove some trustworthy property of this machine learned model. Now, there are obvious reasons why we want to possibly not work on the code itself, but on some abstract representation. And that's what the ... means. It's really all sorts of representations from the high level model to the piece of code. The other difference is, of course, the properties we might care about are probabilistic or stochastic in nature. And so just the expression of the property, like for instance, if you talk about robustness or fairness or privacy, all these formalizations of these kinds of properties usually have some expression that really appeals to expectation or probabilities or some distribution or class of distributions. These are properties in the old world of trustworthy computing, in the logics that we were very familiar with. You know, you write a property and you write a logical expression to express the property, and it's true or false or yes or no, black and white, on or off. And now we're in the world of probabilistic reasoning. So I think by nature, this doubles turnstile will have to appeal to probabilistic logics and reasoning about probabilities and distributions and stochastic processes and all sorts of things that the formal methods community is not used to having to reason about. And then there's something I would like to say that I think is analogous to E, and that's the data. It is, of course, the data that we use to train the machine learning model that we now find is really the culprit for making the model unfair. So now the question is, how do we express this data in a way that we can, you know, put it in the red rectangle and have a neat and tidy formalism that says, with this data or with this class of data, I can prove some property P about M. So we need some way to express a model of the data. And a normal way would be maybe through a stochastic process or simply a distribution that generates the data inputs. I have to get rid of this. This is one problem with the Zoom that needs to be verified. So the point is, trustworthy AI is already upping the ante in terms of the properties we care about. And with a formal methods approach, trustworthy AI is upping the ante in terms of the machinery that we need, the logics, the tools, the underlying mathematics that we need to actually do a verification. So this is the basic framing, and what I thought I would do in my remaining time, Abush, how much time do I have left?
You have another 15 minutes.
Okay, good. What I thought I would do is walk through each piece of this. And now I'm appealing to the graduate students in the audience because I'm going to ask a lot of questions that I don't know the answers to. And they're meant to inspire research questions. So here we go. First, what are the two main differences between kind of verification of computing systems and verification of AI systems? And I think if there's anything that you want to remember from this talk, it's really these two main differences. The need for probabilistic reasoning. I think that's just inherent in the nature of the thing we want to reason about, the expression of the properties usually that we want to reason of, and the expression of the model of data. And the second difference is the role of data. I think this is important, an important difference. And we didn't, for some reason, we didn't have to worry about the input data to a program before, because we weren't talking about massive amounts of data. And we were also going after a for all property. And I'll get to that in a second. So in terms of the role of data, there's collecting and partitioning the data, specifying unseen data, what do we want to quantify over, and how do we do the verification? I think the most interesting question in this list is what do we want to quantify over? So I want to make sure I have time to walk through the thinking about that. So the need for probabilistic reasoning, that's the first difference. And I just want to make a little more of an argument of why I think this is required. So M is semantically and structurally different from a typical computer program. It's inherently probabilistic in that if you think about a DNN, there are probabilities running all over the edges, and probabilities that are actually associated with the output. So it's not like the classifier says the tumor is benign. It says with a probability of 0.9, I think this tumor is benign. Internally, the model itself operates over probabilities and outputs results with assigned probabilities. I just basically said that. And structurally, M is machine generated, unlikely to be human readable. And from a programming language point of view, which is another part of my background, I like to think about it as another kind of intermediate code. And so with that viewpoint, one could ask very interesting questions of program analysis on this different kind of intermediate code. Also, one can ask usual questions of program analysis on basically a very complicated if-then-else statement, nested if-then-elses. P, the property, may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So robustness properties for deep neural networks, for instance, are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. And differential privacy is defined in terms of a difference in probabilities with respect to a small real value. So if P is any one of these genre of properties, we're inherently going to have to be formulating it in terms of continuous and or discrete domains. And then satisfies the probability, the logic in which we want to do this verification are, again, I have this, I think people know what I'm struggling with, these, don't know where to put all your faces. We need scalable, so the good news is the formal methods community hasn't been sitting on their hands not thinking about probabilistic state machines and probabilistic systems. So they've been inventing probabilistic logics and hybrid logics. A lot of work in the cyber physical system space really has inspired these kinds of hybrid logics. And this has been around for a couple of decades, I would say. So that's not new. What is needed, however, is the scalability of these logics and or new verification techniques that work over reals, nonlinear functions, probability distributions, stochastic processes, and so on. So this is what I think is needed. What about the role of data? So I want to first introduce some informal terminology that I like to use. I use the term available data to mean the data at hand used for training and testing, and unseen data, data that we haven't seen yet, data over which the model, the machine learning model, needs or is expected to operate without having seen it before. I mean, after all, why do you build this machine learning model? But the whole point is you feed it new data and it knows what to do with it. So collecting and partitioning data, the problems are, how do we partition an available data set into a training set and a test set? What guarantees can we make of this partition with respect to a desired property in building model M? How much data suffices to build a model M for a given property P? Does adding more data to train or test M make it more robust or fair, etc.? Or does it not have an effect with respect to the property P? And then what new kinds of data need to be collected if a particular desired property doesn't hold? Specifying unseen data. So this is specifying D. How do we specify the data and characterize the properties of the data? We could specify D as a stochastic process or a data distribution, for example, via its parameters, like a normal distribution, the mean and standard deviation. We can use probabilistic programming languages, perhaps, like STAN, which is used prevalently in the statistics community to specify statistical models. So this, again, brings in some aspect of programming languages that hasn't been really investigated. But what if large real-world data sets that don't fit into common statistical models or which have thousands of parameters? How do we specify D in that case? There is an interesting potential circular reasoning that I need to break. So for instance, to specify the unseen data D, we need to make certain assumptions about the unseen data. Would these assumptions not then be the same as those we would make to build the model M in the first place? In other words, how do we trust the specification of D? We're just pushing the trust assumptions somewhere else. This is very common in formal methods, by the way. So there are some possible ways to break the circular reasoning to bottom out. First, there is a repertoire of statistical tools that the statistics community uses in analyzing and assessing their statistical models. And I'll just very briefly mention those later. But the point is, there are tools out there that the computer science community and the formal methods community haven't even begun to think about in terms of using to assess their models. Assume that one other way is assume that an initial specification is small and simple enough that it can be checked by, say, manual inspection, eyeball it, and then we use this specification to bootstrap an iterative refinement process which is akin to the counterexample guided extraction and refinement process in formal methods. So for those of you in the audience who know about this process, this has been a very powerful way to basically bootstrap a verification of a fairly complicated, say, concurrent or distributed system. So maybe we can borrow from that idea. And then finally, another question with respect to specifying D is, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? So those are just obvious questions. And now I want to get to the question which also puzzles me, but I think I know what approach I want to use, is what do we quantify over? So remember, in traditional formal methods, we're striving to prove for all x, p of x, for some property p, for all input values x, p holds for that model, that piece of code, and so on. Or for all executions of a concurrent system, x, p of x holds, so that we can prove that any execution of a concurrent or distributed system will always satisfy deadlock freedom, and then we know that we can just plop in the system that has been proven to be deadlock free in some distributed database. That's what we strive for in traditional formal methods. These what I call for all, once and for all properties. And the whole beauty of that is so that you don't have to test, choose some number of X's and test the program on one at a time, which is in principle can go on forever. So, but what about AI systems? AI systems are not expected, a particular machine learning model is not expected. I mean, it's a different culture of what we're expected to use this M for. And it's not a for all input data. It's not for all situations or for all data sets. And part of the challenge is, of course, we know these AI systems are going to be deployed in environments where there's huge uncertainty. And so how can we grab some of those uncertain behaviors, characterize them, and say, well, for this characterization of uncertain behaviors, I can assert that my self-driving car vision system will actually work. So rather than say, for this particular behavior, I know it will work, I'd like to be able to say for a class of behaviors or a class of data distributions or a class of data sets, my model will work. So I think, so this is even asking this question is already a first step towards progress in kind of figuring out what it even means to verify an AI system. So let me give you a couple of examples. And I just want to argue that possibly even answering the question could be property dependent. So how can we specify the class of distributions over which P should hold for a given M? So for instance, if we're talking about robustness, in the adversarial machine learning setting, we might want to show that M is robust to, say, all norm-bounded perturbations V. That's a very natural assertion that we read about in many of the papers. More interestingly, of course, we might want to show that M is robust to all semantic or structural perturbations for the task at hand. So for example, in computer vision, the point is, if I want a self-driving car, which is using the computer vision system to drive around, we would likely want it to be robust to the fact that there's a dent in the car in front of us, because it's still a car, and yeah, it has a dent in the fender, but I don't want to misclassify it. So it kind of should be robust to that semantic perturbation. On the other hand, if I'm running a repair shop, I don't want my vision system to be robust to that dent. So that's why I say task at hand. Now, going back to the property dependent piece, how can we specify the class of distributions over which P should hold for a given M? Suppose instead of considering robustness, I consider fairness. So for fairness, we might want to show that the machine learning model is fair on a given data set and all unseen data sets that are similar for some formal notion of similar. For example, the recidivism risk with the COMPASS data set. And this is the only small result that I can report in working on this notion of checking the fairness of machine learning models. What we found is it's very easy to basically reweight input data and turn what is called a fair classifier into an unfair one. And the point is, we took the COMPASS data here. The blue is the unweighted data where we built a classifier using state-of-the-art algorithms to build a fair classifier. We actually tried different algorithms and all of them showed this result. And then we very slightly reweighted the input distributions to train these classifiers. And you'll see there's like very little difference between the unfair and fair classifiers. And that basically said these quote fair classifiers are not very robust. So what we did was we tried to invent a way to make these classifiers more robust, and the work uses basically a tailoring an online algorithm in a game theoretic way, and we had just heard a week or so ago that this paper was accepted in Europe. So this is the only technical result I have to share with you. But we'd actually have some fairly good results on that. Okay, so now let me start wrapping up. The verification task itself, and the logical framework in which we need to do this verification. How do we? The questions are: how do we check the available data for the desired properties? If we detect that a property doesn't hold, how can we fix the model? This is akin to the fact that most of the successes in formal methods have been in debugging systems rather than proving something correct. One usually comes up with a counterexample which shows why something is not correct. And so this, I believe, will be also true in the kind of the practice of verifying AI. So we should use this feedback in a very helpful manner to either fix the model, fix the property, get more data, and so on and so forth. How do we exploit the explicit specification of unseen data to aid in the verification task? This is analogous to how do we exploit the explicit specification of the environment of a system to help us in verification. And then how can we extend standard verification techniques to operate over data distributions? Right now, they operate over points, data values, but we really need to elevate that so that our techniques operate over distributions. There are many opportunities beyond the ones that I raised for formal methods. I think the fact that currently still AI systems are being deployed to perform a particular task actually gives us an advantage so that we can target our verification for the task at hand. This begs the question of generalizability, but at least we need to start somewhere. I also advocate a kind of correct by construction approach, which would be model synthesis. So you construct, as you're constructing the model, you have a particular property in mind, like fairness or robustness in mind. And so when you're constructing it through the constraints that you have, you can add constraints that will constrain it to promise by the end that it will satisfy that property. The usual challenges of compositional reasoning, compositionality hold here. And then here's that little brief mention of statistical techniques. The statistics community have been analyzing their models for the history of their field. And I think we can learn from some of the analysis techniques that they use. I'm thinking about things like model criticism, which has had a renaissance recently. So that's the end. This is really the framing that I like to pose in terms of how trustworthy AI meets formal methods. Thank you very much.
Thank you so much, Jeanette. That was an exciting talk, and we always have some questions that have been posted in the chat.
Okay.
For you, let me start with the first one. So do we need to integrate probabilistic logics with representation learning, for example, deep learning, to achieve both trustworthy and robustness at the same time?
First of all, I don't know what we need, but what you suggest sounds like a good idea. So do we need to do it? I would say, why don't we try and see what we gain from doing it?
Yeah. So
in
just
other
as,
words, I am actually very open-minded to anything anyone suggests at this point, because as I said, I only have questions. I don't have any answers.
So yeah, that that's to pose this question in a different manner. There are two kinds of, one way to think about the kinds of uncertainty we have. One is the epistemic uncertainty. Is this fact true? That we have formal methods to do that, and there's a lot of work. The other kind, the aleatoric uncertainty, which has to do with distributions, that hasn't been done as much.
That's right.
And what we need is some way of trying to develop new methods that capture both the kinds of uncertainties in the same framework.
That's right. And let me actually give you even a more technical example. So some colleagues of mine, perhaps you know them, Sumanjana, Zhangfeng Yang, have been using this notion of interval logic or interval analysis to prove security and safety properties of DNNs. And not surprisingly, they find lots of flaws in these image systems. And actually, they're using some interesting software engineering inspired techniques. But those intervals are still over like two numbers. What you really want are like distributions or a class of distributions that are related in some kind of interval logic. And no one's done that before. But that's that's kind of the elevation of the mathematics that we need if we're going to ever hope to scale to the kinds of AI systems that we're using today.
Yeah, so that was posed by William Wang. And then let me go to the next question that has been posed by Yushang Wang. So you talked about formally verifying differential privacy and fairness guarantees. These typically depend on an unknown input data and sometimes required to apply to all possible input data sets. Existing work in these domains seem to apply only to very specific cases that do not generalize nor replace human researchers in proving theorems related to these problems. What are your ideas in overcoming these challenges? What branches of existing literature and formal methods should we start looking at?
This is also basically helping me frame the question that if you just think about differential privacy, we have all these formal guarantees for a particular, in some sense, constrained setting where it's just like you're saying, applies to a particular, actually, let's say, all ways in which you might perturb a given data set. Or for fairness, we're usually proving fairness of a machine learned model on a single input distribution, you know, the thing that we trained it on, or something similar to that. Well, actually, what we don't usually prove it at all about anything. And so we need to start freeing our mind and thinking, this really gets at that quantification question. Yeah. What do we quantify over? And then what can we, within that quantification, what can we assert? We you know, for the formal methods community, it's not like we don't like testing, but we like to claim that we can do a little better than testing, because you can never test the program on all inputs, but you could prove a property, a for all property on all inputs, and know, even though you might never see most of the inputs, you can rest assured that the program will be correct. So we don't even know in the AI world what the analogies are. So your question, you know, I think there's a lot in your question, but you're getting at the heart of some of the hard issues. So again, I don't have answers to these.
So is there an analog of model checking when you're starting to look at this kind of programs, that if it's going to fail, then there is a finite model on which it's going to...
Here's what, so there are people in the kind of the formal methods community starting to address some of these properties in certain contexts. So for instance, Sanjit Seshia at Berkeley, who's a formal methods, especially cyber physical system guy, has been looking at how to verify AI systems where he's not actually verifying the machine learned model, he's verifying a system where there's a black box inside. So how does he do it? It's really, it's not, I admire Sanjit, and I think he's doing world-class work. He's using simulation because, well, it makes sense to do that, but it's not in the kind of formal framework that I suggested. So, and that's just for robustness. Sure. So I am truly this is like for the graduate students in the audience, if you do, if you're at all inspired by my talk, you will say 20 years looking back, oh, I heard this like Jeanette Wing person talk about trustworthy AI, and it was brand new. Well, it is brand new. And that's partly why I am, I'm usurping my opportunity at the Responsible Machine Learning Summit and not talking about COVID-19, because I am trying to spread the word. So I don't know, maybe. So for those of us who are familiar with formal methods, of course we think, okay, what's the analogous model checker in a symbolic model, the Clark Emerson Sophocles notion of model checking. What's the analogy in the machine learning world? And that is, of course, the way to think about it, because we're not starting from scratch, but I don't know what it is.
Good.
In fact, here's another one. So many years ago in the 80s with Suo Wiki and Leslie Lamport and Mana Ponelli, we made great progress into dividing our properties into safety and liveness. So we could express any property you could imagine of a concurrent or distributed system in terms of some combination of boxes and diamonds. And that was intellectual breakthrough, because once we had that temporal logic, we could encode it, we could manipulate systems against those expressions, and we could decompose those complicated temporal logic into pieces and do parallel reasoning. All sorts of phenomenal progress was made. Well, we don't even have the equivalent of that.
Yeah. Yeah. Thank you. I think that those are excellent questions for us to be thinking about, and thank you for trying to invoke.
Thank you for having me. I really appreciate it, and thank you for all of you who are in the audience who are still listening.
William, it's over to you.
Okay.
Thank you, Ambuja, and thank you, Jeanette. This is really a wonderful talk because I think it's really thought-provoking. You know, my PhD thesis back at CMU with William Cohen was on probabilistic logic, but I never thought about this connection between probabilistic logic and trustworthy AI. So I really appreciate Janet for the wonderful talk. Thank you a lot, Ambuj, for hosting this session. And we are just about to conclude this wonderful day of event for responsible machine learning summit on AI and COVID-19. So it's a great day of learning experience, and I'm sure that we all got to learn something new, and that's the most important thing. And I really want to just thank all of the session chairs, all of the speakers, all of the panelists, and most importantly, all of you for joining us and staying until the very last minute. And I really hope that things are getting better and we can welcome you to UCSB, the beautiful campus, in person next year. Thank you, and bye-bye.
Thank you. Thank you, Jeanette. Thank you. Thanks, William. Thanks, everyone.
Thank you, everybody. William, don't forget to save the chat messages.